Hey, Rob.
Hey, how are you?
Hey, good, good. How are you?
Okay,
Yeah. So let's wait for a few more minutes
okay.
before our talk. Okay, I think more people are coming. It's 8 p.m. at your time, right?
Yes, that's correct. Yeah.
Yeah, good.
And I'm assuming you can see my slides, right?
Yeah, it works pretty well. Yeah.
Okay.
Okay, so while we are waiting for more people, let's get started. Our day two of this year APNet. So first of all, we'll have a keynote from Professor Rock Green. So let me first introduce Professor Green. So Professor Green is current professor and department chair of computer science and engineering at Washington University in St. Louis. So prior to WST STL. So he was a professor at the University of Pennsylvania. And prior to that, he spent 12 years at IBM T.J. Watson Research Center, okay, in a variety of technical and management positions. So Professor Green got his PhD from Caltech and undergraduate degrees in France. So he's an ACM fellow, attribute fellow, and he was the prior ACM SIGCOMM chair and EIC for IEEE ACM transaction networking. Okay, he received a lot of distinguished awards, including a 20 Infocom 2010 Achievement Award for pioneering contributions to theory and the practice of QoS in networks. And Professor Green was actually has been very supportive to APNet when he was the ACM SIGCOMM chair, okay, in the past 5 years. Okay, so and he today he will give us a very hot topic, a keynote at a hot topic, which is the interaction between machine learning AI and the networks. Okay, so he will illustrate us, give us his understanding and thought about the complex relationship between AI and network, which I believe will be focus of many of us in our research nowadays. Okay, so without further ado, Rock, please.
Thank you, Kai. Thanks for the introduction. And let me just preamble this by saying I'm no AI ML expert, right? So my expertise is in networking, but like in any area, if you want to keep on top of things, you have to actually not just stay with where you are, but sort of adopt sort of the new tools, the new methods that come around, and AI and ML are clearly I was just looking at the set of papers and talks, right? So, it's present everywhere. So what I want to talk a little bit about today is, in some sense, a reflection of my own experience from a networking researcher perspective on, what role I see for AI and ML models and how that role in some sense intersect with networking research, and conversely, how networks might intersect with problems and research in AI and ML models, right? So as I was just saying, that there's obviously no doubt in anyone's mind, right, that AI and ML systems have had an enormous impact, and we've seen it in networks, right? So there's been a whole range of papers that have applied quite successfully AI and ML techniques to solving networking problems, whether it's congestion control or adaptive video compression, you name it. There's been sort of or intrusion detection. Again, you name it. There's been lots and lots and lots of work, and so there's no denying that they've had an impact on networks, right? So they contribute new solution to networking problems, and from that point of view, it's obviously important for any networking researchers to be acquainted at least and preferably proficient in the use of those tools, right? But I think they go beyond that, and that's the part that I would really like to focus on, right? They actually contribute interesting problems to networking researchers, right? So as I said, I'm no AI ML expert, and I'm not going to pretend that I want to do research in that space, but I want to be able to use those tools when they can be applied to things that I'm interested in. And furthermore, if they create new problems in things that I'm interested in working on, that's also great. That's something that I'm interested in. And so what I'll talk today about is sort of an interplay that at least that I've been sort of witnessing and involved in terms of projects that I've worked on, where on one hand, you do have the networks will affect what AI ML systems do, how you design them, how they operate, right? And that interplay, right? The fact that there is now a network that is maybe not a partner, but at least a component of the operation of an AI ML system gives rise to some interesting problems where the network is sort of not the third wheel. It's a core aspect. And then conversely, in some of those problems, in terms of how you go about solving them, the AI ML tools as a tool will often be providing you with solution that you might not otherwise be able to to come up with, right? And so I'd like to sort of spend a little bit of time going over that dynamics. And so I'll be concentrating on sort of three perspectives that are obviously very related. So I've tried to color code them. Green is the network, and blue is sort of AI ML, and gray is some other stuff, right? And so the three sort of perspectives that I want to look at are the following. The first one, which I term input adaptation, is actually in some sense the most basic one. You have an AI ML system, it runs in a server, but that's not where the data that it requires, that it needs, whether it's for training or processing purposes, the data is acquired somewhere else. And so that data has to be shipped across the network to the place where the AI ML system is going to consume it, right? And that network has certain properties, constraints, limitations, and you want to be able to essentially understand how those constraints and limitations affect what you want to do to the data that needs to be consumed by this AI ML system, which is on the other side of the network, right? And so how do I go about massaging that data in a way that is cognizant of both the capabilities and limitation of the network and what the AI ML system is going to try to do with that data? It's not a brand new problem. We've seen it in a number of different settings and applications. If you think about, video compression, right? I mean, we do that, right? We acquire data, where the camera captures it, and then we want to view it, and how we want to view it. We are now the consumer of that data, and how it's going to be sent over the network is dependent on how much bandwidth there is, and given that amount of bandwidth, how do you render the best possible quality for a human viewer that's on the other side? It's a very similar situation, except that now, what the AI ML system is going to try to do with a piece of data is obviously not just viewing it like we do, right? The second and third are actually related in the sense that they both acknowledge the fact that So AI and ML systems are great, but they're pretty compute intensive, right? And so they sort of require access to significant computational resources. And so very often you want to actually take advantage of everything that you've got in terms of CPU cycle, wherever it is, right? And in many settings, that's going to be distributed over a relatively large area with all the pieces connected by a network, right? And so this is yet another instance now where in order to achieve a particular outcome that an AI ML system is trying to realize, the network plays a role because it ties together all the compute components that are going to be involved in realizing that AI ML task. Now, the difference between the second and the third scenario are that in the second scenario that I sort of term selective transmission, what we are dealing with is that you have, in some sense, an independent AI ML system that is doing some work, and then you may decide to stop there because you've got an answer from that first component that's good enough, right? But in some cases, it's not good enough. And so you now have the option, because that first component is usually running on a relatively low power or low capability system, right? If you think about an edge system where you would have lower capability on the edge and higher capability back in the data center, right? You may then decide that if you're not happy with that answer because it was run on a system that had limited capabilities, you'd like to call upon a more powerful model that can run that. And so now you have to send it over the network. And so the question that arises is that if the network has limitation, when do you spend the resources needed to transmit the data over the network, given that there's a trade-off, right? You could spend it on a piece of data for which you have reasonable but not perfect answer, or you could spend it on a piece of data for which you have very bad answers. So obviously in that case, it's always better to do the latter, but there are many instances where the choice is going to be much more complicated than that. The third one, essentially in some sense, go a step beyond, where you're taking advantage of this distributed functionality, distributed compute resources to actually distribute the AI AML model itself, right? So you now break it apart, and you can think of the network as essentially, a big bus, a big switch that connects, the various components that are together running the AMI system, AI/ML model. And the question that then arises: where do you make the cut? What piece of the AI/ML system do you put on one side of the network versus on the other side of the network, right? And that's why I ended up calling it Flix functionality, is because you essentially cut up your AI/ML model, which is sort of a big atomic entity that's performing a certain function, but you now have essentially gone inside under the hood, and you've split it open and put some pieces on one side of the network and other pieces on the other side, and you have to determine how to do that best, given that, again, the network has some constraints. So these are the three things. I'll go a little bit more details in the three of them, and then I'll actually spend probably the bulk of the time on two examples that are sort of illustrative of the first two, in part because these are things that I've worked on, and I've not really worked on the third one, and so I don't really have a particularly cogent example that I could provide. The two examples I want to acknowledge that are actually joint work with several colleagues. Ayan Chakrabarty, who is now at Google, Chen-Yong Liu, who is a faculty at WashU, just like I am, and two PhD students, Jiaming Hu and Ruqi Wang. Jiaming is one of my advisees, and Ruqi is advised by Chen Yang. And as is usually the case, the students did most of the work. All right, so let me start with the first, right? And I've tried to follow a similar format. I've put up a few references. It's by no means exhaustive. It's just to give a sense that there's actually a lot of work that's going on in that space. So I'm obviously not the first one to realize those things. I'm just trying to organize them in a way that I think tried to highlight how these different things sort of fit together. So in the input adaptation case, right, as I was saying earlier, we have an AI/ML system that's fully implemented in an edge in a server, right? And we have data acquisition on one side, and you now have faced with the task of whenever I get a piece of data, given what the network is capable of, how do I best manage, or massage that piece of data so that it arrives at the AI/ML system, and the AI/ML system is capable of generating the best possible result given the limitations of the network, right? So that was, the other example that I provided earlier was the case of video compression, where given some rate limitation, you want to send the bits that are the most useful to the rendering of a video frame that is being viewed and perceived by a human being. In the case of, let's say, a classification system or an object detection system, the information that you want to extract from the data that you've just acquired is obviously different. And so the problems that arise in these settings is, how do I decide what piece of data I want to keep and ship over to the AI/ML system, given that the network is imposing certain constraints, both in terms of the amount of data and when I'm able to sense that data, right? And so the sets of problems that this gives rise to is one of adaptation of the data that you are acquiring, where that adaptation needs to take into account both the network limitation and the goals of the AI/ML system. The second one is so there's actually a pretty long history of sort of problems that are falling under that particular, I would say, umbrella. At least the way I tend to think about it, one of the places I was first exposed to is this sort of notion of cascade of models, right? So AI/ML systems, as we've been discussing, are expensive, right? And very often you may want to essentially look at a trade-off between how much you spend in terms of computational resources versus the quality of the answer that you get, where the relationship is the more you spend, the better the answer. And in the cascade of model, especially since AI models are statistical in nature, you could essentially run a relatively simple model and get a very good answer, and then you're done, right? Or you could run a very simple model and get a not very good answer, and then you cascade on to the next model, right? A generalization of this is this sort of early exit, which is now just a monolithic system, which you have, extended so that at intermediate points within the system, you check on the quality of the results, and if it's good enough, you stop. If it's not good enough, you keep going. In a distributed computing environment, this sort of maps pretty naturally to essentially a question of quote unquote function placement. You place certain modules, the low quality modules are going to be running on low-end compute platforms, while the high quality models, which are more complicated, are going to be running on high-end or high performance compute platform. And usually these are connected by a network. And now we're facing what I was alluding to earlier, a particular situation where if the network has, say, limited capacity, so that you are only allowed to send a certain number of those pieces of data, and you have this local model that gives you an answer with a quality metric for that answer, which one do you send, right? I mean, in order to optimize sort of the global performance of the system, especially in an environment where there might be a whole bunch of distributed local compute resources that are, sort of not coordinated with each other. And so you need policies that allow you to decide this. The third one is again, very closely related, which is sort of this question of, if I have a huge model that might be very expensive or even impossible to run on a single server, I will want to split it up, right? But now I have a network that's going to be essentially in the middle between, which is going to take the output of the first piece, the head part, which has done some of the processing, and then the output of that first part needs to be shipped over the network and then consumed by the tail part, right? And so the question is, where is the boundary between the head and the tail, given that this is going to influence the kind of data that has to be shipped over the network, right? And so, there's a lot of, this is an instance where the presence of a network is actually affecting the design choices of the AI ML system. And in particular, there's been a whole slew of works where you actually research, people have added an autoencoder in the middle of the AI ML system, just for the sake of actually making their choice of the boundary between head and tail the right choice by compressing the data, so that there's, even though it could be a relatively large chunk of data that you want to send, the autoencoder will allow you to compress that so that you can now ship it to the tail part of the model without incurring a huge penalty. And so again, this is an instance where the presence of the network influences the design of the AI ML system. So let me now move on to sort of those two examples and try to make this a little bit more concrete by anchoring into two examples. The first one is an instance of adaptive compression in the presence of a network where the bandwidth fluctuates, right? So pick any Wi-Fi network, right? If you look at any Wi-Fi network and you plot bandwidth, right, or throughput over time, it's not a flat line. So unlike, coaxial cable or Cat5 or fibers, which give you a pretty steady bandwidth, the wireless environment is inherently variable. Right? And so what we're going to be looking at, right, the problem that we are facing is one where we have a data source that is acquiring data that needs to send it over the network to an AI ML model that's, in our particular scenario, is going to be doing image classification or object classification, right? And in between the two, there is a network that has bandwidth that varies, right? And so what that means is, we may not always be able to send everything that we want, and so we need some kind of adaptive speed. All right, so this is sort of the setup that this would be sort of mapping to, right? You have those cameras. This is a conveyor belt. It carries objects. You're trying to pick up what kind of object it is, because depending on what type of object it is, you might make a different actuation decision, right? Sending a parcel to the right or to the left, and that needs to be controlled by a system based on the type of object that's arriving on the conveyor belt. Object arrive at a certain rate, and so you don't have an infinite amount of time to make those decisions. And the camera is capturing a picture of each object and then sends it over typically a low power wireless channel to a server, which then performs this object classification and then sends an actuation decision. The problem is that the network bandwidth fluctuates in a way that is nearly impossible for us to fully predict, right? So it's not as if we could say, oh, yeah, this is, I know ahead of time how many bits I'm going to be able to send, right? And so the problem we face now is we need a compression scheme that is such that no matter how much data I send, right, the classification engine at the server, which will receive whatever it is that I've been able to successfully send, will be able to perform the best classification decision on the basis of that amount of information. So that's the problem we essentially are looking at, which is created by the presence of a network with limitation, namely the fact that its bandwidth is inherently variable and pretty much impossible for us to predict, at least at the time scale where we need to predict it, which is in the rate at which successive objects or images are arriving. All right, so the way we forward this is you have an input, a sequence of images. As I said, they arrive at regular time interval, and that then gives us a deadline for performing our local task of massaging the data, adapting the data to a format that the server is going to be able to consume, right? Send it, and then have it processed at the server, and then have an actuation decision that's being made, with the bandwidth of the network in between being essentially random, a random variable. We don't really know what it is. And our goal is to maximize the accuracy of the system in terms of the decision that it makes, given the transmission deadlines. Namely, we need to make a decision by a certain time, namely before the next object arrives, and given that we can't predict the network bandwidth and how it's going to be varying. And so our compression scheme has to have essentially two properties. It needs to be aware of the goals of the AI ML system, which is object classification. And it needs to be able to operate in a sort of a progressive way, right? No matter how much data I have received, when the deadline ticks, then I have to be able to make a classification decision based on whatever amount of data I have received, right? Now, there's a bunch of, this is again, not a drastically new problem. There are a number of existing options. You could actually say, forget about the AI ML system. We know how to do progressive compression. Progressive JPEG is a perfectly good example. It's actually a very lightweight solution. It can run on pretty much any embedded system. It is also low latency, so you can make those compression decisions pretty quickly, right? The drawback is, as I said earlier, it is not cognizant of the goals of the AI ML system. The JPEG standard was designed based on sort of human beings looking at pictures, right? Which is clearly not the same as doing object detection using sort of an AI machine learning algorithm, right? And so we expect that its accuracy, right, it's probably not the best option. There are much more sophisticated progressive solutions based on recurrent neural networks that are very much aware of what the AI ML system wants to do. The problem is that they are extremely expensive, and there's absolutely no way we can make them run, or at least no way that we have been able to figure out that we can make them run on an embedded device with a relatively low computational footprint. Right? So they provide a nice baseline, but it's not a practical one. And so we need a solution that is aware of the fact that we are trying to do image object classification, but can run on a relatively low-end device, because that's all we have access to in our environment. And so the solution that we ended up sort of homing on, right, is actually using an AI ML based solution, where we're basically going to have a system that outputs sort of a set of features, right, which is sort of the output of the encoder of the AI ML system. But those features will have a property, namely that they're going to be ordered in the rank of importance, where importance is based on the object classification task that the AI ML system running on the server is actually performing, right? And so as soon as once we have that, then essentially we have a solution, because we encode the image. The output is this set of features. The most important one is the first. The second most important one is this second, and so on and so on. And so we start sending the first one, and if we have the bandwidth is low, that's maybe the only one we're able to send. But if there's enough bandwidth, we send the second, the third, and the fourth. And then whatever the edge server receives is going to have access to those features, and then it's going to be using them to do object classification. And it will be able to do it no matter how many features it has received, except that obviously the quality of the decision may not be as high, right? And so now, how does that work, right? So this is actually not a technique that we came up with. It's sort of a technique that's been proposed about 2 years ago, called stochastic tail drop. It's actually a pretty clever and intuitive techniques when you think about it. It's you take an AI ML system with an encoder, right? And it generates a set of features. And then what you do during the training part is that you actually randomly drop or zero out some of the bottom features, right? And then you send that to the decoder and then the classifier. And by keeping that as part of your training, right, you essentially make the system recognize that I better not put the important information in the bottom features because they're going to be dropped. And so this produces an autoencoder where the features are sorted by importance, which is exactly what we want. Right? And so this is essentially what we use, right? We produce this autoencoder, which has these features ordered in order of importance. We send whatever features we can, depending on the amount of bandwidth. If the channel quality is good, we can send all the features. If the channel quality is bad, we only send a subset of them, and then we decode that and then input that into the classifier, and basically let's see how well that works, right? And so this is giving you a sort of a snapshot of the performance. The red, the stars are the system that I was just describing, and we're comparing it to two baseline. One of them is progressive JPEG, which is sort of a basic, sort of equivalent, except not designed for object classification. The other one is this recurrent neural network that I was referring to earlier, which is there just as a comparison point because it cannot run on embedded system. And we've also included a couple of non-progressive baseline where we've just essentially, which can, however, be tuned to produce an output of a given size. So if you knew ahead of time how much bandwidth you had, you could reconfigure your encoder and generate an output that can fit given the amount of bandwidth that you have. But as I said, we don't have access to that information. So in some sense, they are not practical, but they're sort of included there for completeness. And what we can see is that actually this sort of stochastic drop-based autoencoder performs remarkably well, given that it is actually in some sense a very simple scheme, and it has also a very low computational footprint on sort of low-end embedded devices such as the Raspberry Pi. All right, so just to recap what we've just covered, but this was an example of what I'd call input adaptation, namely a scenario where you have a network that is creating problems or introducing constraints for your AI ML system, and where you have to actually decide, given the network constraints and given the job that the AI ML system is trying to do, right? How do you best, select what data you're going to be sending to the AI ML system in order to optimize its overall performance. And in this particular case, we ended up coming up with a solution that was itself using an AI ML based type of approach. All right, let me move on to the second example, which is intelligent edge offloading, again for object classification. So yeah, I'm sort of somewhat enamored of object classification. It was one of the first sort of AI ML systems that I actually was able to understand. So it's in part why I'm sort of pulling on it. Now, that particular scenario involves a low-end classifier, which can run on an embedded device, but is not always the most accurate. And it then has the option of if it's not happy with its answer, of invoking the help of a more powerful classifier that runs in an edge server, and they're connected over a network. But that network is not a dedicated network. It's shared with a whole bunch of other similar embedded systems, and so there are constraints on how much each one of these embedded systems can send over the network, and we're going to be essentially capturing those constraints through in a particular way, which I'll describe in a second, but which is a standard regulating mechanism in packet networks, namely a token bucket. All right, so the environment, you can cast that problem in a very, very similar environment as the one we had before, right? And I decided not to change it since I've already introduced it. Right, so we still have cameras, we still capture images of objects, but now the camera is performing a local classification, and could then, if it's happy with its own result, could actually directly perform the actuation decision. But if it's not happy, it has the option of going out and ask for help from a more powerful server by sending the image over a network. However, its access to the network is regulated. It cannot essentially offload everything. It has a certain budget, and it needs to essentially conform to that budget. And now that creates a new problem, which is how do I use that budget in a way that will maximize the overall performance of the entire system. And as I said earlier, the regulation of transmission is in the form of a token bucket. The token bucket is, I'll very quickly sort of outline it if people are not familiar with it. Basically, you have a certain rate, which is allowing you a certain sort of average transmission rate. So in our case, for example, you can transmit 1 out of every 10 images, right? So that determines your rate, which is 1 out of 10. Now, it may be that, you don't want to transmit image, 1 and 10 and 20, right? It may be that image, 1 and 15, and then nothing until 35, for example, are the ones that you really want to transmit. And so the token bucket gives you that flexibility by allowing you to save some of those credits, those transmission credits, in a bucket. And that bucket has a bounded size, right? So you can save as up to a certain number of credits, and then you can essentially use those credits to send a whole bunch of images back to back if you have saved enough by not having transmitted image for a pretty long time before that. So that's sort of the flexibility that the token bucket is providing you with. All right, so the setup for the problem, the formulation of our problem is, again, we capture images, we do local classification. This local classification produces a confidence a metric in terms of how good of the quality of the solution that has been produced by the classifier. In many of these sort of classification systems, this is in the form of a probability vector, right? Where you have, this is the probability that this object is in this first class, and then in the second class, and so on and so on, right? And so if the classification is perfect, then you have one entry which has probability 1, and all the other entries as probability 0. In practice, that's never exactly like that. But so you can now look at essentially the quality of your output based on the distribution of the classifier output in terms of this probability vector. Right? And then what a standard technique is to actually look at the entropy of that probability vector, and then during training map that entropy to a confidence metric that you use in your decisions. Right? So the camera is going to need to decide whether or not to offload a particular picture based on that output, its local output, right? And it has to, however, estimate, try to guess, how much better will the decision be if it's performed by the strong classifier, by the more powerful model that runs in the server, but it doesn't know what the strong classifier is going to be. And so that's one part of the unknown, right? And the other part is it has to make those decisions based on how many credits it has. If it had no credits left, then obviously the decision is easy. I cannot offload the image even if my confidence is very, very low. If I have lots of credit, then maybe I can afford to be very aggressive and send an image even if my confidence is pretty high. On the other hand, if I don't have many credits, I have to be much more conservative in deciding which image to offload. Right now, the interesting thing is that this is a scenario which is indeed a reasonable or realistic scenario, namely that if you look, and that's sort of based on the sort of the ImageNet sort of set, right? If you look at images that are in that data set, they typically fall in 3 categories, right? One category where both classifiers do a good job, namely the weak classifier or the relatively simple model that runs in the embedded design, embedded system, and the strong classifier that runs in the much more powerful edge servers. They both are able to accurately classify that particular object. There's a certain category of objects for which it's hard for both, right? So neither of them is going to be able to do a good job. But, and that's the interesting category, which is motivating, the setup that I've just described, right? there are actually a reasonable chunk of objects for which you get a low confidence in the local classifier, and a much higher confidence result if you send it to the strong classifier. And so these are obviously the images that we want to offload. Right? The question is, figuring out which one they are, and given that this is not a completely black and white sort of scenario, right? Sort of makes sort of decisions that are aware of both the potential benefits of offloading to the strong classifier, to the edge server, versus the cost in terms of spending a credit on that particular image. All right, so the sort of recap of the scenario, right? Images are coming out. We have a local classifier that makes a decision with a confidence of the quality of that decision. And then it has to make a second decision, namely, is it happy with its local result, or does it want to, ask the help of the remote server given the constraints of the token bucket? Right? And so this is, this interaction where, you have on one hand the goal of optimizing the accuracy of the AI/ML system, and on the other hand, the constraints imposed by the token bucket regulator, which is essentially representing the constraints that the network is introducing. How do you now pull these two things together in coming up with a quote unquote optimal policy? That's where I think, the interesting problem comes out. So the two challenges are, the first one is, given that the local classifier has only access to its own local information, right? It knows how good of a job it did. It has no idea how good a job the remote classifier, the strong classifier that runs at the server, how good of a job that's going to be. And so, estimating that the reward that you would get, how much better of a decision will you be able to have access to if you send it to the strong classifier, that's obviously not an easy task. And then there's also the potential of, the question of, am I spending my credits, my tokens on the right images, right? So, I could say, oh, if I send this image now, I will getting a certain reward. But if I'd waited for the next image, right, I might have gotten a higher reward. And now, depending on how many tokens I have, this obviously is going to be influencing my decision. As I was saying earlier, if I have lots of tokens, I might be a little bit more aggressive than if I have very few tokens. And the third constraint that we are facing is that whatever policy we come up with, it better be straightforward, because we are, in a really resource-constrained environment since we are running on these embedded devices. All right, so the solution that we've sort of honed in is one that uses a deep Q network. So again, right, this is an instance where AI/ML systems provided both the problems and the solution. We had actually an earlier version of that system where the solution was actually not an AI/ML system. It was a standard modeling. So there was a Markov decision process sort of base of approach, which would work relatively well, but was not capable of handling many practical situations, which is what actually motivated us to go and explore this sort of more sophisticated system. So, DQN is a relatively standard but reasonably powerful sort of approach, although there are actually more recent sort of similar techniques of reinforcement learning that actually perform slightly better than DQN. It uses sort of a Q value, which is essentially is an estimate for the reward that your action is going to be bringing you, and you basically in the DQN setup, you actually are training a neural network to estimate those rewards, right? As using a standard reinforcement learning type of process, where you have a certain state, right? Which in our case, actually, the state is the output of the local classifier, its confidence, and the token bucket state, right? And you're essentially trying to figure out what reward you get by taking different actions. And in our case, the two actions that are possible are, do I offload or do I not offload? So it's a binary action, right? And so, you can actually, it's a relatively standard machinery that we can apply to our environment. So let me give you a few examples of how that works, right? So this is a scenario where you can think of, sort of you are in that warehouse, you have a conveyor belt, and the quality of the lighting, depending on the time of day, whether it's during daytime or nighttime, right? The quality of the lighting changes, which actually potentially affects the quality of the local classifier decisions. Or it could be that sometimes people walk in front of the light, and that again changes the quality of the image, right? So here, what this is representing is sort of a scenario where the local classifier alternates or toggles between periods of time during which it's making low quality decision or low quality decisions at a different levels of quality, right? So the y-axis is plotting the offloading reward, which in some sense is measuring the difference between the quality of the local classifier and the quality of the stronger classifier. And if the reward goes up, it means that we are in a period during which the local classifier is struggling. If the reward goes down, it means we're in a period during which the local classifier is doing fine, right? And this keeps toggling, right? But we don't really know when and why those toggles are happening. And so the training of the DQN model, if you have enough samples of this particular type of evolution, will actually be realizing that, yep, the system is actually transitioning between these sort of periods of time during which the classifier works well or not so well. And it's going to be essentially using that information to create a policy, which in our case is a relatively simple threshold-based policy, where you basically, the system looks at the value of the estimate of the reward, right, which is based on the local classifier confidence. And if it's above a certain threshold or below a certain threshold, it then offloads, right, if it has credits. But the value of that threshold depends on how many credits you have. If you have lots of credits, that threshold tends to be higher. If you have few credits, the threshold will be lower. And in addition here, it will also use the information that it has learned through the training process about, have I recognized that this is likely to be a period of time during which the confidence is high, and therefore, I'm going to be getting, few images that I need to offload, or is it a period of time during which the confidence is low and I'm going to get lots of images during which I would want to offload? And so these two conditions are going to create different policy decisions. So, oops, I thought I had, oh, sorry, okay. This is actually illustrating what happens in a scenario where the part in the green circle is, so these are traces where this is a whole bunch of images, right? That's the x-axis. The traces are essentially the y-axis, and each dot is representing an image, and the position of the dot is indicating what kind of reward you would have had if you had offloaded that image. And the color code is indicating the decisions that the policy is making. And we're comparing a couple of different policies, one which is this sort of a DQN policy, and the other one which is a policy that is does not have access. I don't have time to go into all the details, but doesn't have access to all the information. And so here, this is when you are in a scenario where, for example, the reward is high, right? That's what is in that green sort of ellipse, right? This is a period of time during which the reward is relatively high. And so both policies, right, the one that did not have access to, that was not able to learn the structure of the output of the local classifier, that policy is actually targeting images that are have a higher lower reward metric, because it doesn't realize that it is in an environment where on average you're getting much better quality output, right? And so it's actually sending images that don't really need to be sent, right? Because it's not recognizing that this is a period of time during which you have lots of really good, lots of really bad images. The offload, the reward is pretty high, and so you have lots of bad images, and so you need to be a little bit more careful. While the policy that was trained with that awareness is actually recognizing that and is capable of sending only those higher reward images, right? And then in the second round, what happens here is that you have a switch to actually both lower rate at which images are arriving and lower rewards. And so now the policy that was trained to learn to realize that you could have this toggling back and forth between periods of high and low rate, that policy recognized that it's now entering such a regime, and it's actually becoming more aggressive, right? So the blue dot are that particular policy, and it's actually deciding, the reward is low, but I know that I'm stuck in a period where all the decisions are pretty good, and so if I don't upload images, in some sense, I don't spend those credits, I'm going to be wasting them, and so I can be more aggressive in doing that. So the net of it, right, is that what this particular example, I think, illustrated, or hopefully illustrated, is that we were in a situation where we had an AI ML system, which was in this sort of cascade of model or early exit type of model, where you had two components that were connected by a network. And the first component had to decide when to essentially use or rely on the other component to finalize a decision, and do that in a way that would sort of maximize the quality of the global decision that those two components together were making, given that the network was actually imposing some constraints on when it could go and ask for the help of this stronger components, right? And so in this particular case, we again were able to solve that problem, which was created by inserting a network inside or in the middle of an AI ML system. We were able to solve that particular problem by, again, using AI ML solution, although, as I mentioned earlier, that's not necessarily always the case. There are sometimes other approaches that work reasonably well. So let me sort of wrap this up. I think what I wanted to sort of highlight is that networks and AI ML systems have some interactions that contribute new problems for both. AI ML models are certainly very powerful tools, but they are, at least for me, the more interesting part is not just tools. They create in the network settings sort of new problems that are interesting to solve in their own right. There's the flip side question, which is, what we've certainly seen instances where AI ML systems or models have solved networking problems. We've seen instances where networks have influenced the design of AI ML system. But the last example that I gave was one that is certainly fitting in that category. But there are plenty of others. What we haven't, I think, not yet seen, right, is have AI ML system influence the design of a network, right? So what is the best possible network in order to best support the capabilities or the operation of an AI ML system? And so I think that might be actually an interesting question to ask, looking forward, in the same way that, for example, data centers, right, have influenced the design of networks that are used to connect servers within a data center, right? If you look at the structure of a data center network, it's nothing like the structure of, say, the internet or other types of networks. Right? So clearly there was an instance here where the application, the users ended up influencing the network. And it may very well be that in an environment where the producers and consumer of the data are purely AI ML system, you will want to design networks that have particular properties that are very different from the ones that we have in today's network. And I will stop here and take any questions if there are any.
Okay, great. Thank you for the nice talk. I think your talk covers a lot of aspects from, as you said, the input adaptation, transmission selection, and of course, you focus on this two part, and the functionality splitting, I think, also an important aspect, like how to better use AI models in a distributed way. Okay, I guess a lot of questions from audience. So first, I think audience, Sunday, you have questions you can ask.
Thank you. I have a question. Both double Q-learning and DQN based on Markov. I wanted to know what is the difference between double Q-learning and DQN. When to use double Q-learning and when to use DQN. Thank you.
When to use DQN and the other one? I didn't remember. I couldn't hear what.
Double Q-learning.
I mean, right. So I guess for us, it was really a question of both simplicity, right? So we wanted to have the simplest possible model, given that we were trying to fit this on an embedded system. And so that was the primary driver for our selection, for our choice.
Okay.
Was that the question that you had? I mean, I'm not completely sure if I answered it.
Thank you.
Okay. Yeah, let's move to the next one. Yeah, Xingchen, you have a question? Okay.
Yeah. Hi, Professor Guirin. Thanks for your informative keynote. I have two questions related to your keynote. The first one is for your input adaptation part, you have introduced many compression techniques. I wonder if such techniques all have strict theoretical proof, or since we are not AI experts, but rather system researchers, so we can just use the satisfied experimental results as a proof of all these works.
Right. So, so first, I mean, let me again restate that I am not an AI ML researcher, and therefore, sort of my knowledge in that area is obviously limited. However, I think although I think people who are working on optimization and statistics have started coming up with formal proofs of the capabilities of different types of AI ML systems, including deep neural networks. But at least as far as the system that we've used is concerned, right? The results are essentially empirical, right? So in some sense, the quote unquote proof is whether or not it achieves the goal that you're trying to accomplish, right? And so for us, it was able to generate features that were ordered in what seemed to be orders of decreasing importance. And we actually did some cross-validation where you send the features in a different order, and that actually produces a much worse outcome than if you send them in the order that the autoencoder has ultimately sorted them. But there's no theoretical proof, right, that this is optimal in any kind of sense, right? So it is purely empirical.
Okay, thank you. And the next question is, you have introduced a paradigm that you can just use a simple local classifier for easy job and a powerful remote classifier for hard job, right? And this reminds me of the autonomous driving field. For such field, I suppose it is a latency sensitive job because the system must classify objects as soon as possible and then make actions. But for accuracy, it should also have huge computing resources for classification. But obviously, I think
Right.
the computing resources in the car are far smaller than those remote supercomputing. So I wonder if the paradigm you introduced would work for autonomous driving field.
Yeah, I mean, actually, it's a very good point. So I don't know if it would work. I've actually heard the concept put forward by other people. You know, and it's indeed very much, it would fit the exact same paradigm. You have some limited local compute capabilities in the car. You need to make a decision within a certain deadlines. I think, you know, with the advent of 5G and edge computing, where you can have pretty powerful servers that are going to be accessible relatively near the car, right? And with 5G, you can have relatively low latency and reasonably strong guarantees of those latencies. Actually, many 5G networks you can actually implement the equivalent of a token bucket on them. It may actually be a reasonable, you know, option. I think the main cost, the main feasibility issue is that you need a pretty ubiquitous infrastructure in order for that to become reality, right? So that may be possible in, say, in a very large city like Beijing, or, you know, sort of where you can essentially deploy that infrastructure and have the vehicles. The question that arises, you know, what happens if you drive out of that infrastructure and now don't have access to those resources? But yeah, otherwise, I totally agree. I think that's a very interesting and promising sort of setup where you exactly would have those kinds of problems.
Okay, thank you.
Okay, so there's a question from chat I can have to ask. So what are the main challenges for coordinating functionalities of AI or machine learning system between edge and cloud, actually?
All right, so I think that's I mean, so right. So in some sense, you can think of, you know, that there's really a three-level hierarchy, right? You have the local devices, the edge server, and the backend cloud data center. I think so in general, I would sort of split the scenarios in sort of two pieces, right? One where you have predictable networks and the other one where you have unpredictable networks, right? So when you have an unpredictable network, which is what many traditional wireless networks are, 5G is aiming to be more predictable than traditional wireless, but I think it's still, you know, certainly much less predictable than, say, a fiber network, right? But so I think in an environment where you have an unpredictable network, that is in some sense for me the biggest challenge, because you don't really know what you're going to be able to send to that resource, that compute device that you know that needs that data in order for the job to get done. And so I think, you know, in an environment where you are connected, whether it's to the edge server or if there is no edge server directly to, you know, the data center itself, but if there is a component of your network that is unpredictable, and you have obviously some timing constraints, right? You don't have all the time in the world for the data to be sent. That is the biggest challenge. In the environment where the network is predictable, I think then I think the challenge boils down to cost, right? Is, you know, if I can afford, you know, infinite bandwidth, then there's no challenge, right? I mean, the only challenge is going to be compute resources, and then you might actually, I mean, if you think about it, right, the token bucket regulator is helping, that I was referring to earlier, is helping both the network and the server, right? If you overload your network or you overload your server, you get a bad result, right? And so you want to avoid scenarios where you're going to be overloading some of the resources that are required in order for the job to get done, right? And so now if you have no cost constraint, then there's no problem. I think, in that second environment where the network is predictable, when the resources are predictable, the biggest challenge is essentially coming up with the best possible solution under cost constraint.
Okay. All right. So does that answer your question, Jinbing?
Yes, thank you. Thank
Okay.
you very much. Yeah.
Okay, great. I think time is up. We need to move to the next session. Let's thanks again for the great talk. Thank you, Ron.
Sure, you're welcome.
Okay, so next, yeah, great. Thank you.
Enjoy the rest of the conference. I'm going to go and grab something to eat. So.
Okay, yeah, take your time. Thank you.
Bye.
Okay, so let's have maybe a 1 minute break before we move to the next session of industrial spotlight talk. Okay, so. So Alan, you will take over. Okay.
All right, yeah, let's wait 1 more minute. All right, I guess it's time. So hello, everyone. My name is Alan Zhaoxing Liu, currently assistant professor at Boston University. So I'm the session chair of the second Industrial Spotlight talk, featuring 3 excellent, exciting talks. So right now, we have the first talk from Yongguang Zhang. I'm not sure if Yongguang is here. Can you start to share your screen and your slides? All right, excellent. So let me do a quick introduction. So I think it's my great pleasure and honor to welcome Yongguang Zhang, who is a senior principal researcher at the Office of CTO, Azure for Operators at Microsoft. And previously, he led the Microsoft Research Special Project, Cloudification of Telecom Network Infrastructure, which is the topic of today, that led Microsoft entering this business. And he received his PhD in computer science from Purdue University in 1994. And he was a recipient of Usenix Test of Time Award at NSDI 19. And he was a general co-chair of ACM Mobicom 09. And he is currently an IEEE fellow. So let's welcome Yongguang.
All right, thank you very much. Thank you, Alan, for the introduction, and thanks for the organizers who invited me to give an industry spotlight talk. I work for Azure for Operators, which is a group in Microsoft setting out to build the future of telecom. So this talk is to explain the current industry trend of telecom network cloudification. So let me start by saying that this is not a research talk. I will focus on what Microsoft is doing and what the broader IT industry is doing. Much of this talk draws from our research and project experience from past 6 years. 6 years ago, we started a Microsoft Research Special Project to look into telecom. It turned out that this is a very successful project because it had led the company into this direction. Now, I'd like to help the academics and the research community to make sense of what we are doing. This community has driven a lot of networking events in the past, like the internet, data center networking, SDN, and so on. But very few is involved in the current telecom network revolution. I hope to give all of you, get all of you excited about this new trend, and so you can provide an R&D leadership here. And before I start, I'd like to thank my colleagues at Azure for Operators. It is not possible for me to list all the names, but I do want to call out Bosidat and his team. Many of you know him. The team were with me in this journey since day one. All right. So today we're going to talk about cloudification of telecom network infrastructure. The question is the following: what are the best ways to build a telecom network? In particular, a mobile cellular network like 5G or 6G. So this is a system implementation issue. So my thesis is the world's cellular network is better built on the global cloud infrastructure. And in fact, the industry is going this way. So put this to a historical perspective, networking has gone through the telephonies era, the internet, and recently SDN. And I believe we are now in a new era. We are witnessing how cloud computing changes how we do networking. So to illustrate my point, let me start with a quick introduction of the cellular network. So what is a cellular network? A cellular network blankets the world with cell coverage and connect mobile users to the internet. More precisely, it connects mobile device to the mobile service backend in the cloud. Because nowadays, most of the service backend are in some sort of clouds anyway. And cellular network is also massive. We have millions of base stations worldwide and hundreds of clouds that can host mobile apps. And this can span thousands of kilometers. Obviously, we need some layers of link aggregations and data reductions. This is called the transport network. In terms of network processing, the cellular network has three major components. RAN, the radio access network, is the well-defined process that handles signal processing, medium access, and protocol conversions. Now, this picture has a lot of internal steps. I just put it there, but I don't expect you to read this. I only need you to know that it involves lots of computations and header manipulations. And there's nothing special about this. And our colleagues in EE or communication departments have been working this for decades. So these steps are pretty standard. The packet core network, or simply just core, handles the roaming, charging, section management, and so on. It also involves a lot of header manipulations and bookkeeping. Finally, OSS, BSS stands for Operational and Business Support System. This is usually not what we are interested in, but it's quite important to the network operation. Now, how do we build cellular network today? Today, each mobile operator is responsible to build out the physical network. They would buy equipment from the telco equipment vendors and install them in various locations. They would build out the cell size, they will lay the fibers, build out the transport network, set up the nodes in between. But today, the equipment is mostly from the top three vendors, Huawei, Ericsson, and Nokia. They have something like 80% of market share. But this is changing now. The industry trend is to move away from this purposely built monolithic hardware. Operators are demanding that the industry to open up, to adopt new technology. So more and more you will see cellular network equipments use virtualization technology, adopt standard telco-grade x86 servers, and move towards open interface and disaggregation. But still, cellular network build-out model has not changed. It is still operator acquiring hardware, now plus software, and build out the physical network. Nevertheless, I think it's time to rethink this model. So let's look at cellular network on a clean piece of paper. So fundamentally, what is cellular network? Let's start at its input and output. So the input is the continuous wireless signal being picked up by the base station antenna. The output is a stream of IP packets destined to the mobile service backend. Now, this is just one direction. The other direction is kind of everything in reverse. So let's just look at this one direction only. So we have input and output. The white space in between is the cellular network. Now, we learned from our colleague, Professor Lin Zhang from Yale, who has been saying this for many years, that wireless is essentially a compute problem. Signal processing is just numerical computation. MIMO, multiple input, multiple output, is just lots of magic competition. Routing, switching is just table lookup. So you can say that a mobile cellular network is just a distributed computing system problem. Okay, you will say that is too generic. Oh, we can be more specific and add a lot of adjectives. The input and output are geographic significance, and this has to have some real-time constraints. Some computation has to be done in microsecond, and some have to be done in millisecond. And the scale is massive. We have tens of millions of base stations to deal with, and each potentially generating 100 gigabit per second. And of course, the whole system has to be reliable, has to be 5.9, has to be secure, has to be trustworthy. So we can say that this is a massive, mission-critical, real-time, geo-distributed computer system. But it's a distributed system, nonetheless. Okay. So what is the right compute infrastructure to solve this problem? What should be the hardware, the OS, and the software? So I believe, as of today, the most suitable hardware is the hyperscaler distributed cloud infrastructure. So hyperscaler cloud companies like Azure, Amazon, Google already have hundreds of mega data centers all over the world. They are extending out to the edge. There will be many more edges. The near edges are large data centers, probably dozens of racks. They're not as big as the mega data centers in like the cloud regions, but probably hundreds or thousands of servers, nevertheless. And there will be even more far edges, which are smaller data center, probably a rack or two, tens of servers. And to the cellular network, this far edge is just the first order of aggregation. And probably one far edge serving dozens to hundreds of cell sites. And the near edge will be the second order of aggregations, with one near edge for dozens to hundreds of far edge. Then we need another layer on top of it, which we call it the distributed cloud services. It's like the operating system. It manages the hardware resources from compute to storage, from bare metal to VMs, from transport network to hybrid clouds. And it provides the proper distributed cloud services abstractions, such as a container service, and take care of the automated orchestration and management, so on. Then the cellular network is just cloud-native functions and services living on these distributed cloud services. The radio access network, the RAN, will be on the cloud. The core will be on the cloud. OSS, BSS will be, and actually it's already mostly on the cloud today. So another reason we need to look at cellular network as a distributed system is because different components has essentially different computation characteristics. So this is the same RAN and cloud diagram I showed you before. If you look at the feature for each submodules, along the aspects of implementation techniques, latency budgets, the bandwidth needed for each submodules, and we will see that the most suitable hardware and location will be different for different modules. For example, the physical layer, the PHY, has a very tight execution time constraint and need to process orders of magnitude more data than MAC. So they shouldn't be put together in a monolithic system like today. And the industry actually come to the same conclusion and has already proposed several ways to split up the RAN. So this is the well-known option A, option 72, and option 2 split. And further, the industry also wants the open and standard interface between these split. The openness will allow vendor diversity, meaning that the new players can start with the small pieces. They don't have to have the entire RAN, but they can be specialized on the small pieces, but can still be able to interoperate with other pieces. Another benefit of open interface is now we are able to collect the inside data informations from all this internal interface. There are also other ways to split this, like the user plane and control plane separation, and also horizontal splits like the network slicing. What I want to say here is that once a black box of cellular network is being opened and being disaggregated, each component can find its best location and best platform to run on. The current industry best practice is to divide the RAN into RU, DU, and CU. RU stands for radio unit, DU stands for distributed unit, and CU stands for centralized units. The core network is also divided into two functions, the control plane and the user plane. Here is the common practice on where to run these functions. RU runs on the cell side, DU runs on the far edge, and CU and core runs on the near edge. But because this is a codification, operators are freely run them anywhere they want. So you can run it DU and CU at the cell side or core network or CU on the public cloud. These are all possible. So what are other benefits of cloud infrastructure? Now, cellular network can enjoy all the benefits of cloud computing that other industries has already accustomed to. For example, the cloud platform will take care of all the compute resource management, and cellular network vendor and operator only need to focus on improving the business without worrying about running the infrastructure. Let me just give an example of a cellular network. Traditionally, RU, DU, CU core connection is static, and RU will bind to a particular DU server. But with cloud computing, you can do it differently. You can put many DU servers in the pool and have a software load balancer in the front. In addition to load balancing, you will also get reliability and availability and power saving by scaling the servers up and down. Or you can skip the far edge and go all the way to near edge. Remember that near edge is bigger than far edge is big. Near edge is bigger than far edge, and the same amount of compute is usually cheaper in a larger data center. So you may want to do that if you have a network slice that is not latency sensitive. Also, if you are in a dense area that have more than one far edge nearby, you will have a choice. You can go to an Ericsson RU that may be more efficient or have better features than others, or you can go to a Nokia DU running elsewhere. So how real is this codification visions? Actually, this right now, this has a wide industry involvement. including many newcomers and many non-telecom and traditional not telecom players. So this open disaggregating cellular network approach with the codification vision actually get the industry very excited. So a lot of companies in different domains come together. The anchor of these new ecosystems is the cloud company, Microsoft, Amazon, and Google Cloud. So I put a lot of logo here, and this is not meant to be a complete listing. And we just want to show you that there's a lot of excitement and there's a lot of energy in this domain. And I will further argue that for building a distributed system this big, naturally, Microsoft, Amazon, and Google Cloud, and these three hyperscaler cloud companies are probably the most suitable to take on this task. So Microsoft CEO has famously declared that Azure is being built as the world's computer. So if Microsoft has these ambitions to building the world's computer, then this computer should help solve the world's cellular network problem. So in fact, this is what we're doing. Microsoft formed the Network 4 operator group 2 years ago. We took some leaderships from Azure Networking. Actually, both CVPs of Azure Networking plus some dev managers and program managers come to set up this new org. For those who know about Azure Networking, we only have 2 CVP, and both are contributing to this effort. Albert Greenberg, many of you know about him for being in this SecCom community. Of course, he left a couple of months ago for Uber. And we also took 20 networking researchers from Microsoft Research. Many of them you all know, well known in the SecCom community. Then we acquired 2 companies, both were leaders in the cellular network virtualizations. And we also acquired AT&T's Network Cloud. And AT&T is the pioneer in network virtualizations. They start building the AT&T integrated cloud, or called AIC, 8 years ago. Now this is part of Microsoft now, and because it's not economical for one operator to build a cloud technology only for one operator. With Microsoft, we now build for all operators in the world. So with Azure 4 operator, we now have over thousands of engineers working on telecom problems. We currently have several products. Well, let me just highlight 2. The first one is called Azure Operator Distributed Services. This is the distributed cloud services layer that I described in the architecture slide. And the other product is called Azure Operator 5G Core. Now, Microsoft is a telecom solution provider now. This is a cloud-native core network that can run on public cloud, on edge, or on operators on cloud. So, in fact, AT&T is using this product in its 5G standalone network. Finally, we have the office of the CTO team, who's doing research and technology development in RAN, in 5G, 6G, in anything that will make cellular network run great on Azure. So let me give you an example of a cellular network that is built from Azure for operator products. So we will start from the nearest Azure region. If we don't already have edge infrastructure, we will find out the best location and fiber runs. Microsoft will design the far edge and near edge. I put some approximate numbers here. Edge configuration varies, depends on many factors. Depends on the fibers, the location, the user densities, and many factors. This is just approximations. And and then it can grow. If the user demands grows, then you can always grow the far edge and near edge. Then the hardware vendor and rest of the ecosystem will build the hardware. Operators will put them in the right places. Then they will load Azure for operator distributed services. Now, once that is running, this layer will tie everything together as a distributed cloud infrastructure. So next, the operator can choose what version of cellular software or service they want to use. They can choose anyone's RUDU, CU, anyone's core network, although Microsoft, we have one too. They can use us or they can use anyone else. And they also can use anyone's OSS, BSS to build up a satellite, a cellular network this way. We are working with AT&T on this. So AT&T's next generation network is building out this way. Now, we are not the only one. Amazon is doing similar things. So if you look at the Amazon's architectural design, it's quite similar. They have distributed cloud services, which is the underlying infrastructures that connects all the Amazon regions and the Amazon edges, powered by Outpost. Radio access networks runs on this cloud, core network runs on this cloud, OSS, BSS runs on this cloud. The Dish network is a completely built for the cloud. So Dish network is the number 4 operator in the US. Amazon is building the network infrastructure for Dish. Google, the same thing. Google have similar, they have distributed cloud services called Google Distributed Cloud Edge, GDCE. And then you can see that the RAN runs on the edge, the core network runs on the cloud, OSS, BSS runs on the cloud. So all 3 of the hyperscaler clouds is all have similar vision one way or the other to cloudify cellular networks. Now, I'll give you some further examples of how this changes how we are thinking. Now, let me ask you, let me pose these questions. So when we're building the whole cellular network, shall we build the cellular first or shall we build edge first? But the traditional thinking is that you build a cellular first and edge is just optional. Look at the 3GPP 5G architecture. Look at the ASIC MAC, multi-access edge compute architecture. You're going to build a RAN, you're going to build a cloud, and then you're going to do a local breakout to put in the infrastructure to run edge compute application. But the result is that operators fail to find material edge business to justify this edge deployment. So at the end, we'll find that there are a lot of 5G networks out there. There are very little, none meaningful edge business, third-party edge application business. We can talk about smart driving, you can talk about AR, VR, but they're just not there. So instead, we should look at this differently. So the cloudification approach will call for we build the edge first. We should be building a general purpose edge platform that can provide edge compute services for any application. Then the cellular network, the RAN and the core is just an app run on this edge. And together you can run other apps, AR, VR, gaming, they're all just app for this platform. So together, so all these applications will drive the edge deployment. And this is actually what's happening now. You don't see operator deploying infrastructure to support edge compute. Instead, you see that hyperscaler cloud company deploying a lot of edge compute infrastructure, and they will be powered edge application, and they will be powered cellular network as well. Now we'll come into a research question. So when you are saying RAN and other non-RAN edge application can share the same platform, how can they share compute? And our observation is the computational load for RAN is actually intrinsically non-uniform and sparsely. Even with a RAN pool, even with multiple cell size aggregated together, there's many factors determining on the amount of computation for the RAN. For example, the number of active users, the signal quality, the coding, the behavior. So that determines that the amount of computational node will not be uniform across time. But when you run the RAN on the cloud, you have to allocate the computational resource at the peak load. Otherwise, you will have missed deadline. So the average to peak ratio is usually below 30%. So we have a internal research project to look at these problems. So how do we run RAN together with non-RAN workload? And we come up with an approach that we will schedule CPU tasks at 20 microseconds time slot. We will anticipate, we will predict how many slots needed for each RAN task with the predictive modeling. Then we will allocate sparse slots, those slots not used for RAN, to non-RAN workload. The result is that we apply this to a commercial RAN system, we would be able to reclaim more than 70% of CPU cycle with a 5-9 reliability requirements. So that 70% CPU cycle will be able to use for other edge workload. I will refer you to the SIGCOMM publication last year for details about this technique. These are just examples of the new research that we can do on this type of platform. So another work that we think that it would be very interesting is to look into the cellular network data analytics. Now, in the past, the cellular network is a black box. You will not be able to look inside. You're not going to know what's going on. But with the cloudification approach, the distributed cloud services will be easy to create a data pipeline to collect the operational data, both from the platform, from the hardware, and also from each individual cellular network components. And those data will be able to collect and store on the cloud storage. And then we can apply cloud AI, cloud machine learning on this data to derive a lot of information from them. So in fact, we're doing this. Azure Operator Distributed Services is building up this data pipeline. But we need a lot of works in like understanding what data we should collect in each of the RAN processings and how to apply AI and machine learning modules to this data. So let me conclude my talk by saying that I believe mobile cellular network is just a distributed compute problem. I will argue that the best system implementation infrastructure is the hyperscaler distributed cloud. And I've shown you that this is actually indeed is the industry trend. And Microsoft has created 1,000 people organization called Azure 4 Operator to build out this vision. And I further believe that this is going to be a hot topic area for networking research. We are in the new areas that cloud computing will change how networking is done. We'll have a lot of real and open problems for academics. I hope to get all of you excited and spend your time, spend your PhD students in this topic, and we are very happy to work with you. I can open for question now.
All right, thank you, Yongguang, for the great talk. So I think let's start some Q&A. If you have any questions, please raise your hand or just speak up. All right, let me monitor here. We got a question from the chat. So question from Tao Sun from China Mobile. The core network of 5G has revolutionarily transformed to SBA. So how you see the difficulty of cloudification of RAN? The computing force of RAN use of like x86 or FPGA or other domain-specific computing that can be shared in the cloud. Can we achieve end-to-end SBA in 6G? So I think there's a couple of questions. The first question is how do you see the difficulty of cloudification in the radio access network?
Right. Okay. So there's two questions, right? So one is about the core network. The core network is the SBA architecture. How is it being codified? So this has been containerized. Each of these functions. Let me put up the slides that I have all the components. So each of these components has been converted into container services, and they have been individually implemented as containers. I have not been prepared to get into details about how each component is being implemented, but that is basically how we have been doing that in Microsoft, and I believe Nokia is doing the same thing with their Nokia Cloud network core. Now, in terms of the question of a RAN and especially special hardware, I mean, the general industry approach would be using hardware acceleration. So our approach is that the far edge of design will include specific accelerators hardwares. So today, the most common accelerator is probably be the one in Intel. Of course, you can use FPGA, and there are other companies. NVIDIA's proposing using GPUs. There's Marvell. There's like Qualcomm's. So I mean, all these silicon vendors, they are all coming up with physical layer reference design that tie to their silicons, and then layer 2, layer 3 OEMs like Altron, Radisys, we are building up reference design to integrate it with these new silicons and the new lower layer processings into the silicons. And these are, when they are done, they are just containers, either running on a VM or running on a bare metal. And they would be orchestrated the same way as other network functions. But you just have to, I mean, the cloud platform just have to understand this particularly container require this particularly accelerator. You have to match it, match to the right server that contains this accelerator. So you're not going to orchestrate a version of radio access network that require a Qualcomm accelerator to far edge that does not have Qualcomm chipset.
I see. Thanks for Tao said thanks for the great answer. I think our next question has come from the chat from Rajan from National University of Singapore. He is asking, what's the current capability related to radio unit and data unit, distributed unit assignment? Can the uplink traffic from one RU be split and processed on different DUs?
Yes, that's I mean that basically is the idea. So right now, I don't know about which particularly RU be able to support this kind of a functionality, but the industry is moving this way. So we will have RU be able to talk to different DUs, and we will be putting up this kind of like the load balancer and splitting like I described in these figures, that RU will hit the load balancer, and the load balancer will distribute it to any DU that's appropriate. So you will have a RU connects to different DU in a different time, different slice, and they can actually on the flight. So it is possible that one DU goes down, you can immediately switch the RU connection to other DU.
All right, thanks a lot. So I think given the time, so we can move our discussion offline. And let's thank you again, Yongguang, for for the great talk. Thank you very much.
Thank you.
So our second speaker is Yuliang Li. So Yuliang, are you here?
Yes, let me present.
Can you start to share your screen? All right, so let me introduce Yuliang first. So Yuliang Li is a researcher at Google Network Infrastructure, who is focusing on high performance network transport and cloud synchronization. So his work, he won the PhD SIGCOMM dissertation award for his PhD thesis, and also the Harvard CI's Outstanding PhD dissertation award. Prior to Harvard, he received his bachelor degree from Tsinghua University. Let's welcome Yuliang. Yeah, Yuliang, please go ahead. Hi, Yuliang, are you muted?
Can you hear me now?
Yes, we can hear now.
Can you hear me? Oh, okay. Yeah, hi everyone. Thank you, Alan, for the introduction. So I'm going to present at Google what we are doing for clock synchronization. And we built a system called Sundial that can provide fault tolerant and achieve very tight clock synchronization in data centers. So in data centers, the synchronized clocks becomes more and more important. They can simplify or improve many existing applications, such as distributed databases or getting consistent snapshots. For example, both Google and Microsoft both have built some distributed system that use a protocol that uses synchronized clocks. So which means the more precise clocks are synchronized, the higher performance they will have. Besides, we can also use the synchronized clocks to enable new applications, such as network telemetry, one-way delay measurement for congestion control, distributed logging and debugging, and ordering different events across the whole network. And we believe there will be more applications if we really have synchronized clocks that are tightly bound, whose precision are tightly bound. And we find that the bound is actually a key metric in production. We call it time uncertainty bound. This notion is first introduced by the TrueTime from Google. And this bound is very important for the correctness of applications. Let me give an example. So in many distributed systems, the wait operation is very important for ensuring ordering and consistency. But the way it works is like this. Suppose server 1 read a shared value at its local time t. So its local clock report t at this time. And another server 2 wants to write to the same shared value x. But because their clocks are not synchronized, so the server 2 may read its local timestamp smaller than t, right? Although the actual event is later. And this is inconsistent. So one way to avoid such inconsistency is to, for the server, do not read x immediately, but wait for a while. So the server read t first, and wait for a period, and then read x. And the wait time should be long enough to ensure all other clocks in the same cluster must have passed time t. So the key question is how long we have to wait. If it's not long enough, it means it will cause mistakes in applications, and that's unacceptable because they can affect hundreds or thousands of different services and billions of users. So we must have a time uncertainty bound to help us decide how long it has to wait. And this bound must guarantee correctness. We not only need a bound, we also need a very tight bound today, because both the latency in the network and on the host are going down to microsecond level. So the time uncertainty bound starts to become the bottleneck. A recent study shows that even 10 to 20 microsecond time uncertainty bound can cause 25% extra median delay. So we built Sundial to provide sub 100 nanosecond time uncertainty bound, even under failures. And this is 2 to 3 orders of magnitude better than previous designs. Now let's start from the state-of-art clockwork synchronization. The basic building block is to calculate the offset between two clocks. For example, between clock A and B. This can be done by sending a pair of packets. A send a packet to B and B send back. And the offset can be calculated by using the sending time at A minus the receiving time at B plus the one-way delay. And because we don't have, there's no way to get to measure one-way delay. So we have to use RTT to estimate the one-way delay. And second question is, how do we send the messages? Many systems, they send message over a path of multiple hops. But this can introduce a variable and asymmetric delay because the forward path and reverse path can be different. And also there can be queuing delay in the switches. So this means the RTT is a noisy estimation of the one-way delay. So it will make the offset calculation inaccurate. So the best practice is to synchronize between neighboring devices. So yeah, the devices that only one link that connecting them, like neighboring switches or the TOR and the NIC. The benefit is that it has fixed and symmetric delay, because on a link, the forward and reverse delay are almost the same, right? It's pure physics, and there's no queuing delay. Now we need to extend this pairwise to network-wide synchronization. The common practice is to structure the whole network into a spanning tree, starting from a root node, which typically has a GPS that knows the ground truth. And that root will distribute the clock value along the tree edges to all other nodes. And finally, we need to do this synchronization periodically because the clocks can drift apart over time. So we need to periodically synchronize all the clocks. As a result, the time uncertainty bound is also a periodic function. It will growing, and after a synchronization, it goes down to a low level and continue growing. How large the time uncertainty bound depends on two factors. One factor is how long it has been since the last time a clock gets synchronized. So it is now is the reading time, now minus the last sync time. Another factor is how fast different clocks can drift apart. We will show that both factors can be affected by different types of failures. The maximum drift rate can be affected by frequency-related failures, such as cooling or voltage fluctuations. And there are connectivity failures, such as link device failure, that can break the spanning tree and disrupt the synchronization for a long time. And because the time uncertainty bound consists of the product of both factors, no previous solution can achieve a very low time uncertainty bound. So now let's look at the different type of failures. The first type of failure, they have impact on the maximum drift rate. This is because the clock drifts because their oscillator, right, that drives the clock. The oscillator frequency can change over time, especially when the temperature or voltage changes. For example, some oscillator can have 100 ppm frequency change over a range of temperature in the specification. 100 ppm means it can drift 100 microseconds per second. And there's various failures that can cause such large variation, such as cooling failure or even fires in data centers. So we must set the maximum drift rate very conservatively large in production to guarantee correctness. Actually, someone may ask, what if we'll do it more aggressively? Actually, we have tried before, but when a cooling failure happens, we see a huge number of clock-related errors, which is unacceptable. So to guarantee correctness, we have to set a conservative maximum drift rate. Then this implies if we want to keep the time uncertainty bound very small, we need a very small interval between synchronization. So we need a very frequent synchronization. But frequent synchronization alone is not enough because there can be other failures, such as switch or link failures, that break the connectivity of the spanning tree and cause a long period of no synchronization. For example, if this link goes down, and node B will stop synchronized to A, and it takes a long time for it to recover. So the B's time uncertainty bound will continue to grow. That means for all these nodes, whenever they are affected by failure, their time uncertainty bound will continue to grow to a large value. But this is not the only problem, because not only B, the whole subtree of B under B, they are all affected. Existing time clock synchronization protocol, they try to continue synchronization even if there is a failure. They try to continue synchronization in the subtree. In some sense, it makes sense because at least the whole subtree is still synchronized. But this also means all these nodes, they continue receiving message. So they don't know they are affected by link failure. So, which means they don't notice the failure. Therefore, in order to prepare for the worst case, they have to report a large time uncertainty bound all the time to prepare for the unnoticed remote failure. And this is terrible. how large the time uncertainty bound depends on how long the connectivity failure takes time to recover. So the second requirement is very fast recovery from the connectivity failures. So we build a sundial based on these two salient features. We use a hardware-software co-design. In the hardware, we build message sending and processing, so that it can have very low overhead, even if sent frequently. We also build failure detection in the hardware. The hardware, when it detects failure, it reports to the local software in the same device. And the software will immediately enable a backup plan by reconfiguring the hardware to restructure a new spanning tree. This loop is pure local, so it's very fast. The backup plan is pre-computed by a centralized controller. This can take longer time, but it's not on the critical path. So now let's look into the detailed design. In hardware, we have we designed three key aspects. First is, as mentioned, very frequent message every around 100 microseconds. The second, and because of the frequent message, we can also detect failure very fast using a small timeout. For example, when this link fails, the node stops receiving message, so it can use a timeout to report a failure. But remember, we also have other nodes that are further away from the root, and they also need to detect failure that are remote to them. So the third key feature is to enable remote failure detection and design asynchronous messaging. By synchronous messaging, we mean a node can only send a message when it receives one. So all the nodes except the root, they can only do synchronous messaging. Only the root can send the message spontaneously. And because of the synchronous messaging, when a link goes down, the whole subtree all stop receiving message. So all of them will get timeout. After timeout, each node that gets timeout will try to recover by turning to a backup parent. And this will distributedly form a new spanning tree that recover the connectivity. The backup parent is pre-computed by a controller. So now let's look at how the controller pre-compute the backup plan. The backup plan has one backup parent per device. And there are many multiple options for each node as its backup parent. For example, in this example, the top node is the root, and the dark arrows are the edges of the spanning tree. The dashed line is a link that is unused for synchronization, and the red arrow denotes the backup parent. In this case, the option 1, it can recover under this link failure because this path can lead it to the root. But under a different failure, under this node failure, it doesn't have any path connect to the root. So this option doesn't work. On the other hand, option 2 works for both failures. So this means we have to be very careful when picking the backup parent for each node. At the same time, devices cannot distinguish different failures because all they observe is that they stop receiving message. They don't know which switch or which link fails. This means we have to design a backup plan that's generic to different type of failures. By generic, we mean it has to handle any single link failure, any single device failure. A root failure is a special case, which needs special handling. And beyond the single failure, there are also concurrent failures that can cause by fault domain failures. In this talk, I will only talk about root failure and domain failure. But all the details are in the paper. So the backup parent have one backup parent per device, as we previously discussed, and also one backup root globally. This is for handling the root failure. The backup root node, normally it's a normal device. So what makes it special is that when the root fails, it elects itself as a new root. So the key challenge is how does a backup root detect the root failure? Well, actually, not detect root failure. It can always detect root failure. It can detect all the failures, but how does it distinguish root failure from other failures? This is non-trivial because, for example, the dark blue node is a backup root. But when this link fails or this root fails, all it sees is that it stopped receiving any message. How does it know if it's a link failure or root failure? So our key idea is to find some independent observation nodes. By independent observation, we mean some node that can independently observe the root. This node, no matter what failure that affect the backup root, this node can continue to see the root. So we can find a node from this set of independent observation nodes. And we set the backup parent of the blue node from that independent observation node. In this way, if a non-root failure happens, the dark blue node continue receiving message along this path. But when a root failure happens, then there will be no message in the entire network because only the root can spontaneously send messages. So on the backup root, it has a second timeout. The first timeout, on the first timeout, it will turn to its backup parent. But if it continues to see no message incoming, then it knows the root is done. I have to become the new root. Besides the root failure, we also need to handle fault domain failures. This is because if one domain failure breaks the connectivity of a node, and at the same time also take down the backup parent of the same node, then this node cannot get synchronized anymore. This means in the computation of the backup plan, we have to handle this case. So we evaluate Sundial in a large testbed with more than 500 servers and more than 200 switches. And we'll compare with other state-of-art solutions. Since they don't provide a time uncertainty bound, we also enhance them to provide a time uncertainty bound. And this is the key metric that we evaluate. We evaluate under different scenarios, including normal time when there's no failure, and also inject different failures. During normal time, we plot the distribution of the time uncertainty bound of different approaches over all devices and over all time. We see that Sundial reduced the time uncertainty bound by more than 2 orders of magnitudes. And even the maximum value we observe is only 43 nanoseconds, which is very small. The reason other approach has to report a large bound is either because their synchronization interval is large, or most of the device cannot detect remote failure, so they have to report a large bound all the time. And during the failure, we also look at the performance across different approaches. And we also see Sundial can provide more than 2 orders of magnitude lower time uncertainty bound. This is because when the failure happens at second 1, at 1 second, it very quickly recovers it. So it has only a very small spike, and then it go back to a very low bound. And in order to understand how Sundial's different techniques helps, we decompose it into 4 stages. Starting from the baseline, which is PTP plus the time uncertainty bound. After we add the frequent messages, we can bring down the bound by an order of magnitude, but we cannot bring it down any further because most of the node, they cannot detect remote failures. So they have to always report a large bound to be on the safe side. Then after we add synchronous messaging, all the nodes can detect any failure that affect them. So they can safely report a small bound when they don't see any failure. But when failure do happen, they have to their bound will grow. Finally, by adding the backup plan, Sundial can very quickly recover from any connectivity failure. So it can provide very tight bound. We also show Sundial can improve application performance. For example, we improve Spanner. In Spanner, we show 3 to 4 lower commit with latency. And in congestion control, with the synchronized clocks, we can measure one-way delay instead of RTT. So in Swift, by using one-way delay, we see 60% higher throughput under reverse path congestion. And we are also working on more applications using Sundial. So to conclude, we find time uncertainty bound is a key metric in production. And existing solutions, they fall short because of failures. So we build Sundial based on hardware software co-design. In the device hardware, we build frequent messages, synchronous messaging, and fast failure detection. And in the device software, we build a fast local recovery based on a backup plan. The backup plan is pre-computed by the controller that is generic to different types of failures. By building Sundial, we build the first system that can provide sub 100 nanosecond time uncertainty bound. And we show improvements on many real applications. This concludes the design of Sundial, but the story of clock synchronization is just beginning. For example, now with Sundial, all the switches, all the NICs, their clocks are fully synchronized. Perfect. And how do we use them? One way to use them maybe whenever software wants to read the clock, it sends a request to NIC, and NIC read the clock, and it goes back. But this is impractical because it has to go through the PCIe every time, which can cause microseconds of delay. So one of the major use cases of NIC clock is actually the packet timestamping. So that is when a software sends a packet to the NIC, the packet will then be sent into the link, into the fabric. Just before the packet enters the fabric, before the packet exits the NIC will take a timestamp, which is the TX timestamp. And on the other side, on the receiver side, when the packet hits the NIC will immediately take a timestamp, which is the RX timestamp. And there are a lot of questions and a lot of challenges involved. For example, how can a NIC efficiently deliver per packet TX and RX timestamps? Should we store it in metadata or packet descriptor, or should we embed the timestamps in the packet itself? There are many trade-offs that involves across the cost of parsing the packet, in the API compatibility, and in the evolvability when we add new timestamps. And to get a line rate TX timestamp is really challenging. There are mainly two challenges. The first challenge is that the TX timestamp is taken at the very end of the egress pipeline of the NIC. So when the software sends a packet to the NIC, they go to stage 1, stage 2, stage 3. And until they get at the very end of the stage, the NIC gets a timestamp. So how does the NIC get a timestamp all the way back to the software? And the second challenge is that to process line rate per packet timestamp, the sender has to effectively double the processing overhead. Because the sender already sends per packet, every packet, but the timestamp comes only after the packet is sent. So it comes asynchronously, which means the sender has to have another processing thread to process per packet timestamp. And these two challenges together makes it extremely challenging to get line rate TX timestamp. And another question is, can we get more precise timestamp? For example, 1 nanosecond precision. Today's NIC can get hardware timestamp, but the precision is not 1 nanosecond. They can be 7 nanoseconds. And this is important because every nanosecond counts as the latency continues to decrease in the future. And more industry are moving into the cloud with their own precision requirements. And also, every nanosecond error, right, on every hop, they will accumulate in the synchronization. As we showed previously, sundial can achieve, in a normal time, it can achieve 43 nanoseconds. A large fraction of the 43 nanoseconds come from these timestamping errors. And another question is, can we support the timestamp in a more diverse environment? Can we get more types of timestamps? Can we get timestamps at different locations? If we think in the context of a smart NIC, the smart NIC has many different components, like packet processing, some other processing engines. Right? Some application may want to get timestamp from different applications because packet can traverse different components in the NIC. And sometimes we may want to know the delay spent in the NIC. So beyond the TX timestamp, which is taken when the packet exits the NIC, we also want a timestamp when the packet enters the NIC. And this becomes more important. And this becomes more important if we think of it in the context when the data network boundary has really expanded. This is because in the ultra-low latency environment, which is because more and more important today, the in-host delay becomes a very significant part of the delay. So there are many different components connected. For example, CPU, GPU, TPU, and NIC. They are connected by a PCIe bus. And the delay spent on them is very important for this ultra-low latency environment. But for tens of years, most software didn't pay any attention to this in-host latency. So software today are facing a lot of problems in this new environment. Lots of classic problems reappear in this new environment. For example, if there is an in-host queuing delay, right? If there is congestion that causes persistent delay, how do we deal with them? If we don't handle them properly, then some resource will be temporarily unavailable, and the whole system will be unbalanced. So we need a congestion control across different components, different devices that are also in the host. And when problem happens, we also need to diagnose. So this also means we need precise delay measurement across the devices in the host. And we may also want to achieve consistency across different devices on the host. All of these problems, they all depend on precise clock synchronization and also getting timestamp across a heterogeneous environment. So we want to get timestamp on all different devices and at both ingress and egress, etc. So there are a lot of challenges in the clock synchronization when we view the world in this new context. So with this, I'm happy to take any questions.
All right, I thank Yu Liang for the great talk. So we have time for a couple questions. You can either raise your hand and speak up or type in the chat. So yeah, before we gouge more questions, actually, I have a quick question about clock synchronization in the cloud environment in general. So from what we can see, right? So Sundial can already achieve quite impressive precision, less than 100 nanosecond in all the scenarios. Do you think that this Sundial is already approaching the best that you can do, or why or why not? Do you see any still room to further improve the clock synchronization, or already we are hitting some kind of very hard limitation at the moment?
Yeah, thank you for this question. Yeah, it's a good question. So yeah, so we build the hardware to try to achieve the best we can, but we still see some rooms for improvement. For example, as I mentioned in the end of the talk, the timestamp can have some jitter, some errors, which are several nanoseconds, and it will accumulate on every hop. So yeah, that will so if we can reduce that timestamp jitters, then the accuracy will be further improved. Also, another thing is that across the fabric, across the NIC and switches, these clocks are very well synchronized. But when we look at the software at the end host, right, we still see there are the software, the CPU are connected to NIC through a PCIe bus. And that one, we don't have a very deep understanding. So it can cause some jitters there as well. Right. This is both at the end host, right, at the receiving side of the clock, and also at the source of the clock, right, which can maybe have a GPS clock or atomic clock. Distributing from the GPS to that NIC can also introduce some error. So this is also part for improvement.
I see. I think it's a follow-up is that, do you think like under certain precision that there will be no significant effect for the real applications? Let's say, do you have any concrete number in mind? Right now, you think you're talking about 43 nanosecond. You talk about it's always less than 100 nanoseconds for your system. That do you think, like, for example, should we achieve 1 nanosecond or should we achieve 10 nanosecond? What do you think on that?
Yeah, so yeah, many applications, different applications have their own requirements. For example, congestion control, maybe microsecond level is good enough, right? If the fabric latency is maybe 10 microseconds. But there are also other applications that they really care about the nanosecond part of the precision. Right? For example, if there's if we want to order different events, and if the application really care about the order, right, it may involve some fairness. Whoever comes first, whoever comes next, then it's really important for us to get to this nanosecond precision. Yeah. Otherwise,
thank you so much. I see.
First, maybe process next, which is unfair to them.
Got it. Thanks. We have more questions from the chat from Wei Bai at Microsoft. So he's asking, do you have any comments on comparing your work with Balaji's cloud synchronization work?
Yeah, that's a great question too. So yeah, if I understand correctly, Wei Bai is referring to Huygens, right, from NSDI sometime. So yeah, Huygens is an approach where they only based on end host, right? They don't use the switches, and they send a huge number of probes across different. They send a mesh of probes. And because of this nature, right, it's basically it's a big data approach. It has to rely on the fact that the clock are stable over a period of time, which in the Huygens paper, I think is 2 seconds. So it has to base on the assumption that the clock is stable over 2 seconds. This may not be true for 2 reasons. First, there can be some failures, such as cooling failures or even fires in the center that can dramatically change the frequency. And also, we recently find that if the oscillator depends on quality, it has some short time scale, right? Sub-second scale, it can change the frequency. It doesn't depend on temperature. Even temperature is same, voltage is same, the frequency can still vary over a sub-nano time scale. So that's that means we need to do it very frequently for those oscillators.
Got it. Thank you so much. Let's see if there are further questions from the audience. The last chance. Anyone wanted to ask questions, please raise your hand or just speak up and unmute yourself. All right. So given time, so thank you so much. Let's thank Yu Liang again for the great talk, and then we can let the next speaker to get prepared. Thank you very much, Yu Liang.
Thank you.
Awesome. Okay. So our next speaker is Ying Zhang. So it's my great pleasure to introduce her. So Ying Zhang is a senior engineering manager in Meta. So she works in large-scale network management problems. Her team owns a lot of software for network modeling, design, configuration, and verification for metadata centers, backbones, and edge networks. She has more than 80 granted US international patents, and she published more than like 100 peer-reviewed publications, and also recently was named by Swedish Median as Mobile Network 10 Brightest Researcher. She also avoided as a rising star in the networking and the communication area. Let's welcome Ying.
Thank you. Can everyone hear me well? Let's see my slides. Okay.
Yes.
Great. Thanks everyone for having me here. My name's Ying. Alan, thanks for the introduction. I'm a senior engineering manager at Meta, and today I'm going to talk about scalable, flexible, and agile network planning. So large content service providers like Facebook, Google, Amazon usually operate a global network. And the backbone network serves hundreds of terabytes of traffic at any given time. In order to meet operational requirement, it is very critical to dimension the backbone network in a very accurate and cost-effective way. And this is what we know as network planning problem. So network planning is a very important step in the entire network delivery lifecycle. So it starts, the entire lifecycle starts with forecasting the demand and then building a plan for the network. So the plan is used to the network plan is used to begin the process of procuring fibers, which usually had a lead time of months to years. And then the network plan is used to design IP and optical network, which is then further deployed. And network planning problem is also hard in practice. First of all, it is cross-layer. It needs to consider both IP and optical layer for the backbone, so that we need to make decisions for both layers and consider their dependencies when we form a network plan. It is also multi-phased, and it is an iterative process. In production network, the planning process is done over a short-term and a long-term horizon, respectively, in order to generate the short-term actionable signals for operational teams while allowing for optimal long-term network evolution strategies. And also, it needs to be failure aware. we need to ensure the reliability of backbone network under different failure scenarios. And network planning is also not just about managing the current network. There is also a time dimension to it, and that is really the theme of today's talk. Network is evolving, demand, requirements, services are ever changing. So network planning should also evolve through multiple time dimensions. And across different time, there are different problems and challenges. So in the remaining of this talk, I'm going to show how network planning manifests itself across different time domain, from monitoring the risk in production network to midterm service sharing and to long-term network planning dimensioning. And across different time scale, there is a common theme, which is that finding the right model, abstraction, and developing efficient algorithm to compute the optimal plan for the network. This is very important for making network planning efficient and reliable. So in the remaining of the talk, I'm going to touch 4 aspects of network planning from both the short-term and long-term horizon. In the short term, I'll touch on the risk concept, which we use to monitor the healthiness of the current production network. In the long term, how do we use the host-based abstraction to dimension our network? I also want to talk about efficiency. How do we come up with network plan in an efficient and optimal way? And then finally, touch upon our latest work in making it more application aware and interfacing with services. So let me start with introducing the risk-driven backbone management. And I want to start with showing how it is used to reduce the network risk during COVID-19 pandemic. So COVID was really the theme of 2020. Even until now, I think people are getting out of it, but still it is one of the kind of main concern that affects our day-to-day life. And back in 2020, it was when the pandemic started, many social activities are forced to move online. And this changed the global network infrastructure, and it's really put it under a stress test. Right? From all these news reports, we can see the dramatic traffic increase after lockdown procedures were implemented. And over the years, right, there are also a lot of papers from network communities in order to understand how well the current infrastructure responded to this stress test, and how the network infrastructure should evolve in the post-pandemic era. And what our study that appeared in NSTI was really providing a different angle from a service provider backbone perspective. We focus on the backbone of global online service provider. We also focus on how do we monitor and what we have observed, and also go beyond the current traffic and security metrics. And we introduce this network risk, which is a new metric we use to indicate the healthiness and robustness of the network infrastructure under adverse conditions. And at our scale, failures happen frequently, and they have severe impact, right? Fiber cuts, power outages, misconfigurations, and there are natural events. And this severe impact could cause congestion, packet loss, extended latencies, even affect availability, application availabilities. And we use network risk to quantify the impact of potential failures on the network, so we can anticipate the consequences before even the failure happens. And let me first introduce what we mean by risk metric. First, this is a requires a huge engineering effort across multiple teams. So we defined this unified risk metric to make sure we, across different engineering teams, we are managing the network towards the same goal. And these metrics should capture different aspects of failure impact and reflect the service level objective on different QoS services. So we define a comprehensive set of risk metric. We first use demand loss to show the total traffic loss across flows in a QoS class. And the availability is the most important aspect of the SLO service level objective. We also consider latency stretch and path dilation to know if the routing is effective for each flow. So in our daily operation, we constantly ask whether the network is at risk. In order to provide this continuous signal, we developed a risk simulation system for the real-time risk analysis. So this figure shows the important system modules. For each simulation run, the backbone snapshotter pulls the network routers from the latest IP topology and traffic demand. The failure generator generates the hypothetical failure scenarios to be simulated. The risk simulator takes in this information and calls the centralized backbone controller for the global and traffic engineering decisions. And since routing simulations for different failure scenarios are independent, so that we can shard them and improve the overall efficiency for parallel execution. And then the risk metrics are computed from each of the parallel worker instances and finally displayed in a risk dashboard. If the risk values are higher than a predefined threshold, it will trigger production alarms. And there are a lot of details about how this risk simulation system is built. And we provide essentially trade-offs between simulation accuracy and then runtime. It supports fine-grained risk simulation with thousands of failure scenarios, as well as coarse-grained risk simulation with millions of failure scenarios. So the fine-grained simulation can take in customized failures, such as part of our decommission workflow. And before we remove the capacity or migrate the capacity from one fiber to another, we actually generate these failure scenarios and test it through this risk simulation so that we make sure each operation, network operation, is safe. We also use it to monitor and simulate to mitigate the risk during natural disasters. And it is used to also validate the QoS protection policies. For that, we generate the target failure scenarios for each QoS class, and such as single, dual fiber failures, and see if they are fully protected against. And coarse-grained simulation usually can consider even many more possible failures. And we can control like the amount of failures we want to consider versus the simulation speed. And the entire system is implemented in C++, and we have an engineering team that has been optimizing and operating the system. And for now, both the fine-grained can be finished less than 1 second, and the coarse-grained can also be finished fairly efficiently. And there are a few takeaways when we look at the risk results during the entire the initial COVID pandemic period. And I just want to share a few interesting ones with you here, and there will be more you can find in the paper. The first one is about failure models, right? Risk simulation requires high fidelity failure modeling, and there has been a lot of research focusing on failure models. And then we find a few kind of caveats, and one is about subsea fiber failure. So we find that the physical time constraints for repair is actually quite different for subsea cables compared to normal cables, because we all know it's challenge to repair a fiber that is under the sea. And as a result, its failure profile and its model is different from other fibers in a different geographic location. So we should really take these kind of failure model diversity into consideration. Another insight that we learned is about failure statistics on both optical and IP layer. So these figures plot the distribution of optical and fiber IP failures. And actually, we see fewer optical failures during the lockdown and more optical failures after reopening. But this is less, the IP network is less impacted. So the reason is because optical failures are actually more sensitive to on-site deployment work, versus IP failure distribution during lockdown doesn't really have a significant change. But as more network operations are conducted later, IP failures such as device misconfigurations are also becoming more likely. So the takeaway is really to automate the network operations and to reduce human activities. But also we argue for more responsive failure modeling. Today's failure prediction is usually based on long-term signal, but in our cases, if there are significant changes that happened, and that's significant enough, then we should really consider the trade-off between model stability and agility as an open research question. So the second insight is about traffic forecast. So the risk simulation system takes in traffic forecast to predict the network risk. But our traffic forecast was quite off in facing of really the unexpected occurrence of COVID. So there is a limitation that relying completely on in-network signal for time series-based traffic prediction. So we actually find negative correlation between traffic and mobility data, which we collected from a cellular platform. And the result inspired us really to bring in the offline signal, such as mobility, for traffic prediction. But how to model these things considering the complicated interplay of different factors is still challenging. So that kind of concludes the first part of the talk, which is using risk to monitor the short-term network health. Next, I'm going to go to more traditional network planning topic and see how we're doing the long-term network planning in Meta. So historically, network planning has really been based on a forecast of traffic between a pair of nodes, given the topology. It starts with a given set of fibers in the field, and IP adjacency traverses multiple fibers, and IP adjacencies are known before. And the typical planning problems, the traffic volume from a source to a destination are known, and it will output, considering different failure scenarios, and output a network plan. This includes both the capacity turn up, fiber procurement, and space and power. So in this example, it's a very simplified example. Assuming we know the traffic between A, B, and AC, that's the demand, and we plan the network. Here I'm illustrating both the layer 1 and layer 3 network. Layer 3 network is the IP adjacency link. So naturally, we will need 1G on the link A to B and 1G for the link A to C, and known from B to C. And AB and AC are IP adjacencies, and they are mapping to actually physical locations on the third level. Here, it basically shows there is a midpoint, which is an optical device that provides the interconnect between the two IP routers, AB and then AC. It can be more complicated when we consider failure. So in this example, if we want to provide protect capacity, meaning that guarantee capacity of this 1G between A and B, then we need to consider when there is a failure on the link AB, BC needs to have one additional 1G in order to provide the protected capacity of link AB from ACB. So when the failures are becoming more complicated, when the mapping between IP and optical becomes more complicated, then the computation becomes more complex. And what is the typical planning challenge? So the planning process is evolving into a direction to decouple service logic from network infrastructure. Consider an environment like Meta. We have many service groups, right? We have the Facebook main Blue app, we have Instagram, recently Reels, and different business units like ads, different ML departments. They all have their different network requirement. When planning for the network, we want to have this decoupled logic so that service and network can evolve independently. So that is really the first requirement that imposed into network planning. In practice, services can be migrated from one data center to another for many different reasons: load balancing, service scaling, latency reduction, DC maintenance, and so on. So the network and server infrastructure should really mark out the service behavior and provide flexibility for service migration. In addition, for an actively growing backbone like Meta, new DCs are also built yearly, so that it's almost impossible to estimate the traffic demand from to a new DC before it's ever built. So in order to accommodate this in our planning problem, we first introduced this model called host model. So host is a model that's compared to pipe. Pipe defines the traffic matrix from a source to a destination, versus host defines the total amount of traffic that's coming in or exit from each single data center. And one of the reasons we want to use host is that it can reduce the total demand in the host versus pipe. In this example, when we're looking at the total demand in a pipe model versus in a host model for a month, we can see that host, because of its multiplexing and aggregation, it actually provides 10 to 15% lower of the average and 20 to 25% of peak traffic for hosts compared to if we're computing the traffic demand using pipe model. So in our last year's second paper, we introduced using host model for planning. At a high level, the host traffic the host planning takes in the host traffic forecast. So as is shown here, instead of having a point-to-point traffic matrix, we have an aggregated one number per DC. And then similarly, using different failure protection policies and topologies, we apply a cost optimization model and derive the network plan. And one of the main challenge with this approach is that which traffic matrix should we design for the network and how the cost optimization engine will scale. Previous related work considers some more similar problems, but they are more focusing on VPN, which is smaller scale, and also they don't consider cross-layer and for the backbone network. So we developed a host-based planning system, and here I'm showing the system architecture. So it starts from traffic forecast. the key to host-based network planning is really to convert the host constraint into pipe traffic matrix. Because think about at the end, when you have a capacity planner, you have to basically compute the routing paths between any pair of nodes that you have to use a traffic matrix. But your input is an aggregated one number per DC. So we need to have this traffic matrix generator that derive the most useful traffic matrix out of the host input. And after the capacity optimizer fit into failure scenarios, it generates both the short-term plan and the long-term plan. The short-term plan is used for capacity engineering team for capacity turn-up, and the long-term plan is given to the fiber sourcing team for fiber procurement and to optical design and IP design team for deployment of fibers and optical systems. So it is clearly computational infeasible in order to consider the huge amount of traffic matrix samples. But the traffic matrix samples actually have different importance for network planning. So that is our key insight. Because the goal of network planning is to add capacity to the bottleneck links in the network. And traffic matrix with high traffic demand over the bottleneck links plays a more dominant role. So we call this traffic matrix a dominant traffic matrix, such that designing the network capacity for these dominant traffic matrix will give a high probability to satisfy the remaining traffic matrix. And based on this intuition, we basically develop a graph theory. Bottleneck links are captured by network cuts that partition the nodes into two disjoint subsets. The number of network cuts can be exponential to the network size, and we propose a sweeping algorithm to quickly sample the network cuts and the traffic matrix that actually cover the bottleneck links across these network cuts are the traffic matrix which should be used for network planning. So the remaining of this host-based network planning paper talks about how do we sample the traffic matrices and how do we scale using our optimization. So you can think about like having host-based provide agility to services, but on the other hand, it gives a scalability challenge to the network planning team. So we continue to look for other opportunities for us to continue make the planning software more efficient. And one idea is to apply reinforcement learning. So what I didn't show you earlier is that at the end, the network planning is still an optimization problem. It is formulated as an integer linear programming problem, right? And the objective of ILP is to minimize the total network cost, which is a sum of both the IP layer and the optical layer cost. And then there are a few constraints. For example, constraint 2 basically says that it's a flow conservation constraint. 3 says that link capacity there is a cap. And 4 is the spectrum consumption, a constraint on each fiber. And 5 finally is really the existing topology constraint. So any of such ILP problem will be fed into an ILP solver. However, ILP approach usually hits the limit of scalability in production scale without any question. So in many cases, we have to rely on heuristics in order to actually get the work done, right? Get the software finished. And there are just a few of these potential heuristics. The first one is topology decomposition. It means that the topology is too big. So we decompose a big backbone network into several subtopologies and solve the ILP independently for each subtopology. For example, it can be naturally broken down into different regions, into different continents, Europe versus US. And then at the end, solve this joint. And after we solve each subtopology separately, we use some heuristics to combine the results. Topology transformation aims to reduce the search space or the number of variables. For example, we can make the capacity unit, like how much capacity delta we're adding, a larger number. So it means that each action is kind of a more coarse-grained. Or we can collapsing multiple nodes or links together. We can also play tricks on failure selection. Instead of satisfying all failure scenarios, we may pick a subset of failures for the ILP. And these are all heuristics. Actually, it works in production when we still heavily rely on them. But then it kind of gives us a natural idea, right? Since we humans are involved, and it comes up with these heuristics, right, to reduce the time of the optimization. Naturally, can we have a more intelligent way to learn about these heuristics, right? So our approach here to revisit this problem with different take by using different reinforcement learning algorithms, right? And hopefully, people may ask why RL can help solve a network planning problem. Because the typical goal of our RL is to train the RL agent to learn to take multiple actions in an environment in order to maximize the cumulative reward it receives. And the environment provides the state as the input and the reward as the feedback. So naturally, we build our neural network-based planning system called neural plan. And the input to the neural plan consists of 5 components: traffic demand, network topology, failure scenarios, reliability policies, and cost models. The RL agent only needs to really encode the network topology, and the other 4 are handled by the plan evaluator. Basically, it can intelligently pick different inputs. The RL agent, it interacts with the plan evaluator to learn to generate the network plan that minimizes the network cost while satisfying the traffic demand under reliability policies. And it generates the rewards to the RL agent. It receives the network plan from the RL agent, checks if the traffic demand is satisfied under different failure scenarios, and then use the cost model to compute the cost for the plan. And after the learning process is completed, the RL agent outputs an initial plan for the first stage. And then at the second stage, the ILP solver can actually find the final plan in the pruned search space. So this is actually a hybrid approach we take, and we are still continuously exploring if RL can do more, right? If it can replace ILP eventually, probably for a subset of the planning problems. And finally, I want to also give a very quick overview of our most recent work on network planning, which is application aware. So I talk about short-term risk in risk monitoring and use hosts to generate long-term plan. But you may still ask, right? Network is a finite resource. What if we cannot, or it's still, we cannot afford to allocate unlimited, infinite capacity to it? Especially these days, we know there is a practical supply chain shortage, right? And we need to find other solutions for network dimensioning, which is we need to understand the services and application better. So network, this is called network entitlement. When we operate the network, we provide different classes of services. We provide failures and protections and different levels of SLOs. And all of these are part of network planning and operation. And of course, the challenges are demands are growing very fast, outpace capacity. Service needs to are growing very fast, and sometimes service has specific requirement on service specific locations, and there is a constant debate between service and network for the network accountability. And network entitlement is our most recent work in this space, and it is a bandwidth contract between network engineering and service owners. If the service sends less traffic than their entitlement allows, then the network will guarantee their performance. However, if the service exceeds their entitlement, only the portion below the entitlement will enjoy their performance guarantee, and exceeding portions performance is not guaranteed. And this is achieved using our DSCP marking, which we talk more in our most recent this year's SIGCOMM paper. And network entitlement is work conserving, which means that while the exceeding portion will be transmitted with best effort, their performance is not guaranteed, but they can still transfer if there is spare bandwidth. Network entitlement as a concept applies to many layers of network, including intra-building, intra-region, wide area network, and even in data center. And finally, we actually use some of the concepts and building blocks we talked earlier, such as host models, simulations, to actually implement this system. And the network entitlement starts also with forecast for each service. And it starts with production topology. And we run simulations to see if the demand from each service can be admitted. If the total flow cannot exist, then we have a fair-based bandwidth sharing. Consider also QoS and failure SLO requirement to go through an entitlement approval engine. The approval engine outputs the entitlement contract, which is shared between both the networking team and the services team. And finally, we using BPF to enforce the packet transfer. So due to the limited time here, I cannot talk too much about the entitlement details, but I want to stop here and do a quick summary of what we have talked about. So network planning is not just solving one optimization problem. I show you how the risk-based metric is used to monitor and find some interesting observations from our current production network. I also touch upon our latest work on using the same abstraction host and the same simulation platform to solve service sharing problem in the near term. And finally, how does host help with providing service agility in the long-term network dimensioning? So I want to stop here and take any questions. Thanks.
Thanks, Dean, for the great talk. Let's open the floor for Q&A. So for any questions, you can type on the chat or raise your hand or just speak up. So before, waiting for the stream of questions. So I actually have a quick, question.
Okay.
Kai, are you talking?
I want to ask also a quick question. So thank you, Ying, for the nice talk. So I think you're using so for your network planning life cycle, you have long-term, mid-term, and short-term tasks. Those tasks. Are you using AI and machine learning, or I saw you DIL, long-term network planning. Are you using these DIL models in short-term or mid-term? So what's the overhead? So when you use those deep reinforcement learning models in your like if in your production those network planning or management. So any insight on that? So actually, I'm curious about how the real world production network using those, especially DIL, deep reinforcement learning approaches in practice, because I know that those DIL approaches, while they can adapt to network dynamics, but they indeed introduce a non-trivial overhead, even you use them for inferencing. You know, if you do it training, for example, online learning, it may introduce a even more significant overhead. So what's your experience and insight on this aspect? Yeah, thank you.
Yeah. Thanks. That's a great question. So that's why I kind of started with talking about there is a different time scale. There is a short-term, mid-term, and long-term. And because different scale has different time requirement, and I often find kind of scalability is still overlooked piece in most of the kind of research of applying, you're right, applying ML to solve network problems, right? So to put it simple, for short term, if we are answering any production network risk, let's say you want to drain a link, right? You want to do a maintenance and you're waiting for this engine to tell you an answer. We don't use any ML because that's not going to be fast enough, right? We use customized, sometimes multi-commodity flow and highly optimized parallelized routing simulations to answer these questions. And for that, we won't simulate a full range of failure scenarios. So we only simulate a very limited set. But then there is long-term. Long-term, we can afford long computation time. And typical ILP runs weeks. And that is only if it finishes, right? And for there, I think ML does play a very important role because in some places ILP cannot finish. Some places ILP takes so long, right? In those time frame or those type of problems, ML is actually very useful. Even if it can, like in this paper, Neural Plan, we talk about only a hybrid approach, using ML to create basically a cap or a reduced search space for ILP. That already helps a lot with reducing the search space and improve the speed. But there is also another caveat. It doesn't apply to all the problems. So planning has actually not just like one problem formulation. It has multiple problem formulation, depends on what you want to plan. I may want to plan IP adjacency, meaning that for this IP link, point-to-point link, how do I build my layer 1 link, optical link, in order to satisfy this, right? That is a slightly more constrained, easier problem. And sometimes we find these kind of problems are easier or more feasible to solve using ML problem. Yeah, so it's not, I think there is in production, it's still a trial and error. And it is still a hybrid approach with ILP. We're also working with our AI research to continue push the limit. And even in the kind of the FAIR team AI research, using reinforcement learning to solve optimization is one of, I think, their hot research topic. Yeah, I hope I answered your question.
Thank you, Ying. So one quick question, yes or no? So DL has been used in Meta's infrastructure or not?
Yes. It is used in production. It is used, but not for all the planning problems. So that's why I mentioned there are some problems that are easier, and we're tackling those first. Yeah.
Okay. Thank you.
Thank you, Ying. It's also answered part of my questions as well. So we have one more question from Wei Bai. So I think it's about the third topic you mentioned. So for example, some applications do not need much bandwidth, but they are kind of sensitive to the queuing delay. So do you still need to configure these large weights for these applications?
Yeah, there are two two primitives we have. First is QoS, right? So that is very standard, old school primitives that most network use, and those means that the traffic will be put into different queue. And hopefully that can address the high sensitive latency, but less traffic, not too much traffic volume type of application. But this entitlement is more for, but QoS, we cannot have too many fine-grained classifications. That kind of brings into, it's not enough, right? Within one QoS class, there could be many still traffic. Let's say storage, they are all pretty much similar, but there are still different service. There are storage for different services, and we want to provide a further classification or sharing across them. That's where we use this entitlement. Yeah.
I see. Thank you so much. Hopefully this answer Wei. So I think given time, I think it's an excellent Q&A, and let's thank you again for the talk. And I think our next agenda should be in a lunch break, and then we'll come back in about 20 minutes. Thank you very much.
搞什么啊？
啊，太抽象了啊！有意思。
All right, I think we can get started. All right, hi everyone. So hope everybody has already had a good lunch break. Okay, let me check if the authors for this session are already here. Is Zhiwen here? Kai Hui and Ziyuan?
Okay, Zhiwen is here.
Oh, hello. Okay, I can't tell who is speaking.
Yeah, Zhiwen.
Okay, Ziyuan is here. So it's Zhiwen and Kai Hui. Are you here?
Yeah, Zhiwen is here.
Okay, Zhiwen is here. Kai Hui, are you here? All right, so it looks like Kai Hui is not here, but that's okay. Kai Hui's talk is the second talk, so hopefully he will join us in the meantime. All right, so I think we are ready. So yeah, welcome back, everybody. So now let's start the afternoon session. So in the first session in the afternoon, so we are going to have 3 very interesting papers on network measurements. So the topic ranges from traffic modeling in data centers to microburst detection and to operation data aggregation in the network. All right, so first up, we have Zhiwen Liu to present their work on data modeling in data centers. Traffic modeling in data centers. So the speaker will be Zhiwen. Zhiwen Liu is a second-year master's student from Tsinghua University at the Institute for Network Sciences and Cyberspace. Zhiwen's research interests are in digital tree networks and data center network modeling. All right, so with that, okay, I think, oh yeah, Zhiwen has already shared his screen. So Zhiwen, you can start.
Okay, thanks for Jialin's introduction and good afternoon, everyone. My name is Zhiwen Liu, and this is Locality Matters. Traffic demand modeling in data center network. This is joint work with Wang Mowei and Professor Cui Yong. We all come from Beijing, Tsinghua University. Oh, oops, I think I can't open this video. So in this work, we want to build a generative model of the traffic demand in data center networks. As we know, there have been many interesting works on traffic measurement and analysis, and these prior works revealed complex traffic patterns, such as burstiness and the self-similar nature of traffic on different time scales, and the scaled traffic metrics, and the heterogeneous traffic patterns across clusters with different service placement. And some recent works also discovered the temporal and the non-temporal traffic structures. In our work, we focused on the flow-level traffic demand modeling in data center networks. By saying traffic demand, we mean the end-to-end data transmission intention to fulfill application-level service, and routing issues are out of scope for our modeling work. And the motivation of our work is to promote better designing of data center networks and to promote better evaluation of these proposed designs. For the designing, better traffic demand model means better understanding of the traffic patterns, so it can help build demand-aware topology. For example, the optical wireless data center networks, and demand-aware scheduling, demand-aware congestion control are also feasible given strong enough traffic models. And for evaluation, a generative model can create realistic traces. Then by having better traces, we can have a better evaluation for these proposed novel designs. These potential use cases are very helpful to build low latency, high bandwidth, and high utilization data center networks. Before we move on to the details of our model design, let's look at the locality properties of traffic demand in data center networks. As shown in this figure, we visualize part of the traffic data within 16 source and destination pairs. In subfigure A, each row represents one source and destination pair using a distinct color, and each rectangle represents a flow within this source and destination. The width of the rectangle represents the flow size, and the blank between two rectangles represents the interval time. Subfigure B and subfigure C plot the probabilistic distribution of interval time and the flow size within each source and the destination pairs. And we can see significant difference in interval time and the flow size distribution across these source destination pairs. Besides, we sum up all flows within these 16 source destination pairs and get the total demand distribution as shown in figure D. And we can see the skewness of total demand. And finally, subfigure E plots the degree of each node in this data center. And the result shows that the degree distribution is also highly skewed. And one thing to be clear is that the degree measured here is not the physical connection, but the number of peers each server talks to. So conventional models are insufficient to capture and recreate the complex locality properties. Many prior works focused on the statistical characteristics, but they didn't consider the fine-grained flow level patterns. And some recently proposed works considered the temporal and non-temporal traffic characteristics at the same time, but it excludes the well-concerned information like flow size and packet size. So as a result, these prior works cannot be used to generate realistic traces. And researchers have to concede to the outward communication pattern with equal interval time and flow size distribution as a common practice. When using common practice, flows are generated assuming the source and the destination are randomly chosen, and the interval time is independently sampled from a Poisson process with parameter lambda, and the flow size is independently sampled from the empirical cumulative distribution function. Even though the common practice is easy to reason about and can be the stress test cases for certain network design, but is still oversimplified. So our design goals are to build a traffic demand modeling framework. It should be accurate, can capture the complex locality properties, and recreate the joint distribution of multi-dimensional traffic demand attributes. And it should be fine-grained, can model the well-concerned flow level attributes like interval time, flow size. And it should be transferable, can adapt to different data centers with heterogeneous traffic demand patterns, and also can allow researchers to synthesize traces in different settings, like to adjust the time windows or average load. And we also hope to make this work become the benchmark models for generating synthetic traces, a handy tool to the research community for better design and evaluation before deployment. In this paper, we propose a hierarchical Bayes model of traffic demand. We choose to divide and conquer the multi-dimensional traffic demand attributes. As we can see in the function 1, this is the joint distribution function of these variables we are interested. And the character n means the number of nodes, v means the flow level samples. The first two variables, source and destination, they are discrete variables representing the spatial pattern. While the last two variables, interval time and size, are continuous variables representing the flow type distribution. And in this work, we take the interval time and the flow size, these two tuples, as the metric for flow type. We then use the Bayes approach to build our model, which is 2 stages. First, we consider the spatial pattern, aka the source destination distribution. And then we model the flow type distribution conditioned on the spatial pattern. And the final version of our model currently is a hierarchical Bayes model by using a latent functionality layer. And introducing the latent space brings in 2 advantages. First is to reduce dimensionality. We can use latent layers as low dimensional representations of a huge number of source destination pairs. And this is particularly useful when modeling a large scale data center. And second is to enhance transferability. The latent functionality distribution in data centers are related to the high levels data center service. Therefore, the traffic demand model with latent layer can be transferable to other data centers as long as they have the same service type. Then I will give an intuitive explanation about how to generate the traces using our model. And there are 2 parameter metrics in our model. The first parameter matrix represents the mapping relationship from latent functionalities to physical nodes. And the second parameter matrix represents the mapping relationship from physical nodes to flow types. So by iteratively sampling from these 2 parameter metrics, we can get synthetic traces. Okay, so qualitatively, if you visualize the real world trace with this colored rectangle representing flow, you can see a lot of locality and correlation of flows within the same source and destination, which is in one row, and the huge difference across source and destination. But in traffic trace generated by common practice, you don't see this locality. Neither the cross-sectional differences. It's sort of just a random mix of different flow types. The traffic traces generated by our model named LOMAS, it does has this locality and important properties. It looks like the realistic real traffic data. And we also use a preliminary metric named KS distance to quantitatively evaluate our model's performance. The minimum value of KS distance is 0, and meaning 2 identical distribution, and its maximum value is 1. So the lower value is better. And you can see in this figure, for interval time and flow size attributes, we calculate their average KS distance, and the x-axis k in these figures is the hyperparameter of our model, meaning the dimensionality of latent layer we chose. And the y-axis is the KS distance value. And the preliminary evaluation results show that the generated traces by our model performs better than the common practice with lower KS distance. And I would briefly describe our potential future works. We want to make this work an easy-to-use platform about traffic modeling, generating, and even simulating to research communities. And the researchers can use it to model their own data sets or directly use our trained model to generate traces. And we also want to combine common simulation environments with our traffic modeling framework so that researchers can evaluate their novel designs using realistic traffic traces as the simulation input. Okay, so finally, I want to briefly talk about the advantages of a traffic model over the historical data. And similar discussion has been given in other papers. So I do it again quickly. The first thing is that publicly available data sets are very limited, and collecting real-world traffic data is very time-consuming and expensive. And the second thing is that historical data is not flexible and will quickly become obsolete. But models let us adjust the parameter for what-if scenarios. And the last thing is that model can be used for short-term flow prediction and help fine-grained traffic engineering. Okay, there are a lot of more details in the paper, but I will stop here. To conclude, we build a novel framework to model real-world traffic demand in data center networks, and we can use it to generate realistic traffic traces and recreate complex locality properties. And the preliminary evaluation results show promise to adapt our model to many data centers. And the code and the models are available online. Okay, thank you.
All right, thanks, Zhiwen. All right, so now we have about 3 minutes for Q&A. So anyone in the audience have questions for Zhiwen? Feel free to speak up or type it in the chat. Well, I don't see anyone asking any questions, so maybe I'll ask one question. So Zhiwen,
sure.
So is there any rationale behind the model you use for your for training? So you say here, so you use Bayes model with hierarchical Bayes model. So is there a rationale behind using that? And have you tried any other kind of machine learning models? And what's the reasons they would pick this one over the other machine learning models?
Yeah. Okay. So first thing is that we think because we focus on the 4 variables here to describe the traffic demand distribution, and by data analysis, and we found that the traffic distribution, we mean the interval time or flow size, is highly correlated to its source and the destination distribution. So we think given this correlation, so we think about a multi-stage modeling framework. So we think the Bayes model first, and so we try it, and we found this model is simple but very useful by our preliminary evaluation results. So and there are many other more powerful machine learning, even deep learning models can be used to model this traffic demand. And I think we can put this in the future work to try other more powerful models and compare their complexity and their performance.
All right, thanks. Thank you. Any other questions? All right, okay, so maybe I can ask one more question before we end. So I think you mentioned that this the model you generated is for a particular type of service. So what are kind of these services you're referring to?
Pardon? You mean data center service type?
Yes, yes.
Okay, so because the flow let me use this week. The flow the traffic flow distribution why we say that this distribution is correlated with services that there are many prior works they mentioned that for MapReduce service, the traffic distribution is have a strong out-12 pattern, but for the work mentioned in Meta's paper, they found that in their social network data centers, for different clusters with different service, like some web search or database, there have other traffic patterns, not out-12. So we and for a large data center with thousands of servers, actually there are only very limited service types. So it's the number of service types is very smaller than compared with the number of server. So we think about to choose a latent layer with very low dimensionality to represent a huge number of servers.
All right, very cool. All right, thank you. This is very cool work, and yeah, I think that your future work slide looks very promising. So yeah, please keep working on this. I think it will be very useful for the research community. All right, so let's all thank Zhiwen for his excellent talk. Okay. So next up, we will have Kai-Hui. Kai-Hui, are you here?
Yeah, I'm here.
Okay, hi Kai-Hui. Yeah, feel free to turn on your camera. Oh yeah, you already turned on your camera. Okay, hi. All right, so Kai-Hui will talk about will present their work on bandwidth efficient microburst measurement. So Kai-Hui is a fourth-year PhD student in the Department of Computer Science and Technology, Tsinghua University. He is supervised by Prof. Dan Li. So Kai-Hui had broad interest in networking and systems, including programmable networks, intelligent networks, and currently he is focusing on using programmable data plane to diagnose and improve the performance of data center networking. All right, with that, so Kai-Hui, you can start your presentation.
Yeah, thank you, Jialin. Hello, everyone. I'm Kai-Hui Gao from Tsinghua University. I'm proud to have the opportunity to present our paper, Bandwidth Efficient Microburst Measurement in Large-Scale Data Center Networks. Due to the quick reason of network scale and bandwidth, the applications are increasingly rigorous to network latency. Consider an application with 5 sequential remote requests. If network latency is 30 milliseconds, the job complete time is 150 milliseconds, which can deliver a satisfactory user experience However, if network latency is 200 milliseconds, the total latency reaches 1 second, which brings poor user experience. Unfortunately, latency anomalies, for example, microbursts, are widespread in large-scale DCN. Data showed that the latency of 44,000 requests exceeded 100 milliseconds per hour per cluster. Then, what is microburst? Firstly, we need the operators to specify a threshold of queuing delay. When the queuing delay of a packet exceeds the threshold, it indicates that the packet experiences a microburst, and the application will be affected. For example, if the network's base RDT is 24 microseconds, the threshold can be 50% of the RDT, so that is 12 microseconds. So we have the formal definition of microburst, which defines the beginning and end of one microburst. Firstly, we get the queuing length when packet dequeuing at DQLAN, and assume that a snapshot of the queues when packet dequeuing can be obtained. When a packet with DQLAN and snapshot dequeuing, if the dequeuing exceeds the threshold, the pod enters the microburst state, and the status ends when all the packets in the snapshot are dequeued. For example, at the beginning, there were 6 packets in the queue. Then packet 1 is out of the queue. Its dequeuing exceeds the threshold, so the microburst started, and the snapshot of the queue contains packet 2 to 6. Then packet 2 is out of the queue. Its dequeuing is less than the threshold, but it belongs to the snapshot, so it is involved in this microburst. The same applies to packet 3 to 6. So they all belong to the snapshot, and they are microburst involved packets. However, when the packet 7 dequeuing, its dequeuing is less than the threshold, and it doesn't belong to the snapshot. So it is not microburst involved packet. In general, the purpose of using snapshot in the definition is to identify microburst involved packets and help measure contributing flows. The contributing flows have the most contribution to a microburst. Here is the formal definition of contributing flow. In brief, in all the microburst involved packets, the flow that accounts for the largest proportion is the contributing flow. Microburst and congestion can cause network jitter and performance degradation of application. The detecting, profiling, and understanding of microbursts and contributing flows are critical for a wide range of goals. Firstly, congestion can be caused by various reasons, such as priority contention, TCP incast, and burst UDP. Profiling the detailed flow level information in microbursts can help diagnose the actual root cause. Secondly, public cloud showed by mutually on-call operative tenants and applications. Identifying the responsible applications can help better load balancing and VM placement in data centers. Thirdly, quickly identifying the microburst and the contributing flows enables rapid mitigation of congestion-related attacks. Recently, researchers propose utilizing the programmable data planes to identify the contributing flows, which can be divided into 2 categories: microburst agnostic or microburst aware. However, they all require a lot of bandwidth to collect the information. Specifically, for microburst agnostic solutions like in-band network telemetry-based systems, they add telemetry metadata about switch port and queue into the packets or the mirrored packets, then analyze the microburst and the contributing flows of line. Due to the randomness of microbursts, they need to measure all packets to detect microbursts. So they consume bigger than 10% network bandwidth. Furthermore, the massive telemetry information requires expensive processing resources. For microburst-aware solutions, like burst radar, the state-of-the-art system in microburst measurement, it generates one courier packet to carry telemetry data for each microburst involved packet. This optimization can reduce bandwidth overhead, but it captures packet-level information. And our experiments show that it still suffers sizable overhead of network bandwidth. We can theoretically analyze its overhead based on the distributions of microburst frequency measured by Facebook networks. The median of the overhead is bigger than 1%, which means that the measurement requires 25 terabits per second for a network with 400 switches. So how to measure microburst with low overhead is an important problem. We consider that only flow level results are required in microburst measurement. So we have the basic idea. Firstly, we detect packets which involved in a microburst. Then we measure flow level information in these packets using a sketch. Finally, we calculate and report the flow level information about contributing flows by only one telemetry packet. However, there were two challenges to realize our basic idea. Firstly, identifying the microburst involved packets in switch queues, including multi-queues, is non-trivial, because egress queues cannot pick and mark the packets in any queue. And so the involved packets need to be detected in the egress pipelines. Secondly, after the packets have been marked and counted, how to derive the flow IDs and the statistical information from the sketch? Performing these operations is not yet supported or would hurt the performance of high-speed switch ASIC. So in this work, we propose burst scope to address these challenges. First of all, in order to detect the microburst involved packets in egress pipeline, we add a variable in egress pipeline called packets remaining to track the remaining packets in the snapshot, although we don't have snapshot anymore. Let's continue with that example. When the packet 1 dequeuing, it enters the egress pipeline. Its dequeue length exceeds the threshold. This packet is marked. At the same time, packet remaining records the dequeue length. That is 5 packets. Then, when packet 2 enters the egress pipeline, the packet remaining is bigger than 0, which indicates that the packet belongs to the snapshot. It is a microburst involved packet, so it is marked. Finally, packets remaining has to be subtracted by 1, or the packet length. The same applies to packets 3 to 6. They are marked as microburst involved packets until packets remaining equals to 0. So then, after microburst packets are detected, we deploy an invertible sketch, like MV sketch, in egress pipelines to count these packets. This sketch records the flow IDs and counters. By applying the majority vote algorithm, MV sketch could check the heavy flow in an online streaming fashion. The vote algorithm ensures that the actual heavy flow must be the candidate heavy flow stored by the sketch at the end of the streaming. Then, analyzing the contributing flows and other useful information need complex computations, which are not supported in high-speed switch ASIC. So we install the computation into the control plane of the local switch. When specifically, when the microburst status ends, burst scope reports the sketch to the control plane via PCIe. When the control plane reserves a new sketch, the CPU calculates the flow level statistical information, including the contributing flows, duration, microburst length, traffic proportion. Finally, the control plane generates only one telemetry packet to carry this information to a remote server. Here is the format of the telemetry packet in burst scope. We need 4 bytes to represent the location where the microburst happens. Then, burst scope reports top 5 contributing flows, which requires 65 bytes. Besides, other statistics like queuing length need 4 bytes. Finally, we evaluate the overhead, accuracy, and the resource utilization of burst scope on a testbed, presented in this figure. We compare burst scope with 2 network monitoring tools. One is microburst agnostic tool called NetSight. Another is microburst aware tool, that is burst radar. Then we use trees from literature for evaluation. Firstly, since the frequency of microburst is related to the threshold, we show the bandwidth overhead on the different threshold in the figure. Evaluation results show that for a threshold of 5% of RDT, NetSight consumes network bandwidth up to 15%, and burst radar consumes network bandwidth up to 1.2%. Conversely, burst scope incurs only 0.02% bandwidth overhead, which is 60 times less than burst radar. The second evaluation is the accuracy. Due to Hashi collision, the contributing flows identified by burst scope may be wrong. So we evaluate the identification accuracy of burst scope and the baselines in this experiment. The accuracy of burst scope is up to 97%, while the accuracy of burst radar is 94%. In the table, we compare the hardware resources required by burst scope, burst radar, and the production version of switchdoor P4. In conclusion, the usage of all resources by burst scope is well below 100%, which means that it can easily fit on top of switchdoor P4. Okay, in conclusion, we have proposed burst scope to measure microburst at flow level with low overhead. Firstly, it detects the microburst involved packets and counts them in an evaluable sketch. Then the control plane computes and reports the flow level microburst information. Finally, burst scope generates only one telemetry packet for each microburst. Thank you for your listening, and I'm happy to take questions.
All right, thank you, Kahui.
Hey, hi.
We have about 2 minutes for Q&A.
Yeah.
Any questions from the
Sure.
audience?
Yeah.
I think there's someone. Okay, go ahead.
Raj here. So I have a question
Hey,
here.
Raj.
Yeah, so Kai Hui, first of all, cool work. I'm the original author of Burst Radar, so I am happy to see people making more improvements on top of that. So my main question is regarding the accuracy. So I also read your paper. So basically, the issue with Burst Radar is that it has the bytes and the segments, and so it marks more packets and it is exporting
Yeah.
that. So I did not fully understand how net bus scope will avoid that extra packets addition into the packets part of snapshot, because your snapshot algorithm is almost the same as burst radar. There is not much of a difference I could see. So how do you figure out that those packets don't belong to the microburst, the extra packets?
Yeah, that's a great question. When I see the paper of burst radar, I find the error or the accuracy from the segments and the packet size measured in data plane. So in our design, we transform the packet length to the segments easily obtained in data plane. So we minimize the error from this part. So if the packet size is below the segments, we can convert the accurate the number of segments it contained. So
All right. Yeah. So basically, the last line in this code is where you're making the improvement, the segments and size function. Yeah.
yeah.
All right.
Thank you.
Thank you. But good work.
Thank you very much.
All right. Thanks, Raj. So any other questions from the audience? So Kai-Hui, so what's your plan moving forward with this work? Is there any further improvement you plan to implement?
Yeah, thank you for your question. So far, this work have solved the microburst measurement problem. So in the future work, we will focus on the measurement overhead. So as you know, the bandwidth overhead and computing overhead is also sizable in large-scale data center. So in our future work, we will want to reduce the overhead and reduce more overhead. Thank you.
All right, thank you. All right, so yeah, let's all thank Kai-Hui for his excellent talk. Great work. All right, thanks, Kai-Hui.
Yeah, thank you, Jialin.
And now we can move on to the last talk of the session. So last talk will be delivered by Ziyuan. Ziyuan, are you here? Okay, I can see your screen, Ziyuan.
Yeah, can you hear me?
Oh, yes, we can hear you. Have you turned on your camera yet?
Yeah, let me. Wait for a while.
Yeah, no rush.
Okay.
All right, now we can see you. Okay, so last talk of the session, we have Ziyuan Liu to present their work on data collection in data centers and doing aggregation in the network itself. Right, so Ziyuan Liu is a third-year joint PhD student from Beihang University and Microsoft Research Asia. His research focuses on data center networks, and especially on programmable network devices. So with that, Ziyuan, you can start your talk.
Okay, thanks for Jialin's introduction. Yeah. Hello, everyone. I'm Zuan Liu. In this presentation, I will present our work, LT. This is a joint work with my colleagues in Microsoft. Because of the evolution of data centers, current data centers generate operation data at high speeds, such as packet traces and device logs. Data center operators collect and analyze this operation data for various purposes, such as problem diagnosis, resource utilization improvement, and performance optimization. Airflow, a passive networking monitoring system in Microsoft, is a typical example. It helps data center operators to diagnose network issues and can operate at 380 gigabps in one data center. Another typical example is Facebook's log service, Scribe. It can operate at 20 terabps for Facebook's all data centers. Here, we focus on the applications which collect data and store them in persistent storage. It is a common requirement for applications that want to perform offline analysis, aggregate data from multiple sources for a complete view, or feed data into the following analysis pipeline in bulk. The first step for these analysis applications is collecting data from multiple data sources. However, current data collection methods adopted by these applications more or less have problems. Server-based data collection methods usually have considerable CPU loss, which is undesirable because collecting data does not add any value. It just collects data together. Therefore, data center operators tend to minimize the operation expense of collecting data. Some technologies, such as kernel bypass or user space implementation, are proposed to improve the performance. However, it is not free. They usually treat transparency. When one wants to deploy these technologies, existing applications which are not tailored for such technologies cannot work anymore, as these technologies require some special controls of hardware. Another option for collecting data is to use hardware solutions, such as FPGA-based appliances. Though these kind of solutions do not consume server CPUs, they usually have special designs and are more expensive compared to the commodity one. Nevertheless, it can only serve some specific tasks, which leads to low resource utilization. The question we want to answer is whether we can have an analysis-friendly data collection method with low CPU load, transparency to other applications, and cost efficiency simultaneously. The answer is our work, LT, a data collecting system that can achieve the previous mentioned three properties simultaneously. First, it can achieve completely zero-host CPU involvement during data transmission, and only requires host CPU for setup and teardown. Second, it is transparent to other applications. LT only requires NVMe driver to add an interface which can expose the NVMe queue memory to application, and during data transmission, LT acts as a normal RDMA application. Therefore, other applications can coexist with LT without any code modification. Third, it is cost efficient as it uses commodity NICs and programmable switches. It should be noted that programmable switches have demonstrated their usage in large cloud vendors' data centers, which we believe will become a basic infrastructure in the near future. So, how do we achieve that? The key idea is straightforward. Use programmable switch to write data to host NVMe storage directly via RDMA. However, it is not easy and we must tackle several challenges. The first challenge is how to use switches to write data to NVMe storage directly and performantly. There are no existing solutions that allow switches to do such things. NVMe over fabrics with RDMA seems a promising option at the first glance. However, the Strawman implementation has performance issues. Because programmable switches lack the ability to control packet buffer, it is difficult for them to combine multiple large packets into one. According to NVMe OF specification, it forces us to transmit NVMe command and data into one Ethernet packet. Unfortunately, NVMe storage can only achieve its peak performance when the data size is a multiple of 4 kilobytes, which mismatch Ethernet's MTU size, often 1,500 bytes. This gap leads to 4 to 8 times performance degradation in our testbed. So how should we use switches to manipulate NVMe storage efficiently without the host CPU? It is not easy. The second challenge is how to use switches to store data in an analysis-friendly way. A strawman solution to organize data on the storage is to append database on the receiving order. The solution is easy to realize, but not friendly to post-processing. It requires computation power later to classify data if there are multiple logical streams. To accomplish that, another strawman solution is also straightforward. For each logical stream, just allocate a contiguous space and we can leverage strawman solution 1. This solution is also easy to realize, but because pre-estimate the space requirements accurately for each logical stream is very hard. This static allocation scheme will cause low space efficiency. Therefore, we want to realize dynamic space allocation under programmable switches constraint. But how? The third challenge is how to achieve high space efficiency while tolerating loss. Because data size can vary, we prefer to use linked list rather than fixed size formats to store one data record, as the former improves the space efficiency. However, the linked list is sensitive to loss. A loss will break its structure and cause the all following data loss too, though they have been collected and stored successfully. Usually, it is not a problem as we can use retransmission to ensure reliability, but programmable switches are not the case. The root cause is that programmable switches lack the control of packet buffer, which makes it hard to buffer already sent but yet acknowledged data. Fortunately, most of our target applications do not need reliability. They can tolerate some losses because losses already exist in their original schemes, or they try to mine insights from amounts of data, which doesn't care about the few data losses by nature. Thus, the key question here becomes how to use linked list to organize data while make it tolerate losses. Next, we will present our solutions to these challenges in detail. To empower a switch, the ability to write data to NVMe storage without host CPU involvement, our first key idea is to use the switch to encapsulate data into RDMA packets, and thus we can control storage with zero CPU consumption. To reach NVMe storage's peak performance, we must batch small packets into a multiple of 4 kilobytes. Our key idea for this issue is to leverage host memory as a pipeline buffer. I will give a brief description of the workflow. In the original NVMe workflow, as shown in the left figure, there are 3 parts: the CPU, data and data structures in the memory, and NVMe device controller. To interact with NVMe device, CPU will first prepare data and manipulate in-memory data structures. Then it will write doorbells in NVMe device controller to trigger the interactions. In IoT, we replace the CPU with programmable switch and use RDMA to manipulate in-memory data structure and doorbells in SSDs. Because the interactions between the switch and host are done through RDMA, there is no CPU consumption in hosts. To ensure the integrity of data, a buffer should keep the same when it is dumped into SSD. To avoid blocking the data collection of one logical stream, we organize the in-memory buffers in a pipeline way. The switch can continue transmitting data into another in-memory buffer when one buffer is locked by the dumping process. Combining these two ideas, we can write data to NVMe storage directly and performantly. For the second challenge, store data in an analysis-friendly way, the key is that we need a metadata structure that describes the mapping between a logical stream's address space to an SSD's one. Key value store scheme proposed in other programmable switch researches is not suited for data collection, as it cannot handle varied size data. Our proposal is to repurpose the multi-level page table data structure from operating system as metadata structure. Specifically, we use two-level page table that consists of a page directory, page table, and data page. This data structure allows the switch to dynamically allocate SSD space to a logical stream in the data page granularity. A procedure similar to storing data in SSDs is applied to synchronize metadata with the host. Due to metadata's importance and much less traffic volume compared with data, we decide to use switches control plane for reliability. However, simply storing the whole page table in control plane will cost too much memory and thus influence the max number of concurrent streams a switch can support. Our key idea for this issue is to only keep the required states on the switch, one entry and its offsite in each level of the page table. To mitigate cascade loss impacts, our first key observation is that most loss caused by packet corruption is randomly distributed, and thus is sparse. To tackle this kind of loss, our solution is to leverage redundancy. We encode previous R entries locations into the data entry header, as shown in the illustration. For loss recovery, the header also has a field called magic number. When a loss is detected, the loss recovery process will first search the magic number to find a potential address of the next data entry. After the magic number is found, we will parse the following data according to the data entry format and check whether at least one of the R entries locations matches the known ones. If that's the case, we accept the position as a valid beginning of the next data entry and recover from the loss. Otherwise, the loss recovery process rejects the location and continues to find the next potential location. This scheme can reduce the loss ratio exponentially when R increases. However, if more than R successive loss occurs, the redundancy cannot recover. To solve this issue, our second key idea is to divide a data page into several blocks and ensure there will always be a data entry placed at the beginning of each block, as shown in the illustration. It should be noted that even if the aligned data entry itself can be lost during transmission, its address information is treated as known and can be used in the redundancy recovery process. This technology helps because it can stop the cascade loss impact. We have implemented an LT prototype on a Tofino-based P4 switch. For faster prototyping, we implement the NVMe interaction in the control plane rather than the data plane as in the design. If not mentioned explicitly, we use the following settings in experiments. For the two-level page table, the size of page directory, page table, and data page are 4 kilobytes, 4 kilobytes, and 4 megabytes, respectively. For parameters of the loss impact mitigation, we use redundancy factor R equals 3 and the alignment block size B equals to 256 kilobytes. To evaluate the single SSD performance, we use 3 baselines: TCP dump, DVDK test PMD plus pdump, and NVMe OF target offload. We generate fixed size data packets in this experiment and use the CPU usage and the achieved goodput as metrics. For data packet size, we choose 2 typical sizes in data center networks, 64 bytes and 1024 bytes. Additionally, because almost all commodity SSDs require 512 bytes as the minimum block size, it is impossible to test the performance of NVMe or target offload under 64 packet size. Thus, we add 512 bytes to meet SSD's minimum requirement. The main takeaway is that LT reaches our design goal that storing data into SSD in its peak bandwidth without any CPU involvement and outperform the other baselines. The other thing to be noted is that small block size is not suited for SSD, as its performance would degrade about 4 to 8 times. To demonstrate the impact of loss and the effectiveness of our approaches, we measure the record ratio of data under different network loss ratios. The record ratio is defined as the number of retrieved data records divided by the number of received data records. We evaluate the record ratio of the baseline algorithm, which doesn't have any mitigation, and the LT's algorithm under various network loss ratio. We also compare redundancy-only and alignment-only algorithms for the breakdown analysis. The result shows that even when the network loss ratio is only 0.1%, more than 60% cannot be retrieved back if no mitigation is applied. And LT outperforms all other schemes and can retrieve almost all data when the loss ratio is small. Furthermore, LTE can achieve more than 0.9 recall ratio even when the network loss ratio is 10%. In conclusion, we propose a data collection method for loss-tolerant applications, LT, and achieve zero CPU usage, transparency to other applications on the host, and cost efficiency simultaneously. During tackling the challenges in realizing LT, we leverage RDMA plus pipeline hosted in-memory buffer to write data into NVMe storage directly and performantly. Besides, we repurpose page table from operating system as a metadata structure to store data in an analysis-friendly way. Nevertheless, we combine redundancy and checkpoint to enable high space utilization while being insensitive to loss. Our evaluation shows that LT can collect data without host CPU involvement and mitigate cascade loss impact effectively. LT adds a new feature to existing programmable switches functionalities, manipulating NVMe storage directly and performantly. We expect more applications can benefit from our scheme. And yeah, thanks for your listening.
Okay, thank you, Ziyuan. So we probably have time for just one question. So I see Raj already raised his hand. Raj, go for it.
So quick question of where in the system are the packet losses happening? Are they happening when the data comes to the switch somewhere on the switch, or is it between the switch and the RDMA NIC? Where in the pipeline are the losses that are happening?
Both of them can happen losses. For example, if you want to do some packet capturing like airflow, the switch will first mirror the packets to collect server, and our system resides between the collect server and the mirror switch.
Right.
And originally, the mirror packets will be dropped due to packet corruption or the traffic loss, and and also the loss will also happen between the path between on the path between our system and the collect server, because the switch cannot perform retransmission, so we cannot ensure that the packet be delivered to the collect server from our LT switch reliably. So for your question,
is it a good idea to use a lossless fabric between your ALT switch and the collecting server? Because you're anyway using RDMA NIC, right?
Yeah, for the lossless fabric is a good idea, but in current data center, they have already enabled lossless fabric, but because it relies on some parameter setting and it cannot prevent loss completely. So yeah, we must have to use some technology to decrease the impact of the one packet loss. Yeah.
All right. Yeah. Thanks.
All right. Okay. Thanks, Raj. All right. So due to time, so we can't take more questions, but feel free to ask questions offline. And with that, let's all thank Ziyuan for his excellent talk. So that concludes the network measurement session. So we'll have a short, 2-minute break before we start the next session. So the session on SICOM talks. All right. So thank you, everyone.
Hello, can everyone hear me?
Yeah, you're audible.
Yeah, this is Wei from the Microsoft Research Redmond, and today I'm very happy to be here to host this SICOM talk session. So I remember when I was a PhD student, there were very few papers in SIGCOMM or NSDF from Asia. So it was impossible to organize, a SIGCOMM session in such kind of a workshop. But now I'm happy to see that, there are more and more papers from the Asia in the, top networking conference that is SIGCOMM and NSDF. So, in this year we can have multiple SIGCOMM talk session. So our first speaker is Junxue Zhang from the Hong Kong University of Science and Technology. So he's the PhD candidate from the ISIN lab, and he's under the supervision of Professor Kai Chen. His research interests are data center networking, AI system, and the privacy preserving computation. Before joining HKUST, he received his bachelor and master degree from the Southeast University. So he has published paper at major networking conferences such as SIGCOMM and CONEST. So, Junxue, can you share your screen?
Yeah, could you see my screen? Wait.
Yeah, I can see your screen. Yeah.
Okay. So thank you for this introduction, and hello everyone. I'm really happy to attend the APNet SIGCOMM talk and share our recent work. The title is Light Flow Towards High Performance Adaptive Neural Networks for Kernel Data Paths. And it's a joint work with Chao Liang, Hong, Shui Hai, and Professor Kai Chen. We all know currently in the networking community, more and more adaptive neural networks, they are actually proposed to optimize data path functions, right? Such as congestion control, load balance, routing, scheduling, and so on. For example, Arula is proposed in ICML and MOCC is proposed in Eurosys. And they are all new congestion control algorithms. And then also various other neural networks, they are also proposed to enable new flow scheduling, packet routing, load balancing schemas, right? So here, the adaptive neural network means while it performs model inference, it can also fine-tune itself based on the coming data. So these adaptive neural networks have achieved very good performance because they can learn an optimal strategy and have the ability to evolve itself when the environment changes. Okay, so however, while people, they are trying to focus on designing more and more such adaptive neural networks to optimize the data path functions, they rarely care how to efficiently deploy them, especially how to deploy them with the most widely adopted data path, the Linux kernel data path. Okay, so before describing the actual deployment problem, we will first look into the workflow of how an adaptive neural network based algorithm works. So let's take a neural network for congestion control as an example. So first, the network stack had to collect the necessary signals or information for the neural network inference, such as throughput ratio, latency, and so on. Then they will pass the data to the neural network to perform an inference. While performing the inference, the neural network will also fine-tune itself, right, to learn the new strategy. Then the results, such as the target flow sending rate, it will be enforced back to the networking stack to control the actual flow sending behavior. Okay, so now let's put these things into the real world deployment, right? So first we find the data collection and the result enforcement, they should be performed in the kernel space because these models have to be directly interacted with the kernel space networking stack. In contrast, the neural network inference and fine tuning, they actually preferred in the user space, right? Because they can leverage existing software frameworks. Therefore, when the neural network is used to optimize the kernel data path functions, actually there exists a cross-space communication. So now we have a problem, right? So how to set the communication interval, right? So now let's start from a very simple case. And we use a congestion control plan, the CCP, also a paper from SIGCOMM to deploy the neural network in the user space. And the CCP can use the neural network to control the congestion control module in the kernel space. Okay, so we set the communication interval to be about 1, 10, and 100 milliseconds. And we will only launch one flow, and the flow is controlled by the neural network. And we also launch some UDP background traffic to emulate network congestion. And we measure the good of the flow. Okay, so the experimental results is as follows. And we can observe that if we have a very small communication interval, the flow good output becomes higher, and from around 580 Mbps to 670 Mbps. And the results show that the fine-grained communication is actually needed for those neural network-based algorithms. So you may wonder why, right? So we also perform some tool experiment to visualize the problem to give you a more understanding about this phenomenon. So this figure actually shows an emulated experiment when 10 ms communication interval. And the figure shows the ingress and egress speed of the bottleneck queue, and also show the output of the flow. And then we can see under the 10 ms communication interval, actually the neural network cannot timely control the sending rate of the flow, which called the sending rate of the flow cannot even converge to the bottleneck link. That's and this, like such control will lead to dramatic queue oscillation, right? And which may cause packet loss and degrade the output of the flow. So in contrast, if we change it to a small control interval, and it does not cause this problem, because the flow sending rate can be timely adjusted by the neural network. And the result further show that the fine-grained communication is preferred for those N-based algorithms. Okay, now let's answer another question. So, is a small communication interval always good? Okay, the answer is definitely no, right? To explain it, we will also perform another experiment by launching multiple concurrent flows in a non-conjectured environment. And we will also launch pure kernel implementations of BBR as baseline. And then we measure the aggregated throughput of all flows. And then we can observe that when we have more concurrent flows and a smaller communication interval, the aggregated throughput degrades more. For example, when the communication is 1 millisecond and we have 10 concurrent flows, the aggregated throughput cannot reach half of the baseline. Okay, again, why? So to answer this question, we use a tool called MP-State to investigate the root cause. And we measure the CPU utilization of both actual data path execution and the CPU utilization used in handling software interrupts caused by clock space switch. And we can observe that when the communication interval is very small, most of the CPU actually is wasted on handling software interrupts rather than the normal necessary data path execution. So it leads to a dramatic performance degradation. Therefore, a small communication interval causes large overhead and degrading the performance of data path functions. Okay, so from the above two simple cases, we can conclude that the user space deployment of a neural network suffers from either performance degradation or large overhead, which makes us to think, shall we just put the neural network directly in the kernel space, right? If we put it in the kernel space, there will be no communication, right? So actually there are two approaches. First, we can directly design a full functional neural network inference and fine-tuning framework inside the kernel space. However, as we know, the kernel space development has many constraints and is actually very complex, right? So moreover, to allow the neural network fine-tuning, such as retraining, right, with high precision, you have to use floating points. However, using floating points in the kernel space requires turning on and off the SIMD FP instructions, which will also cause performance degradation. So we have performed the experiment, and we see if we do this way, we will actually have up to 90% performance degradation. So second, we can follow some previous SIGCOMM papers, right? We can convert the neural network into some lightweight ones, right? And those lightweight neural networks are actually more suitable in the kernel space, such as decision tree. However, if we convert those neural networks in the decision tree, the lightweight neural networks lose the learning capacity to adapt to the changing environment, right? So as a result, directly deploying adaptive neural networks in the kernel space also leads to suboptimal performance due to either large implementation complexity, overhead, or lack of adaptation. So our question is how or can we design a high-performance adaptive neural networks for kernel data paths to optimize the function performance? Okay, so our answer is LightFlow. LightFlow is actually a cloud-based hybrid framework, and the insight behind the LightFlow is that instead of adopting one control path for both model inference and fine-tuning as the state-of-the-art adaptive neural networks do, LightFlow decouples the model inference from the model tuning and then put it into like two paths so that each of them can be executed in the right place. The first, the neural network for kernel data path functions, they actually require very frequent inference to be responsive. So we should put them in the kernel space, can reduce overhead, right? So second, the online adaptation is suitable in the user space because it can benefit easy to use APIs, advanced features such as floating point, right? And brought by those mature softwares and libraries in the user space. However, the decoupling is not straightforward, right? We will have some challenges. First, the decoupling method requires two neural networks of different design targets, One is compatible with the kernel space environment and can be efficiently executed there, while the other one is should be compatible with the user space machine learning frameworks. And the second, since only the user space deployed neural network, it will be further tuned, right? So the neural network deployed in the kernel space cannot timely react to the changing networking environment, degrading the performance of data path functions, right? So the third problem in tuning the user space deployed neural network requires data delivery from the kernel space to the user space, right? And such data exchange from the kernel space to the user space will also lead to massive cross-space communications, degrading the performance. Okay, so to overcome these challenges, the design of light flow is as follows. Okay, so first, the light flow is a hybrid solution, and showing it contains both user space and kernel space components. And the second, without letting the users to develop two neural networks, light flow can automatically generate a neural network snapshot based on the user space design and train the neural networks. And the snapshot is deployed in the kernel space and used for inference only. And the third, the neural network in the user space is further retrained with batch data from the kernel space to reduce the data exchange overhead. And lastly, light flow can conservatively update the snapshot to make it adapt to the changing environment while not compromising the performance. Okay, now we will introduce some of the key components of light flow in detail. First, we will introduce how light flow generates a neural network snapshot. First, as discussed, using floating points is not preferred in the kernel space. So we will first perform integer quantization with high precision to convert all floating points numbers into integers. Second, we just leverage our very simple observation that neural network is usually composed of different layers. And one type of layer, it actually shares the same computation logic, but different parameters, right? So therefore, we can prepare all kernel compatible template implementation of all types of layers. Then given a particular neural network, we can just extract the quantized parameters and then synthesize the template to generate a kernel space code automatically. So second, we will introduce how we perform an online adaptation for user space deployed neural networks. First, we do not deliver the data to the user space once we obtain any new data because it also causes massive cross-space communication, making light flow suffer from the similar overhead problems we discussed before, right? So in contrast, we deliver the new data in a batch, or we just collect all data within an interval, and then we deliver it once in a batch. Okay, then why such batch mode works? And actually, we have like two observations. First, the network characteristics usually do not change in a very fast manner. So it actually leaves us the time to tune the neural network in a batch mode. Okay. So second, when the neural network is performing online adaptation, when it's evolving itself, it does not always lead to better performance before it converges. So our experiment show if the online adaptation does not converge, it may cause non-optimal performance. The performance may be worse than the original one. Okay. So we just use the batch mode. Okay. The second question we have to answer is how to determine the batch delivery interval. Since a small interval causes large overhead, while a large interval causes the neural network to lose the ability to learn and adapt. So we recommend to set the interval between 100 milliseconds and 1000 milliseconds. Okay, after performing the neural network fine-tuning, light flow will evaluate whether it's the right time to generate a new neural network snapshot and update the snapshot. Okay, so the evaluation is actually based on two aspects. The first one is correctness, which means the online adaptation should converge. And the second one is that the new neural network has enough difference compared to the existing snapshot. So when updating snapshot, light flow also designs the active standby switch mechanism to reduce the impact from kernel space locks. And you can just refer to our paper for more details. Okay. And the implementation of light flow also contains both the user space and the kernel space implementation. So in the user space implementation, we mainly provide a standard interface. The light flow users, they can provide their own implementation. In this way, light flow is flexible to be extended to support different neural network to optimize different data path functions. And the second, the kernel space implementation also follows the modularization method for high extensibility. The core idea to make neural networks separate and standalone kernel modules in order it can be replaced freely, right? So for different data path functions, as we mentioned before, we have to develop input collector and those output enforcer modules. And the light flow has already provided such modules for canary control, flow scheduling, and load balance. And although LightFlow had tried to lower the difficulty of applying new neural network to optimize data paths, it still remains a limitation right now. And the users have to develop their own like kernel modules to collect and enforce the results. And this may involve some engineering efforts. Okay. So finally, let's evaluate how LightFlow can optimize the real-world applications. And here we choose 3 applications for evaluation. The first one is congestion control, and we will use LightFlow to deploy a rule and MOCC. And the second application is flow scheduling, and we will use a feed-forward neural network from NSDI paper, and the neural network is used to predict the flow size, and then we can use the predicted flow size to schedule flows. And the third, we will design and train neural network for path selection to achieve load balance, and use LightFlow to deploy the neural network. Okay, so we will evaluate the 3 applications. Okay, so first, now let's see how LightFlow supports congestion control. Okay, first, at our previous experiment, we will first evaluate a single flow in a congested network environment and measure its good put. And we can see flow controlled by LightFlow with both a ruler and MOCC, it can achieve higher good put than those flows controlled by CCP. And furthermore, the standard deviation of good put achieved by LightFlow is much smaller than CCP with large communication interval. And the results show that by eliminating the cloud-space communication, LightFlow makes the neural networks more responsible, leading to a better and more stable performance. And the second, we also evaluate the aggregated throughput of multiple concurrent flows in a non-congested environment, right? So LightFlow with both a ruler and MOCC achieve comparable performance as pure kernel implementations, and moreover, LightFlow largely outperforms CCP by more than 60%. So the results show that by eliminating the overhead caused by cloud-space communication, LightFlow with those neural networks can achieve comparable performance as pure kernel space implementations. So LightFlow also preserves the capacity for those neural networks to learn and adapt to the changing environment. So compared to the non-online adaptation settings, LightFlow with a ruler and MOCC can learn and adapt to environmental dynamics, so it can achieve significantly better good put. Next, we will move to the flow scheduling applications. Since we cannot use CCP here, we develop our own cloud-based communication implementation using chart device and NetLink. We first compare the inference latency of different schemes. The experiment results show that LightFlow can largely reduce the prediction latency by eliminating those communications, right? So then we evaluated the flow completion time when using different deployment mechanisms of the neural network for flow size prediction. The results show that LightFlow with the feed-forward neural network can largely outperform the other 2 user space deployed solutions in all cases, showing that LightFlow is actually a very effective solution for flow scheduling. Okay, lastly, we will use LightFlow to support the load balance. And in this application, we developed and trained a MLP model with TensorFlow. The model has 2 hidden layers with a ReLU activation function, and each layer has 12 neutrons. And the results show that LightFlow with the model largely outperform other schemes, and it will outperform user space deployed model by 60% on short flows and 16% on long flows. So now let's conclude my talk. And in this paper, we first point out that existing deployment of adaptive neural network for kernel data paths suffers from inevitable performance degradation problem. Then to solve this problem, we propose LightFlow, a hybrid solution to deploy the adaptive neural network for the kernel data paths. Thus both the neural network inference and tuning can be at the right place. And we also use LightFlow to optimize 3 real-world applications, and the evaluation results show that LightFlow can meet all its design goals. Okay, that's all of my talk. Okay, thank you. Questions are welcome. Okay.
Yeah, thanks, Junxue, for the nice talk. So, any questions from the audience? You can raise your hand, or you can type your question in the chat window. So no questions. So okay, someone. Okay, let me. Okay. So, yeah, go ahead.
Okay, I wanted to know the meaning of your 10 minutes of the picture in your topic lab.
Which one? You mean? Oh, sorry. Let me.
In your first, yeah.
This one? This one?
Yeah. 10 minutes.
Okay, so what do you mean by 10 minutes?
So, before.
You mean this one, right?
Yeah.
Oh, okay, yeah. Okay, I will explain it in detail. So, in this environment, actually, we change the traffic pattern every 20 minutes, and you see if the neural network cannot learn and adapt to the new environment dynamics, it cannot the performance of the neural network will degrade, right? Because we have changed the background traffic pattern, and if the neural network can learn the new dynamics of it can learn the traffic pattern. It can also, it then can boost its performance to the ideal one. Okay, so the 20 minutes is something like it's we are doing a change in the traffic background. Okay.
Thank you.
So due to time limitation, I think we can move. So if you have more questions to Junxue, you can ask question offline. So our next speaker is Peng Zhang. So Peng Zhang is a professor from the Xi'an Jiaotong University. So before joining Xi'an Jiaotong University, he received his bachelor degree from the Beijing University of Post and Telecommunication and the PhD degree from Tsinghua University, both in computer science. So he was a visiting researcher at Chinese University of Hong Kong and Yale University. His research interests include network verification, programmable networks, and network security. So he has published papers at major networking conferences such as CCOM and SDI. So yeah, so Peng, go ahead.
Okay. Thanks for the introduction, and very happy to be here to share our work, which has been accepted to CCOM 22. This work is joint work with my master's student Dan Wang and also Aaron from Colgate University. In our network, we know that there are many outages. For example, the Southwest Airplane and Alibaba and BlackBerry, Central Link, they all experience very large outages, which cost them a lot of loss in revenues. So to prevent these outages, one approach is to troubleshoot the outages after they happen, but this is not the ideal approach. The ideal approach is to verify the correctness of network before we put the network into production. So network verification has been around for 10 years. It tries to approach this ideal network management mode. So in network verification, operators firstly give the verifier a proposed configuration, and the network verifier will return that all the properties are satisfied or return a counterexample that can help operators to fix the problem. So after that, the configuration which has been verified will be put into the production network, and there will be no outages after the configuration is triggered in the network. So network verifiers can help operators to prevent outages proactively instead of resolving them reactively. For network verifiers, lots of interesting questions. Are all the prefixes reachable when we bring down some primary router for maintenance? And is the subnet reachable for 99.9% of the time? And are all the prefixes always reachable, even a bounded number of links fail? To answer these questions is very challenging because you need to reason about the network forwarding behavior across a large header and feeder space. just consider the file tuple. It will have 2 power 100 packets in total. And if there are 1,000 links and any 3 of them may fail, you will need to consider over 100 million failure scenarios in total. So this is quite large. So existing verifiers need to handle this challenge. One type of verifiers, they propose a packet equivalent class. So what is packet equivalent class? All the packets traversing the same forwarding path along the in the network will be treated as a single packet equivalent class because all the packets, they have the same behavior. So example verifiers include Batfish, Plankton, and Shapeshifter. These verifiers works by firstly simulate the network control plan, including the configurations to generate the data plan. By data plan, I mean the forwarding rules in the data plan, for example, the FIPS. So here we can see that we have several forwarding rules there at router A and B. Because this is very simple toy example, we can see that there are only 4 rules. And based on these 4 rules, we have just 2 equivalent classes. One is for 192/2 and one for the 128/2. Each equivalent class has a different forwarding behavior, that is a different forwarding path. But suppose that the link from A to C fail. Then we will need to simulate the control plan again, and we will have a different set of forwarding rules. And in this case, we only have one single packet equivalent class, that is for the 128/1. So the message here is different failure scenarios have different packet equivalent classes. So if you want to cover all the packet failures, you need to enumerate all the failures and compute for each failure the equivalent classes. So in the other kind of approach is to handle the failure equivalent classes. That is, they try to identify the equivalent classes of failures that will result in the same forwarding path for a specific source and destination pair. For example, here let's consider a single source destination pair from router A to prefix 292/2. Then we can see the green arrows show the forwarding path. Then in this case, we have 2 failure equivalent class. One is there is no failures. Clearly, this is very simple. And the other is link AC fail. Because link AC doesn't matter because the forwarding path doesn't traverse link AC. So even link AC fail, the forwarding path is not changed. So they belong to the same equivalent class. The other one is failing the other. It includes 6 failure scenarios, and all these scenarios will result in no packets received at router C. So they belong to the same equivalent class. But consider another prefix from router A to 128/2. Then we will have a different forwarding path by default. Then in this case, we have different set of equivalent classes. For example, here we can see we have the first equivalent class that's standing for link AB fails or link BC fails. They will have the same effect on the network behavior. And for second one, link AC fails, then A will choose B as the next hop. So the forwarding path will change. The other one is failure equivalent class 3. There will be no traffic there because the packets will not be received at router C. So in summary, existing verifiers can either leverage the packet equivalent class to handle the packet space, but enumerate the failures, or they need to leverage the failure equivalent class to handle the large space of failures, but they need to enumerate the packet space. But as we see many interesting questions, they need to explore the product space of packets and failures. So non-existing verifiers can do that. One exception is config2spec, which has been proposed in NSDI 2020. It tries to resolve this tension by alternating between these two methods, but it doesn't fundamentally solve this problem. Besides the scalability, the other challenge is the generality. Suppose that this is a failure space, and we have 1 failure, 2 failures, 3 failures, and more than 3 failures. Then suppose that the property holds in this green area. And determinist verifiers, including ARC and Tiramisu, Huoye, and Minesweeper, they try to identify some counterexamples that violates this property. For example, there's a counterexample here. And these verifiers will conclude that, okay, the property only holds for k equals 1 and k equals 2, but doesn't hold for k equals 3 link failures. So it will conclude that the failure tolerance is only 2. But suppose that we are interested in the other question is, what's the probability the property holds? To answer this question, you need to account for this area, because this area also makes the property hold, but this area is totally ignored by these verifiers because they are out of the boundary of the failure they consider. So recently, the other type of verifiers, including NetDice and ProbNV, they try to enumerate all the failure scenarios which make the property hold, and until they cover all the failure, all the scenarios that the property holds. So this can calculate the probability, but it's clearly more time consuming because it's clear it's more expensive than just searching for a counterexample, because it's need to find all the positive examples. So to conclude, existing verifiers, they like scalability and also generality when they try to explore the space of headers and failures. So our research question is, can we explore the product space of the packets and failures in scalable and general way? Our idea is to not assuming the link is up or down, but let it be some variable. And we introduce a Boolean variable for each link to represent the link is up or down. And also we introduce Boolean variables for each packet bit. For example, if we consider IPv4, we have 32 bits. Then in a high level, SRE will take in the router configuration and the symbolic topology as input, and we'll do the route computation. Different from existing traditional simulation process, SRE will do a symbolic route computation. That is, it will explore the cases where the links up or down, and it calculates all the possible routes in the network. The result is a symbolic RIP, and based on this symbolic RIP, we can calculate the forwarding passes for the packets. We also let the packets to be symbolic to explore every single packet in the network. The result of SRE is a set of packet failure equivalent classes, or PFECs. And each PFEC corresponds to a folding path and is represented by a binary decision diagram here. In the first step, for symbolic route computation, we will propagate the route in the network. But different from existing verifiers, we will introduce a Boolean variable for each route, standing for the condition that this route will be propagated inside of the network. For example, here we can see that router A will receive a route from router C. The condition is that LAC is true because LAC needs to be up. Similarly, router B will receive another two routes, also carrying the link conditions. In the second round of route propagation, router A and router B will exchange the routes. And after the exchange, each router will receive more routes and it will update the link condition. For example, we can see here, router A receive another route from router B, but this route is only valid if the more preferable route from router C is not there. So we need to negate the topology condition LAC. And since the prefixes can also be represented by Boolean variable, so we can represent the prefixes here. What we call as a symbolic RIP. This symbolic RIP will each one is just a Boolean formula, and we compute we call as a port predicate for each port of the router. For example, here we can see from router A we have two ports, one for router B and one for router C, and we calculate the conjunction of the forwarding rules. And similarly, we can calculate the port predicate for router B. And since we also have an echo here, we will also calculate the predicates here. So with that, we can traverse the network using the symbolic packets. And we have first packet filtering class traversing from A to C, and the other one from A to B to C. Each is represented by a Boolean formula. So let's then we are ready to answer some questions. Firstly, what's the failure tolerance from router A to router C? To compute that, we do the disjunction of these two PFECs, because these two PFEC can both arrive at router C. This actually is a Boolean. This is actually a binary decision diagram. Due to lack of time, maybe I don't have time to explain it in details. But each H here is just standing for 1 or 0. The dashed lines for 0, the solid lines for 1. So to calculate the failure tolerance, we only need to find the shortest path. For example, here we can see from the right side, we can see the shortest path is 2, because we assign the weight 1 to the dashed lines. So that means to break the property, we only need to violate, we only need 2 failures. 2 failures is enough to break the property. So the failure tolerance is 1. Then to calculate the probability is also very simple, and you assign different weights to the edges. For example, the link fails with 0.1 probability. So you assign the 0.1 to the dashed lines and the 0.9 to the solid lines, and you accumulate the weights accumulate the weights of all the passes to terminal 1. That is the property where the property holds. It is very easy to calculate that on this binary decision diagram. Here is the highlight is that we are checking properties, not caring about underlying OSPF or BGP stuff. We don't care about the topology. We only operating on a very simple graph. So we translate the problem of net verification to a set of simple graph algorithm, which is very easy and also very general. And we introduced some optimizations which are very critical to make our work, our method work, because some problems like path explosion. In our experiment, we checked all the pair reachabilities in some one topologies, and we compared to still state-of-art methods like Batfish, Minesweeper, and Tiramisu. Then we can see that SRE is 10 times faster. But for fat-free topologies, which has more redundant links, SRE is not as fast, but still comparable to the state-of-art Tiramisu. When calculating the probability, we are comparing to the NetDice, which has been published in CCOM 2021. And we can see that it's 10 to 100 times faster than NetDice on the 91 topologies. To conclude, net money verification test requires reasoning about network correctness across large header space and filter space. But non-existing verifiers has the scalability or generality to answer these questions. SRE symbolic executes the network model to scale, and the scalability is achieved in a general way. So it can assume a deterministic failure model or a probabilistic failure model. Our future work include to incrementally execute the network model, so that after the configuration change, we will not need to from scratch simulate the control plan. Okay, with that, I wrap up this talk and happy to answer any questions here. Thanks.
Yeah, thanks a lot, Peng. So any questions from the audience? You can raise your hand, or you can, type your question in the chat window. Either is fine. Yeah. So Peng, I have one question. So you mentioned that your future work. So does this mean that every time when we apply and some configuration change, right? We only check the diff rather than check the configuration from the very beginning, right? Is this what you mean?
Partially, I think it's very important task to check the diffs. Like our previous work in this year's ICI, we published another paper to check the diffs. It can incrementally calculate whether a property is satisfied or not. But here we care about not only the result, but also the process. That is how to calculate that. We need to incrementally calculate that. Currently, we just simulate the control plan from scratch because we don't have some methods like the other approach DNA that they can calculate incrementally, but currently we don't support the incremental computation, so it can cost relatively a long time. At least DNA can achieve this in 1 second, but maybe we need 100 seconds for something like that.
Okay.
Thanks.
Thanks. Yeah. So let's move to the next talk. So so our next speaker is the Yihao Zhao from the Peking University. So he's the first year PhD student advised by Professor Xuanzhou Liu and Xin Jing, and his research is in computer system and networks with a special focus on cloud computing. He received his bachelor degree from the Peking University Turing class in 2021. So let's welcome the speaker.
Okay, thanks for your introduction. Okay, can you share my screen?
Yeah, I can see your screen.
Okay, great. Okay, hello everyone. I'm Yihao Zhao from Peking University, and today I'm glad to share our work, multi-resource interleaving for deep learning training. This is a joint work with Yuanqiang, Shen Zhe, and Xin from Peking University, Yang Hua, and Yibo from ByteDance. In recent years, deep learning is becoming popular. A wide spectrum of deep learning models is proposed for various fields, such as computer vision, natural language processing, and reinforcement learning. Deep learning training has become an important workload in enterprises clusters. Deep learning training uses multiple resource types. The training process is iterative. That is to say, the training process goes through one iteration by one iteration. For each iteration, there are usually 4 stages, and each stage mainly uses a specific resource type. Specifically, storage I/O for loading training data, CPU for preprocessing and simulations, GPU for forward and backward propagation, and in the last, network I/O for communication in distributed training. Nowadays, deep learning models vary dramatically in model size and types, and training them is bottlenecked on different resource types. To train deep learning models, enterprises build GPU clusters, and the GPU cluster is composed of lots of nodes, and each node contains the aforementioned 4 resource types. Users submit deep learning training jobs to the cluster, and the scheduler schedules the job and allocates resources. The goal of cluster scheduler are like minimizing the finish time of jobs and maximizing the resource utilization. Existing efforts have made great significant progress in deep learning training. However, they assume that GPUs are the bottleneck in deep learning training. Most deep learning schedulers allocate GPUs to a job exclusively. Some explore resource sharing, but they consider only GPU sharing. As deep learning training is bottlenecked on different resource types, these schedulers make the opportunity of multi-resource sharing. There are mainly 2 challenges of multi-resource sharing. First, sharing resources may bring great interference and affect the training speed, especially for jobs on GPU. So we need to reduce interference among shared deep learning jobs. Second, considering the goal of the cluster scheduler, we need to improve both the job and cluster efficiency. To solve the challenges, we propose Muri, which utilizes multi-resource interleaving to improve both job and cluster efficiency. There are mainly 2 techniques in Muri. The first one is multi-resource interleaving. Muri packs jobs to share the same set of resources by interleaving their stages in time. We can reduce interference among shared jobs with multi-resource interleaving. The second technique is the blossom-based scheduler. The scheduler decides the jobs in one sharing group and the sharing patterns to improve both job and the cluster efficiency. Muri is composed of Muri scheduler and Muri executor. Users submit deep learning training jobs to the Muri scheduler. The Muri scheduler maintains a job queue to buffer the submitted jobs and makes job scheduling decisions. There are 3 components in Muri scheduler. First, the resource profiler provides the resource usage for each job when it is first submitted. And the resource profiler also estimates the interleaving efficiency at the input of the scheduling algorithm. Second, the job scheduler periodically schedules the job from the job queue to the cluster machines. Next, the worker monitor collects the resource information of each machine and tracks the progress of each job. The mirror executor is located on each machine. The executor receives jobs and grouping strategies from the scheduler and executes the jobs according to the grouping strategy. There are mainly two types of multi-resource sharing: space sharing and time sharing. Here, I will show an example to compare these two sharing types. 4 deep learning training jobs A, B, C, and D are shown in blocks with different colors. We show one iteration of these 4 jobs. When a job cannot fully utilize one resource type, it can share the resources with other jobs. When the jobs are shared in space, at every moment, each resource type on one machine is used by multiple jobs. As for time sharing, we can shift the stages of different jobs and share the resources among the jobs. At every moment, each resource type on one machine is used by only one job. While in space sharing, due to this interference among shared jobs, each stage is lengthened, and the iteration duration of space sharing 9 is much longer than the iteration duration of time sharing, which is 4. Apparently, time sharing is the one that can solve the challenges of interference. Mirror utilizes the fine-grained multi-resource interleaving to share jobs in time. And 2 characteristics of deep learning training enable the time sharing. First, each iteration of deep learning training has 4 stages in general, and we can shift the stages to perform multi-resource interleaving. Second, the iterative pattern of deep learning training enables us to make the interleaving decisions at the very beginning and at the job level, whose overhead is really low. In practice, pipelining is commonly used to overlap the usage of different resources. For example, it is common to overlap the gradient synchronization with backward propagation, which overlap the GPU and network, as shown in the figure. We remark that the ideas of pipelining and multi-resource interleaving are orthogonal. Pipelining exploits the intra-job aspect, while multi-resource interleaving exploits the inter-job aspect. Here, I show a simplified example to illustrate the benefits of multi-resource interleaving compared with pipelining. We show the resource usage of GPU and network I/O of 2 jobs, A and B. Network is underutilized for job A, and GPU is underutilized for job B. The throughput is calculated for the same set of resources, say 1 GPU. Interleaving jobs A and B, as shown on the right, can improve the throughput by 1.7 times in comparison with running them separately. To maximize resource utilization, we need a metric to compare different grouping plans. Intuitively, a grouping plan that can perfectly overlap the resource usage of the jobs is better than the one that cannot. Here, we use interleaving efficiency to represent how perfect the grouping plan can overlap the resource usage of the jobs. Better resource interleaving efficiency means the less idle time of the resources. Therefore, we define the resource interleaving efficiency, gamma, as the fraction of time that some resources are occupied. To take into account all resource types, we take the average occupied time ratio of each resource. And the occupied ratio is the occupied time divided by the iteration duration. The iteration duration can be estimated by adding the maximum duration of concurrent stages of interleaved jobs, as shown in the blue equation. Given some jobs, Murray schedulers group these jobs so that the interleaving efficiency of the entire grouping plan is maximized for higher resource utilization, along with shorter job completion time. First, let's consider a simplified problem in which at most 2 jobs can be grouped. We can formulate this problem as a maximum weighted matching problem. Specifically, We build a graph where each node represents a job. For example, there are 4 jobs A, B, C, and D at the very beginning. And every 2 jobs are connected by an edge, with the interleaving efficiency of grouping these 2 jobs as the edge weight. Then, a grouping plan corresponds to a matching of the group graph. Therefore, finding the optimal plan can be converted to finding the maximum weighted matching of the graph from all possible matchings. Maximum weighted matching is a well-studied problem in graph theory, and the Blossom algorithm can find the optimal matching in polynomial time complexity. However, the problem becomes complicated when the resources are more than 2 types. With k resource types, we need to consider matching k jobs on a k-dimensional hypergraph, where each hyperedge represents grouping k jobs. Finding the optimal grouping plan is transformed to maximum weighted k-uniform hypergraph matching. And this problem is NP hard. So we designed a multi-round heuristic algorithm to handle the general case of multi-resource types. The main idea is to divide the matching process into multiple rounds, and each round uses Blossom algorithm to group jobs. At the end of each round, each pair of nodes in the selected matching is merged into one node. The heuristic algorithm still has an acceptable polynomial time complexity. Except for the 2 main designs of Murray, we also optimize Murray from other aspects. First, in widely used distributed training, each worker trains a copy of the model locally and performs model synchronization at the end of each iteration. Because of the need for intra-job synchronization, the speed of a job depends on its slowest worker. For example, job A on GPU 2 had to synchronize with that on GPU 1. On the other hand, multi-resource interleaving introduces new dependencies among jobs. For the distributed training job A, each worker of job A interleaves with different jobs B and C. And in this scenario, inter-job interleaving interacts with intra-job synchronization, which brings additional slowdown for job C. To avoid the slowdown, Murray only groups jobs with the same GPU requirements. Second, given multiple resources, there are several orderings to interleave the jobs. Different orderings have different interleaving efficiency. For example, part A shows the best ordering of interleaving jobs A and B, whose interleaving efficiency is about 5. Part B shows the worst ordering of interleaving jobs A and B, whose interleaving efficiency is about 0.4. To address this problem, we enumerate all the orderings to find the best one, as the number of resource types is typically 4 for deep learning jobs. The enumeration can be completed quickly. Additionally, as multi-resource interleaving improves mixspan inherently, we optimize for the other common metric, average job completion time, also known as average JCT. Murray integrates 2 effective methods, SRSF and 2D-RAS with multi-resource interleaving to minimize average JCT. SRSF uses the remaining service as a priority, while 2D-RAS uses the executed service as a priority. So Murray assigns a priority to each job according to SRSF and 2D-RAS and schedules the job with higher priority first. With this design, we implemented a prototype of Murray with about 7,000 lines of code and integrated it with PyTorch. Our evaluation is performed on a 64 GPU cluster using NVIDIA V100 GPU. We use the real-world traces from Microsoft and 8 mixed popular deep learning models covering computer vision, natural language, processing, and reinforcement learning. We evaluate the overall performance of Murray and 8 mixed popular deep learning models on the 64 GPU cluster using 400 deep learning jobs submitted over 10 days. Our evaluation covers both scenarios when the job duration are known and unknown. When the job durations are known, MURI uses SRSF as a priority and represented by MURI S, and it is compared with RTF and SRSF. When the job durations are unknown, MURI uses 2D areas as a priority, represented by MURI L, and it is compared with Teresias and Themis. The metrics are normalized with those of MURI. Compared with the baselines, MURI achieves higher job efficiency whether the job durations are known or unknown, and MURI improves average GCT by more than 2 times and improves tail GCT by more than 2.5 times. Additionally, MURI achieves higher cluster efficiency with about 1.4 faster mix span. To show the benefits of MURI in detail, we also evaluate some detailed metrics, and these figures show the GPU and the CPU utilization of baselines when the job durations are unknown. And the yellow line shows the resource utilization of MURI. As you can see, MURI can improve 36% higher average GPU utilization and 30% average CPU utilization. We also conduct trace-driven simulations to evaluate MURI with a variety of workloads. Here, we perform simulations over 4 traces, with job numbers varying from 1,000 to about 6,000. In simulations, we compare MURI with one more baseline and span, which is the state-of-the-art GPU sharing scheduler. As shown in the figures, MURI improves average GCT, expands tail GCT greatly. Our paper has many more experiments, including the performance when job durations are known, more detailed metrics, and analysis of MURI. To conclude, MURI is a multi-resource cluster efficiency cluster scheduler for deep learning training jobs. It introduces multi-resource interleaving to share jobs in the time dimension and utilizes a blossom-based scheduling algorithm to maximize the interleaving efficiency. By doing so, it improves both job and cluster efficiency. MURI is open sourced at the listed URL, and thank you for listening.
Yeah, thanks a lot, Yihao. So any questions from the audience? So I have one question. So I'm curious that what if there's some failures during the schedule? For example, for example, when you want to schedule some job, you find that okay, unfortunately, one rack of the server is down. For example, due to some power outage, or for example, when you run some job, right? So the job has, the job is, is killed by the user because they found out that the job is wrong. They want to they want to open new, they want to submit a new job. So I'm curious if your work can handle this kind of, failure or exception case.
Okay. Yeah, that's a really great problem. And well, at MURI, we can handle these failures. For the first case you mentioned, like some machine errors or machine failures, and our scheduler will monitor the execution process of the deep learning jobs and may resubmit these jobs to re-execute these deep learning training jobs. And for the second case, like the users may stop this job and restart a new job. I think it's a common case in deep learning clusters, so it can be correctly handled by MURI.
Okay, thanks a lot.
Thank you.
So our next speaker, is Hao Zheng from the Nanjing University. He received his bachelor degree from the Southeast University in 2020. He's working towards PhD degree in Nanjing University. So his research interests include software-defined networks and network management.
Can you hear me?
Yeah, I can hear you.
Okay. Thanks, Dr. Bai, for the introduction. Hello, everyone. I am Hao. Today, I will talk about our recent work on network measurement. This work, named Flymon, is a research project of Nanjing University and Peking University, China. Flymon is a measurement system that can make on-the-fly reconfigurations among a large set of sketch-based measurement tasks. Let's first look at some backgrounds. We know that network measurement is important to data center operators. Many management tasks rely on measuring real-time traffic statistics. For example, the network operators may need to diagnose network abnormals such as congestions, head of line, and jitters. To improve the performance, it needs to get heavy hitters and other traffic statistics, such as flow cardinality, to perform traffic engineering. As for security, measurement is also helpful in finding network intrusions. There are a lot of measurement tasks. If we make an abstraction for common flow level measurements, we can decompose a flow level measurement task into a key and an attribute. For example, heavy hitters on source IP addresses can be abstracted into taking source IP as the key and frequency as the flow attribute. The frequency can be measured by performing cumulative operations on each packet with the constant number one for packet numbers and packet length for flow bytes. Another example, DDoS victims can be abstracted into taking dest IP as the key and counting distinct number of source IP for each dest IP. Here, the distinct is another flow attribute. So there are many flow keys. They can be any combinations from different protocol fields, even bit level prefixes of these fields. And this case need to combine with an attribute to compose a measurement task. With various common flow attributes, there are a lot of tasks that need to implement it on switches. With so many different tasks in the network measurement, it usually needs to switch among several tasks to locate the root cause of a problem gradually. Suppose a user complains that the performance of their network service is abnormally degraded. The operators then take up his weapons. He needs to switch among various measurement tasks of all related devices to gradually locate the root cause of the problem. So the key question here is that how many different measurement tasks can the switches support for the on-the-fly reconfigurations? Currently, sketches are the most popular measurement methods as they can achieve a good balance between accuracy and resource usage. IMT switches provide a great platform to implement sketching algorithms at line rate. For example, countering sketch and the bloom filter can be implemented on IMT hardware, as shown in the figure. The key hardware resources used to implement sketches are PHV, hash, SCOU, and SRAM. We evaluate the resource footprint of 4 sketches and their coexistence labeled as sum in the figure. We find that the current IMT hardware cannot support more than 4 different keys for the above sketches. Based on the problem, we summarize our design goals. Firstly, functionality. Flymon needs to support on-the-fly reconfiguration for extensible sketch-based tasks. Secondly, efficiency. Flymon needs to have high resource utilization to enlarge the number of parallelized tasks. Thirdly, flexibility. Flymon should adapt to memory requirements for different workloads and algorithms. Last, accuracy. Flymon should maintain a high level of accuracy for various measurement tasks. Take an overview of Flymon. When a new measurement task is issued, Flymon only needs to install runtime rules from the control plane according to the task's key and attribute. Then the measurement task can be deployed on the hardware data plane with specified memory space. The design of Flymon includes 4 parts. We first propose the composable measurement unit to accommodate more measurement tasks. We then explore how to map CMUS on IMT hardware efficiently. We also introduce how to realize dynamic memory management based on the CMUs. Finally, we introduce several use cases for helping understanding. Let's first review a strawman solution. This solution is statically implementing sketches on hardware and make reconfigurations by reloading P4 code. Here is the hardware layout of a counting sketch. Packet fields are stored in packet header vector. If we take source test IP pair as the flow key, then the two fields are hardwired to the hash unit to get a memory index. To update the counting sketch, an SLU is required with the add operation to add a value to the counter addressed by the hash index. The problem is that after the P4 codes are compiled and the switch is forwarding traffic, we cannot dynamically change the hash inputs, the SLU operations, and the memory configurations, including size and bitwise. The compile phase reconfiguration in current IMT switches, such as Tofino, requires interrupting running network traffic. It is unacceptable in most scenarios. So our basic idea is to dynamically compose a sketching algorithm by installing runtime rules. We provide a table abstraction with the task identifier as the match field. The table's action parameters include the key, the attribute, and the memory size of the tasks. With the abstraction, we can deploy a task by installing runtime rules. Record the static implementation of sketches. We can introduce some match action tables to dynamically stack the key and the SLU operation. In a nutshell, CMUs are general operation units for measurement tasks combined from different keys and attributes. There are two phases in each CMU, a key detection phase and an attribute operation phase. Each CMU can concurrently perform multiple memory tasks with reconfigurable memory spaces. Below, we discuss two phases in detail. In the case detection phase of CMU, we can locate a dynamic key, which is used as the fixed input of the hash unit. To realize the case detection, we can use a match action table to dynamically copy protocol fields from the original packet header. However, there is a critical overhead on PHV occupancy. We call the overhead as PHV copy. PHV resources are statically allocated in the data plane and cannot be changed at runtime. This means that if we want to spot 5 tuples as a key, we must statically allocate extra 104 bits in PHV for each SLU. Even though a memory task may only need to set source IP as the key. To optimize it, we introduce a less copy strategy. We generate several compressed keys with hash units. Each SLU only selects the compressed keys or the results of bitwise exclusive OR among the compressed keys. Due to the limited number of hash units, there are limited compressed keys can be generated. It is a drawback. We solve this problem by using the recent feature of Tofino that can install masks for the hash units in the control plane. In the attribute operation phase, since each SLU can accommodate multiple stateful operations, we can also use a table to select different operations for different sketches. A potential challenge here is that there are limited number of preloaded SLU operations. However, the sketches need to support in the data plane are more than the number of stateful operations. To optimize it, we propose a reduced operation set for our built-in algorithms. Our principle is to use simple but dedicated sketching algorithms for each attribute. The generation of the reduced operation set includes 2 steps. Firstly, we decompose the algorithms into data plane operations and control plane analysis. We found multiple algorithms can share a stateful operation. For example, CountMin, MRAC, and the Tower sketch share the unconditional add operation. Secondly, we aggregate some simple operations into one stateful operation. For example, the conditional add operation can simulate the unconditional add operation by setting the condition to constantly true. Sorry, the sketch need to support. Another example is that bitwise AND and the bitwise OR operation can be aggregated into a bitwise AND OR operation because the computing power of SLU is usually larger than the operations required by some Maron algorithms. The SLU can decide which specific operation to run by the conditional judgment. According to above discussions, we further divide a CMU into 4 stages. For the case selection phase, we split it into a compression stage and an initialization stage. The compression stage is used to generate several compressed cases, and the initialization stage is used to set case and parameters. For the attribute operation phase, we split it into a preparation stage and an operation stage. The preparation stage translates addresses and pre-processes the parameters. The operation stage selects a stateful operation to execute. To place more CMUs in IMP pipeline, we arrange multiple CMUs in a grouped fashion. There are 2 benefits of the grouped fashion. Firstly, multiple CMUs share a compression stage to save hash resources. Secondly, the grouped fashion can be easily cross-stacked to improve the resource utilization. Let's talk about the dynamic memory management in Flymon. Flymon provides 2 levels of dynamic memory. Firstly, since each CMU can switch to any spotted memory tasks, thus we can achieve unit-level memory management by adjusting the number of CMUs for the memory tasks. However, since the number of CMUs is limited, it cannot achieve fine-grained memory management. We implement a fine-grained dynamic memory inside the CMUs through an address translation mechanism in the preparation stage. We propose 2 basic translation methods, a shift-based and a TCAN-based. We introduce the TCAN-based address translation here. As shown in the figure, CMUs select a compressed K, which can be an index in the whole memory range from 0 to M, where M denotes the number of buckets in the CMU. We can use TCAN tables to judge different cases. If the current address is already in M½ to 3M fourths, we do not need any processing. Here, the address is 0 to M fourths. We can map it to the target address range by adding M³. So the final real address of this key is 5M8. Below, we introduce several use cases or examples of Lemon to support some sketching algorithms. When firstly, we introduce how to use hyperlog to measure the single key distinct attribute in Lemon. As shown in the figure, the original hyperlog log generates a hashing string for each key. The hashing string includes two parts. Several bits are used as an ID to locate the corresponding bucket. The rest bits are used to tracing longest leading zeros. In the control plane, the hyperlog log estimates the different number of k according to the values in the buckets. In Lemon, we simulate this process with the max operation. We first chain to track the leftmost one by finding the maximum value of these hashing strings. The process is equivalent to the leftmost zero tracking. Lemon also supports implementing hyperlog log with the TCAM entries in the preparation stage to locate the longest leading zero. We prefer the max operation here because it can save TCAM entries. The second example is how to implement Bloom filter efficiently in Lemon, which can be used to perform the existence attribute. Bloom filter works on a bit level. However, to support counter-based algorithms, the CMU's counters need to be set to a uniform memory configuration, such as that all SVM buckets are 32 bits. A simple solution is to simply using the 32 bits as 1 bit, but it is not memory efficient. In Lemon, we set both the k and the parameter 1 to the compressed k that we want to check. In the preparation stage, the k is used to locate a bucket, while the parameter 1 is used to stack 1 bit from the 32 bits of the bucket. This process also called one-hot encoding of the parameter 1. In this way, we can make full use all bits in the CMUs to implement the Bloom filter. The third example is the frequency attribute. We use different sketches under different situations. Besides counting sketch, Lemon also supports several sketches to measure the frequency attribute. For example, we support tower sketch, SUMAX, and counter breeze. Here we introduce the tower sketch. The tower sketch adapts to high-school traffic by holding more small bitwise counters for mice flows. The challenge here is how to realize different bitwise counters in tower sketch. In Lemon, we only use several left side bits of the counter, and the parameter 1 is set to a value under this bit range. Note that the unused bits in tower sketch can be reused by other measurement tasks, such as the tasks implemented by the Bloom filter, as discussed above. Below, we talk about our evaluation. We implement Lemon on a wedge twinner-based programmable switch. We use around 5,700 lines of P4 codes for 9 CMU groups in a data plane. We also implement the control plane with Python, and we provide a simulation framework to fast explore the accuracy of our built-in algorithms. We evaluate Lemon on functionality, resource usage, and accuracy. Due to the time limitation, we only show part of the evaluation results. For functionality, we found measurement tasks can be deployed at the millisecond level. one CMU group is sufficient to support 4 frequently used flow attributes. The resource usage of SHA-2 memory partitions is reasonable, which means SHA-2 concurrent tasks can be efficiently performed with one CMU. We also evaluate the impact of the reconfiguration events in Flymon on traffic forwarding. We use iPerf to generate T-shape traffic and measure the throughput of the traffic. We found Flymon has no side effect on traffic forwarding. In contrast, the reconfigurations of the static deployment method will interrupt the traffic for several seconds, about 4 to 8 seconds in our experiments. We evaluate the usage of 6 critical resources by integrating CMU groups into Tofino's baseline switch project, switch.p4. We found that average resource overhead of a single CMU group is less than 8.3%, and the hash resources are the bottleneck. More than 3 CMU groups can be integrated into the switch.p4 project. With the less copy strategy, we can deploy more CMUs when supporting larger candidate case size. In conclusion, Flymon is an extensible measurement framework that focuses on the runtime reconfiguration of various sketching algorithms and the algorithm inputs and memory spaces. We explore Flymon's implementation in RMT switches, including resource utilization, and gave some use cases. We open source our reference implementation of Flymon. Finally, I'm glad to answer any questions about Flymon. Thanks for your listening.
Yeah, thanks, Hao, for the nice talk. So, any questions? Okay, I see there's a question from the audience. Yeah, go ahead. Oh.
Okay, thank you. In your 20 page, there is the Dominic Hashi faction. Is it the same in the 9th page? In your 20 page, there is a Dominic Hashi faction.
Part.
In your 20 page.
Okay. What's the problem? What's your? I cannot understand your question. Repeat.
My problem is what is the CMU group?
Oh, okay. The CMU group is several. Wait. CMU group is several CMU in the figure. They located in the pipeline in a parallelized fashion, and they share one compression stage. Each CMU can select one of the compressed case of this shared compression stage. This is a CMU group.
It can help to same time, right?
No, because the hardware, the RMT hardware can always maintain line rate for traffic forwarding. So we design the CMU groups here is to maximize the resource utilization to support more CMUs. Thus, the targets of the CMU groups is to deploy more CMUs in the pipeline, as shown in the in this small picture. That if we cross-stacked the multiple CMU groups, just like instruction pipeline of CPU, we can deploy more CMUs and more parallelized memory tasks can be executed in parallel in Flymore.
Oh, okay, thank you very much.
Thanks.
Yeah, so due to the time limitation, I think if you have more questions, you can ask the author offline. So yeah, let's thank all the speakers in this session. And yeah, Yiting, go ahead. Yeah.
Okay, thanks, Wei. Since we are a bit over time, let's have a short break, maybe for 5 minutes. And let's come back at 4:10, okay? Let's start the next session at 4:10. Oh, in the meanwhile, could the speakers of the next session gather and test your equipment? Chi-Jin, could you share your screen and see if it works?
Okay.
Okay, yeah. Yeah, it works. Could you try turn the slides and speak a bit?
Could you hear me?
Yes, I can.
Okay.
Okay, and turn the slides a bit.
Turn slide.
Could you change the slides to go to the next slide?
I'm trying. Okay.
Oh, yeah. Okay, it works.
Is my first time use the software run.
Okay, I think it works. It will be fine. So could other speakers also test your equipment? So, Jaden, please wait a bit. We'll switch back to you. Okay. And
Okay.
our next talk is Sayan and let me see. Sayan and Yashash. Could you also test your slides? Oh, so Chijin, you need to stop sharing first.
Okay. Is it work?
Yes. Yashash and Sayan, are you here?
Yeah, hi, am I audible?
Yes. Could you share your screen? Share your slides?
Yeah, sure. Yeah, sure.
Oh, sorry, you are the third talk, right? Okay, it works. Could you say something to test the audio? Hello, could you unmute yourself? I can't hear anything.
Hello.
Hello?
Hello, am I audible?
Yeah. Okay, now I can hear you. How about Sayan? Hello? Hello? Are you saying something? Hello? Cyan, could you type? You have some. Hello?
Can you hear me?
Okay, okay.
Hello.
Now I can hear you. Good, good.
Yeah.
Okay.
Okay.
And
Thank
the last speaker, let me see. Yuxi, are you here?
I'm
Could
here.
you test your slides?
Yeah. Okay, can you see the slides?
Yes. Could you display it?
Sorry.
Yeah, but
Oh,
wait a sec. Yeah.
yeah.
Okay.
Okay.
Yeah. Okay. Now it works. Okay. Chi Ren. Okay. Now it's your time. Yeah. Please share your screen and let's get ready to get started.
Sure. Share my screen. Is it online?
Yeah. Okay, cool. Okay, welcome back, everyone. Well, this is our last technical session of the day. Welcome to this session. I'm your session chair. My name is Yiting Xia. I'm a tenure track faculty at Max Planck Institute for Informatics in Germany. And today in this session, we will have 3 very interesting papers about network data plane. Okay, without further ado, let's start our first talk. So our first talk will be given by Qizhen Wu. Qizhen is currently an assistant professor at the Department of Computer Science and Information Engineering, Changkong University, Taiwan, since February 2021. He received his PhD degree in electrical engineering from National Taiwan University in July 2012. He has founded 2 startup companies, and his research interests includes content distribution, mobile cloud computing, and artificial intelligence. Okay, please start.
Okay. Hello, everyone, and thanks, Professor Shah. I'm CJ from Changchun University. This presentation title is Enable Innovation in Spectrum Management. It's about reflecting the current mobile network structure, and it's actually try to make a fundamental change in how people buy and sell communication resources, especially in spectrum. Most of communication mechanisms in today's mobile network are about how to utilize or management the spectral resource. So this work try to bring a new spectral management way for next generation mobile networks. And honestly, this work is at a very early stage. We do not demonstrate detailed design and experimental result. It's a presentation paper. Any feedback and comment is great. It's welcome. It's great. It's appreciated. Okay, we envision the capital expenditure may become a potential problem of telecom industry. The mobile carriers such like AT&T and Docomo in Japan, they needed to offer high quality mobile service to their subscribers. And they also have to deploy more and more base stations to meet a fast growing data traffic demand. Okay, that result in increased capital investment, spend a lot of money. Okay, here is a number report by Morgan Stanley. 275 billion invested in on 4G. For 5G networks, more than 700 billion until 2025. So we can see that the capital spend of telecom companies is very high and risky. Mobile carrier may not get a significant return on the invest. Okay. And more important is that developing countries may not or cannot play this game. Okay, we can easily break down the CapEx, and there are two major components of invest for the mobile carrier. First is infrastructure development includes radio access network and core networks. We don't get into the detail of those network, and it also should include the operating cost. Okay, the second is spectral license fees, spectral cost. In fact, a mobile carrier needed to acquire the spectral license for communication capacity. In US, the carrier spent 95 billion on spectral license for 5G. Okay, in short, as a mobile carrier, you needed to develop an infrastructure and also be on a spectral license. Okay, which there are two fields you need to pay, infra and spectrum. So as we know, spectrum is a scale resource for communication service, and it's also extremely expensive. Many research work are focused on how to share the spectral band in space of time domain. For mobile network operator, maximizing spectral using or spectral sharing is very important. It's about save money. Okay. In current mobile networks, there are two major technology trends in spectral sharing. Firstly is dynamic spectral sharing. Is a new antenna technology that enable the parallel use of 4G and 5G in the same frequency band. In short, one antenna and two networks, 4G and 5G. And the other one is deploy virtual and centralized radio access network, create a cloud computing architecture for support spectral management in 5G system. Okay, the centralized approach can more easy to reduce the overall infrastructure cost and network complexity. And this centralized cloud architecture attract a lot of attention both in academia and industry. However, mobile carriers still suffer from the same problem, the huge investor problem. Okay. Here's today's mobile network ecosystem. In the past decades, mobile and wireless communication technology achieved a great improvements. Great works significantly boost spectral utilization such as TDMA, CDMA, OFDM technology. However, the high-level architecture of the stereo network are no change over 30 years. Here is a relationship of the three roles in a stereo network ecosystem. It's kind of a hierarchical structure. Okay. First is a spectral owner is like a FCC in US is a spectral management. They often use action framework to sell the right to transmit a signal over the spectral banks and authorize the spectral resource to a carrier. Okay, and mobile network operator is a telecom company. It operates mobile communication service for their subscribers. And the last one is the user equipment. It's a cell phone and a mobile device to communication with the base station of the service provider. From the 1 to 5G networks, it sticks with the triple relationship for a long time. Here we give a main idea of the proposed the intelligent mobile network system. Okay, again, the main purpose is to make a fundamental change in how people buy and sell the spectrum resource. We introduced the three main conceptual ideas. First, we define the 5 hierarchical roles in the new mobile networks we will describe later. And next is spectral recommendations. It turns the high complexity spectral allocation problem to a spectral recommendation problem. We inspired by the word-to-vector embedding technology in natural language processing. Last, we can use in the embedded technology to assign a unique spectral vector to a communication scenario. The spectral vector is a descriptor include GPS location, mobility, direction, active or user property, and QoS requirement, and spectral usage. Based on the training communication scenario data set, the spectrum recommendation can be achieved. Finally, it's a real-time spectrum bidding market. It's used for trading the spectrum resource. We also will describe later. Okay. Here we give you a assumption in this new mobile network compared to a current mobile network system. Here's 5 roles in our assumptions. We conceptually divide the duty of the current mobile network operator into 2 separate abstract roles. First is first the mobile network operator and the spectrum holder. In our assumption, the carrier focus on infrastructure development, and the spectrum holder is accountable for authorizing the use of the radio spectrum. Okay, spectrum exchange is the spectrum broker is enables spectrum can be traded in an open way, just like a stock exchange service. Okay, in intelligent user equipment, we assume that in linear futures, and intelligent user equipment can have the ability to representing the description of the communication scenario with a particular spectrum vector. Okay, to analyze and learning how the spectrum used, and we assume a new object here is a spectral access right app part is a basic training unit for our spectrum bidding market. Okay, the detail will be presented in next slides. Okay, our spectral access right app part is defined as a basic trading unit. Okay, app part is for short. We assume that an app part is a right to access the spectrum in a period of time. Okay, in the design of our new mobile network, each channel of spectrum can be divided into a small division by frequency and geography and time. Okay, we can compute the we can pre-compute the availability of spectrum APA in a predefined hash grid, like a serial network. And APA is a structure like the tuple is a metadata list, including sales, channel, and timestamp and pricing, so on information. There we assume all carriers share the same map of the predefined hash grid. Okay. Okay, here is a proposed new mobile network ecosystem. Find new hierarchical roles is illustrated in this figure. We can see the spectrum owner and the holder is maintain the licensed and unlicensed spectrums, and they are spectrum APNet suppliers, and mobile network operator is at spectrum demand side. Okay. However, the mobile network operator may play the two roles: a spectrum holder and the mobile network operator itself, and so that a carrier can share their his licensed spectrum to others. Okay, the role between spectrum stakeholder and carrier is a spectrum exchange. It coordinates with the spectrum APA bidding request from the demand side and the APA spectrum APA resource from the supply side. Okay, last one is the intelligent UE. Okay, we mentioned before. Here is we introduce the spectrum the idea of spectrum recommendation. As we mentioned before, the intelligent UE we assume that the intelligent UE can represent the description of a communication scenario into a spectrum vector in our assumptions. So we can leverage the deep learning model to learning the historical data contain the association between the spectrum vector and the spectrum allocation. So to analyze the similar communication scenario to recommend the spectrum APA based on the incoming communication scenario. Okay, thus we can turn the high complexity spectrum allocation problem to a spectrum APA recommendation. Okay, so because the characteristic of the spectrum may limit the range of communication scenario. Okay, so spectral allocation based on this recommendation mechanism may perform better in quality of the experience. Okay, here's a real-time spectrum bidding. Okay, it's based on the concept of real-time bidding system. It's a very popular trading system for internet ads. Okay, similarly speaking, mobile network operator require the spectrum APA resource to offer the mobile service. They are at the demand side and needed to bid on the APAs. Also, they may reserve the APAs for a day or week, depending on the traffic pattern of the and on the supply side is the spectrum stakeholder. It includes spectrum owner and the holder. Okay, they publish the APA inventory to spectrum exchange and develop a pricing strategy for each APA. Okay, and so the bidding process is in spectrum exchange. The bidding process can be based on the spectrum recommendation for matching the best APA and pricing the APA. Here is an example of the RTSP. In the initial offer process, spectrum stakeholder distributed the APA inventory to spectrum exchange, and spectrum exchange also published the pre-computed hex grid to mobile network operators. Okay. And the APA inventory is a list APA tuples as shown in the figure above. So the heads grid contain all available airport inventories published by all Spectrum stakeholders. Okay. And here's next is when the intelligent user equivalent is a mobile phone, maybe it's a mobile phone contact with the base station by the paging operation. The spectrum vector is also updated to the mobile network operators with the paging operator. Paging operation. When the bidding process is triggering, mobile network operator send the bid request based on the spectrum vector of the mobile device. The detail of the bidding operation, please refer to our paper. Okay. Here we list the direction and challenge involved in this work. We are working on the protocol level design of the new mobile network architecture, as well as the control and data plan of the real-time spectrum bidding network. Spectrum bidding market. And the spectrum recommendation model require the training data set of communication scenario. The data needed to be labeled with the spectrum usage and possible communication scenario. However, the data set is not easy to obtain without a carrier support. Currently, we apply the user mobility dataset to simulate the communication scenario, and the incremental deployment topic is also important for the new network structure, network architecture in the current state. In the current mobile ecosystem, it's not easy to deploy a new system. Okay, maybe it's impossible to deploy a new system. So how to deploy a new system incrementally is very important, and how to encourage the existing player to move on the next game is also a big challenge. And transparency is another challenge. That is it's similar to the DHCP service sharing IP address without configuration. Okay, and how to provide a deep serve in this new mobile network is also an interesting problem. Based on our new mobile network architecture, the emergency device can be assigned a higher priority for spectrum bidding. Okay. Those topics should be studied in future, and also a lot of problem and challenge we don't mention, but it should be addressed in further studies. Okay, we summarize our presentation and some takeaway point. And a number in intelligent mobile network architecture is proposed in this work, and its goal is to try to make a fundamental change in how people buy and sell the spectrum resource. 5 roles are defined in this new architecture of cellular network. We introduced 3 new roles: a spectrum holder and spectrum trader, and intelligent UE. Okay. We assume that the intelligent UE with the ability to present the description of the communication scenario to spectrum vector. Here is the descriptor of the communication scenario. Also can can be collected in a base station. Okay, we also introduced two ideas: spectrum recommendation and real-time spectrum bidding market. Based on a new serial network architecture, it's a small carrier can deploy their wireless info without worrying about spectrum license fees. Okay, by benefit from the sharing economy thinking, the hardware info and the spectrum all can be shared. Okay. Thank you. Is my any question?
Okay, thanks, Chiren, for the talk. So any question from the audience? Okay, so since there's no questions and we are a bit over time, let's move on to the next talk. So whoever has questions with Chiren, could you follow with him offline?
Thank you.
Okay. Okay, our next speaker is Yuxi. Yuxi has received his bachelor's degree from Hebei University of Technology of China in 2020. He's currently a master's student in the School of Electronic Science and Technology, Southern University of Technology, China. And he is interning at Pengcheng Laboratory and conducting research on packet classification algorithms. His research interests include software-defined networks and network algorithms. Okay, please start.
Okay, sorry. Okay, can you hear me?
Yes, I can.
Okay, can you see the slide?
Yes.
Okay, let's begin. Good afternoon. It's my pleasure to present our work Hyper TSS and this conference. Our work is a packet classification algorithm which uses the recursive scheme to make cross-grain tuples to fine-grain tuples. Here is the outline. I will introduce our work in the following captures. First is the background and our motivation, and the second is the details of Hyper TSS. Then is the experimental evaluation. And finally, I will conclude the Hyper TSS and introduce our future work. First, let's review some related works. The first is OpenWay switch. Recently years, OpenWay switch based on OpenFlow is more and more widely used and become a general network solution for virtual machines, containers, and other virtual platform. And this is the structure of OpenWay switch. When received a packet, it will first match in the fast path. If not hit, OpenWay switch will report to control plan and search in the slow path, and then insert the route into the fast path catch table. This is a detail of OpenWay switch, three-level flow table. The fast path includes two catch table, exactly match catch and mega flow catch. And the slow path is the open flow table. Packet classification plays an important role in OpenWay switch and used in mega flow and open flow table. And it's one of the key models that affects the performance of OpenWay switch. Next, let's give a brief introduction to the packet classification problem. Packet classification is a multi-dimension match action problem. We have a rule set which contains many rules with priority and corresponding actions. When receive a packet, we need to query the matching rules and return the action. And this question can be transformed into a point location problem in multi-dimension space, like shown in the right. Each rule can be transformed into a hypercube in the space, and each packet can see as a dot. For example, we can map the packet PI into the red dot in the space, and we find the packet match the root 5 and root 6. We select the root with the highest priority, that is root 5, and return the action 5. The mean evaluation indicators of packet classification algorithm are as follows, such as throughput, memory access, memory consumption, and so on. And with the development of software-defined network, whether to support real-time update has also become important. Packet classification is a very classic problem which has been widely studied for more than 20 years. Generally speaking, this algorithm can be categorized broadly into 4 major approaches, as shown in the famous picture given by Dr. Taylor. And is exhaustive search, decomposition, design tree, tuple space, in order to support real-time update of rules. OpenWSwitch adopt tuple space scheme for its packet classification. And next, we will give a review with the tuple space search. The tuple space search algorithm builds a tuple space based on the prefix length of each generation according to the rules. And for rules within the same tuple space search uses Kuko hash to look up rules. And the tuple merge is the state-of-art tuple space search algorithm. Tuple merge first builds cross-grained tuples. When the number of hash collisions increases to the threshold, the current tuple will be split into 2 tuples when querying. Both two algorithms need to traverse each tuple and query whether there is a matching rule in the current tuple. Compared to tuple space search, tuple merge improves the lookup throughput by reducing the number of tuples. The two algorithm has common weakness. They still have too many tuples and need to do many hashes. And in the tuple space search, the packet is hashed once in each tuple. And when we query more tuples, the lookup throughput will be very poor. Tuple merge effectively reduces the number of tuples and achieve a high performance in lookup. So our motivation is to further reduce the number of tuples. This will lead to 2 difficulties. The first is how to reduce the number of tuples. And the second difficulty is when reduce the number of tuples, each tuple will contain more rules. This situation will lead to more hash clues in each tuple. And how to reduce the hash inclusions is the second difficult for us. For the first difficult, we build a top-down models with reinforcement learning, and for the second difficult, we use recursive hash stretch to convert more cross-grained tuples to fine-grained tuples. The following characters will mainly focus on the above 2 parts. This is a framework of hybrid TSS. Our key idea is to avoid tuple exclusion in orange tuple space search by recursively partitioning rules into multi-layer tuples from top to bottom. And thanks to reinforcement learning, we have an efficient solution for construction tuples. And next, we will introduce the details of hybrid TSS. At the beginning, we should give the definition of the terminal node and non-terminal node. We set a very small value as bits. When the number of rules is more than bits, we call the node as non-terminal node. And in non-terminal node, we can use the reinforcement learning module to get next action with in the next generation, or use the tuple space search to build fine-grained tuples. And when the number of rules is no more than bins, we call the node as terminal node. In terminal node, we use the linear search function. Generally, non-terminal leaf node will consume more memory, and usually means that there maybe exist more fine-grained partitions of our reinforcement learning model. So our target is to construct more terminal leaf node and eliminate non-terminal leaf node as much as possible. RL framework is shown as below. We use reinforcement learning to partition cross-grained tuples to build fine-grained tuples. We take the non-terminal node as the next step and use the reinforcement learning module to build more fine-grained tuples. The challenge of hybrid TSS are as follows. If we use the whole root site as the observation space or all dimensions as the action space, that is too large to train. So how to define the observation and the action space is the first challenge. The second challenge is how to define an effective reward. Reinforcement RL is very intelligent. It's a very intelligent model which can easily find the defects with the reward site when the reward site is not appropriate. So our reward needs to effectively evaluate the performance with the entire model. And the next challenge is how to reduce the hash occlusions in cross-grained tuples. Usually the cross-grained tuple contains more rules and the probability of hash occlusions is higher. We should reduce the number of hash occlusions. Yeah, and for the first challenge, we should define the observation space and the action space. However, if we use the whole root site is too large to train in RL model with the probability of each root belongs to a unique tuple space, and each tuple space corresponding to a unique root site. We can use the tuple space to represent the observation space. Observation state. Also, we can use dynamic programming to accelerate the in training process. We also can't directly use the whole space as the action space. For IPv4 type rules, the whole action can reach 104 options. So we the constructions that each level can only select actions in a couple of dimensions. We can see the following example. In the state S0, we can use 0, 0, 0, 0 to represent the observation space, which means the prefix of the roots in this tuple is longer than 0. That's the whole root site. After RL model, the entire root site is splitting into 4 cross-grained tuples. For the non-terminal nodes, we select them as the next state and do the next action. Select the appropriate reward is the second challenge in hybrid TSS. As we mentioned before, all non-terminal leaf node means that there may be more fine-grained partitions. So our goal is to reduce the non-terminal leaf nodes as much as possible. However, RL agents are always smart enough and they will put more rules into field non-terminal leaf node. That's not the result we wanted. So we use the inverse of the sum of the rules in non-terminal leaf nodes as reward. Okay, for example, the orange node represents the non-terminal node and the green represents the terminal node. After reinforcement learning, the root site 7 is one of the non-terminal leaf node in all leaf nodes. So we take the inverse of the number of roots in root site 7 as reward. And then we use Bayerman expectation equations to update our Q table. And we reduce the hash occlusions in cross-grained tuples by construction tuple space search rescuely. Since we generate cross-grained tuples with more rules at each layer, they will lead to increase the hash occlusions. For example, after action, for all rules in R1. The prefix length in the first dimension is longer than x1, and the prefix length in the second dimension is longer than y1. So we use the feature. So we use this feature as the hash key value. Through this method, hash collisions are effectively reduced. Then for the non-terminal node, we see them as the next state, and then use RL model to get the next action. Okay, this is an example of hybrid TSS. The root is in the left corner. After first reinforcement learning, hybrid TSS generate 4 cross-grained tuples. We can say there are many collisions in cross-grained tuples. Then we use the unique prefix length as the hash key to get many entries in each subset. We can say most of them are already terminal node, and for the non-terminal node like entry 3 in the subset 2, we need to do the next round process. And we after RL model, we construct 2 tuples and then hash them. This will come to the final state. And in the finally, we can say there are 2 non-terminal leaf nodes with total 4 roots, the root 9, root 10, root 11, and root 12. So the reward of this epoch is -4. Okay, the next factor is the experimental evaluation. Our rule set is generated by class bench with the rule size varies from 1,000 to 100,000. There are 3 types of rule set: access control list, the firewall, and the IP chain. We generate for total 36 rule sets. In terms of lookup performance, our comparison algorithm chose PSTSS, which uses the open vSwitch, and the top merge, the state of the art tuple space search algorithm. The CutPSS, also the state of the art design tree algorithm, and the neural match, which also has excellent lookup performance. Due to the neural match don't support update well, we select the PSTSS, the tuple merge, and the CutPSS as the constructor algorithm in update performance. And our experiment configuration is shown as the slide. Okay, this figure shows the average classification time of one packet on 3 types of rule set with different size. And the red line represents the hybrid TSS. We can see that the hybrid TSS has the lowest time consumption under most rule set, especially hybrid TSS achieve 7.78, 10.09, and 8.03, better than PSTS under 3 types of rule set. Also, hybrid TSS achieve 1.92 and 1.54, 1.82 and 1.81 speed up compared to CutTS tuple merge, and the neural match with the tuple merge, and the neural match with the cut delete. This figure shows the average update time of one rule on 3 types of rule set with different size. Hybrid TSS achieve 0.96, 1.45, 1.44 speed up compared to PSTSS, CutTSS, and tuple merge. This means that hybrid TSS has almost the best update performance in packet classification elsewhere. Okay, let's have a summary. HyperTSS adopt IL method to build a small number of cross-grained tuples and use recursive tuple space search effectively reduce the hash occlusions in cross-grained tuples. And finally, HyperTSS achieve throughput and fast updates. And for the future work, we may adopt new machine learning or reinforcement learning approaches for global balanced tuple partitioning, and combine the packet classification with flow table and integrated open-way switch and offload to FPGA. Okay, that's all my presentation.
Okay, thank you, Xin, for the nice presentation. Okay, I see we have a question from the audience. Could you open up your mic and just ask the question? Could you go ahead to ask your question? Yes. Yeah. I see one audience raise up the hand. Could you unmute yourself and ask the question?
What?
Hello?
I'm here.
Hello.
Yeah,
you.
please ask.
I want to know how to install rules. I know OpenFlow is widely used in SDN network, but you didn't mention the controller. Could you explain how to install the rules?
Do you mean install the rules into the open-way switch or into the HyperTSS?
OpenFlow.
Yeah, I know.
Is there a controller in your program?
Our program is just a soft-based algorithm and for test the lookup performance. Yeah, and there is not the in the entire system. So we don't have the control plan, and for our future work, we will we may integrate to the open-way switch yeah.
How to install the rules?
How to here is an example of HyperTSS installed IPv4 type rules, and our paper is how to install.
Yeah, so Yushin, I guess he asked how to install the rules. Could you briefly describe that?
Can I use the example of the IPv4 rules? I know there may be some difference with IPv4, some difference between the IPv4 and OpenFlow. This case is an example of install the IPv4 rules.
Okay, thank you.
Okay, so if you have other questions, could you email Yushin? Yeah. Okay, let's move on to our next talk. Thanks, Yuxin. Okay, our next talk will be given by two speakers, Yashash Andaruli and Sayan Day. They are both master students in the Department of Computer Science and Engineering at Indian Institute of Technology, Hyderabad. And during their studies, Yashish has worked on compiler technologies for networks and program representation and machine learning. And science research interests includes the compiler optimizations and interaction of compilers and networks. Could you share your screen? Hello? You see, could you stop sharing? Yes, okay. Yashash and Sayan, you can share your screen now.
Hello, Yashish is not able to unmute. Can you please check this?
Okay, I'll unmute him. Let's see. Okay. Oh, sorry. Okay, I think you are ready. Please get started. Oh, and Sayan. Okay.
Hello. Hello.
Yes, we can hear you.
I'm Yashish. So I will be presenting along with Sayan or work on packet processing algorithm modification using program embeddings. So there has been a consistent growth in data rates in high-speed networks. This has led to an increasing gap between general-purpose CPUs and the packet processing speeds of such CPUs and the network speeds. So SmartNICs are a recently emerging alternative which provide programmability along with high-speed packet processing. So in a situation where we have a fixed function NIC, there is a high load on CPU as most of packet processing is done by the CPU. Whereas a SmartNIC is programmable and provides more features. This reduces load on the CPU and the packet communication. So in the following slides, we'll go over some of the features of SmartNIC. So SmartNICs provide several generic cores for packet processing that is specified by a network function program. And offloading a program to a SmartNIC and using such generic cores leads to significant performance improvements such as latency, throughput, and power. So iPipe is one such work which showed that using IPsec program, they achieved 22.9 Gbps on a 25 GB SmartNIC. So SmartNICs also provide hardware logic called accelerators for frequently used operations and algorithms such as hashing and cryptography. These accelerators provide even lower latency and higher throughput than generic cores. So the goal is to offload NF programs from general purpose CPUs to SmartNICs. So these are some of the SmartNIC models and algorithms for which accelerators are supported on the SmartNIC. For example, the Metronome SmartNIC supports hashing algorithms, encryption algorithms such as AES RSA, and IPsec algorithms and truncated prefix match algorithms. Whereas the KVM SmartNIC supports only IPsec. Here are some network function programs and the algorithms they use. So the L3 router uses the hashing algorithm and LPM algorithm, whereas the VPN gateway uses hashing, AES, RSA, and IPsec. So we want to port such diverse NF programs using various algorithms to the varying SmartNICs with varying accelerator support. So in order to port and map a network function program to a SmartNIC, we want to identify the regions of code that is suitable for an accelerator. However, the same algorithm can be implemented in multiple ways. This makes it difficult for a developer to identify such an algorithm. Porting also needs manual analysis and multiple rounds of tuning, and this is usually manual, which is a difficult for the developer. The program must be tuned by adding the appropriate SmartNIC accelerator calls. So identifying and mapping the regions of code in network function program is tedious and laborious, and we need to simplify this process. So the problem is to provide a workflow that will simplify this porting process from x86 CPUs to SmartNICs and automatically identify regions in network functions that can be mapped to accelerators. So we approach this as a ML classification problem. We use compiler techniques to help developers to map NF programs to SmartNICs. We use machine learning to identify code regions performing specific tasks, such as an algorithm, and we create a realistic data set of packet processing algorithms. So we choose to use ML because identifying algorithms in a program is an undecidable problem, and ML can help us achieve an approximate identification in a scalable fashion. ML tool can also help us quickly identify accelerators for each function in a program, because manually assigning accelerators for functions in a program is tedious. There's also a large variation of implementations of algorithms, and the SmartNIC architectures are quite diverse. So we face the following two challenges. We need to represent algorithms and programs as an input from machine learning model, and create a dataset that is realistic, diverse, and has a wide range of applicability. So to tackle the first problem, first challenge, we need to represent programs. And to do this, we use LLVM IR, which is the intermediate representation of the LLVM compiler toolchain. So here we show a C function and the corresponding LLVM IR that's compiled from the source. So such a representation expresses a program in assembly-like instructions in a higher level of abstraction, and this is independent of the source language. This framework, along with the LLVM compiler toolchain, allows us to perform analysis and easily obtain the required information about the program. So now we need to represent the program as a mathematical representation for the machine learning model. There are various techniques in use. The first involves correcting features using domain expertise. The second involves treating programs as tokens of natural languages. And the third involves using abstract syntax tree representations. And finally, we have IR-based representations. So for feature-based representations, these are usually manually identified and are specific for a task. And natural language representations are capture only syntactic information. AST representations capture syntactic information and semantic information to an extent, whereas IR-based representations capture syntactic, semantic information and are generalized for any program analysis-based task. So this makes IR-based representations suitable for a problem. So IR2 obtains information from the IR, such as opcodes, types, and arguments, and obtains correlations between them. These are used to obtain representations of such of entities. These are further combined to form instruction representations and function representations and program representations. IRTOIC also encodes information such as useDef information and reaching definition information to capture data flow analysis. This makes IRTOIC also capture semantic information. So we use ML-based techniques to appropriate accelerators on the program and utilize IRTOIC embeddings to encode syntactic and semantic information. And we use ML to predict the accelerator for each function. So given a source code that can be mapped to an accelerator, here we show an AES-CBC encrypt function, which calls the AES encrypt function. And we compile this to LVM-IR. So this is translated to a call instruction. We obtain the data structures from LVM-IR, such as the call graph, and pass this to the IRTOIC module. This gives us the representations of different functions. As also the caller representation includes the representation of a callee function. These are passed to the ML classifier for training. However, we need a suitable dataset for training such a classifier. So challenge 2, which involves generating a suitable dataset, will be presented by Sayan.
Hello, everyone. So we know that for training any ML classification model, we need a suitable dataset. But our earlier works on this domain, like Clara, had only around 7,500 programs, which are clearly not enough for training the ML models. Like we can see that the famous ML datasets like ImageNet contains 14 million images. Coco contains around 330,000 images, but Clara had very few number of programs. So to solve this challenge, we had one way, that is writing all the programs manually for different algorithms, but that was a very hectic process. So instead of going through that way, we created our custom dataset for the MF programs. And in the further slides, we'll be describing how we created our dataset in a proper, well-fashioned manner. Okay, so to start with, we started collecting programs of various encryption algorithms like AES, DES, and RSA. So for these programs, we considered some open source libraries like OpenSSL, CryptoPP, Botan, Natal, Wolfscript, Embed TLS, etc. And not only that, we also considered different modes of such algorithms like CFP, CTR, ECB, etc. Now, to start with, we only collected the encryption and decryption functions of these algorithms. And regarding the classification purpose, what we did was we have not classified based upon the library or the modes. So suppose we are considering AES, then whether it is of OpenSSL library or Botan library, or whether it is implemented in CFP mode or ECB mode, whatever, it is considered to be of the same class, AES. So here only 3 classes are considered, as you can see in the left. So after putting so much effort also, we were only able to gather only 121 programs, so which is really not sufficient for training any ML model. So we had to extend this dataset. In the further slides, we will discuss how we extended our dataset. Okay. Yeah. So we used our custom approach of compiler transformations to expand our dataset. So after applying the compiler transformation process, we got a diverse dataset. By diverse, I mean the code size of the program also changed, as well as the performance characteristics of the code changed, like latency, throughput, power usage also changed. But at the same time, we made sure that the semantics of the original codes were preserved. That is, the functionality is not changing. So in this way, we got sufficient data for training any ML models. Okay, so in this slide, we will be discussing the actual implementation details of our compiler transformation process. So as you can see here, it is LLVM IR representation of a AES encrypt function. Okay, so what we did is we applied permutations of different compiler passes. We actually considered 100 compiler transformation passes, and we combine them to form 300 permutations. By compiler transformation passes, I mean dead code elimination, constant propagation, loop unrolling, loop simplify, inst combine, etc. Okay. So now each of the permutations of the transformation passes resulted in a sequence. Okay. And each of the sequence of the passes, by sequence I am meaning the permutations only. So each of the sequence of the passes are actually giving us one program point. So we applied 300 permutations. So we got 300 programs. And not only that, we also applied some standard optimization sequences that are provided by the LLVM toolchain. So these are O1, O2, O3, OS, and OZ. So what are these? Like each of these optimization sequences again contains some individual transformation passes. Like O3 itself contains 102 transformation passes embedded within itself. So we again applied these sequences. So total 300 plus 5, 305 equivalent programs we got from one single program point. So finally, from 121 functions that we shown in the previous slide, we got 37,000 program points, like 121 into 305. 37,000 program points were received by us. And this number is sufficient for training any ML models for the classification purpose. Okay. So now in this slide, we'll be discussing about our experimentation, and also we'll brief about how we implemented. So our goal was actually classified into two types. First one was the detection of CRC and non-CRC programs. For this, we used Clara's dataset, but the fact is that Clara's dataset was a bit skewed. Means it had only around 56 CRC programs, but few thousands non-CRC programs. So to remove the skewedness from the dataset, we again applied compiler transformation passes on their CRC programs to make a balance between CRC and non-CRC programs. And coming to the second goal, it was actually a superset of the first goal only. Here we classified 5 classes: CRC, AES, DES or triple DES, RSA, and non-network function programs. So for this experimentation, we used our custom dataset, and the dataset generation process is already discussed in the last 2 slides. Okay. Then coming to the implementation details, what we did was we generated the LLVM IR files from each of the libraries, and then link those LLVM IR files into a single LLVM IR file. So for each library, like OpenSSL, we got a single LLVM IR file. Like this, we continued, and then we used IR2vec to get the vector representation of the LLVM IR. So the LLVM IR version that we used is 12.0. And finally, we got the vector representations and fed that representations to the ML models, and we did our classification task. And finally, we compared our results, like the precision, accuracy, recall, and inference score of our ML model with the approach followed by Clara. The comparison of our approach and Clara's approach will be discussed in the further slides. Okay. So here we can see the precision. So we used 6 ML models. You can see in the left: gradient boosted decision tree, multilayer perceptron, SVM, KNN, and AutoML. So here the first 2 columns are showing the comparison of our approach and Clara's approach for CRC. That is the binary classification one. And the next 2 columns are showing the comparison of Clara's approach and our approach, that is the APNet approach, for the multi-class classification problem. So as we can see, for all the ML models, our approach is having better values. Only for gradient boosted decision tree, Clara is having slightly better value. Okay. Now coming to recall, also same thing. All the ML models are having better performance for our IR2vec based approach, as you can see in both the columns. Yeah. Now coming to F1 score, which is a very important measure for seeing the predictivity of a model. Here also, our IR2vec approach is having better numbers than the Clara's approach. So the reason for such difference in numbers is that Clara used an encoding technique which only extracts the opcode information of program, and also they are using the old version of LLVM toolchain. But what we did was we used IR2vec approach, which captures both the syntax and semantics of the program, like the usedef, the flow equations, the reaching definitions. All these features of a program is captured by IR2vec. That's why I think our approach was giving better results than the Clara's approach. Okay. Now coming to summary and future work, our contributions in the networking field and our future plan will be discussed by Yashish.
To summarize, So we are using embedding techniques such as APNet to represent programs from networking domain. We model algorithm identification problem with a scalable machine learning approach and collected a realistic data set and generated semantically equivalent programs. So we plan to extend this work by applying it to real-world network functions and identifying other algorithms in such programs. So these are the others. So Venkat, Yashas, Sayan, and Professors Rinku, Praveen, and Ramakrishna. Thank you. We are open to questions.
Okay, thank you, Sayan and Yashash. Any questions from the audience? If not, let me ask a question. So very interesting work. I see the point of using machine learning technologies to identify the program to be offloaded, but seems you haven't touched like after you identify what program can be offloaded, how is it converted to the code to be like runnable on the SmartNICs? So could you briefly give us some intro to that? Is it automatic based on some compiler technologies, or programmers need to manually reprogram it on the SmartNIC?
Yes, so the current work involves only identifying regions of code that may be mapped to accelerators on a SmartNIC. However, we could use compiler techniques to map to a SmartNIC. So that for now, we are only identifying regions in the program.
Yeah, so that's a very valid question. So as of now, we are just identifying, but what you said is our plan for future work.
Okay, okay, thank you. Any other questions? Okay, if not, then let's conclude the session. Let's thank all our speakers for the nice talks. And next, I think we will start the poster session, and Bill will chair the session. So Bill, the floor is yours.
Okay, thank you. Thank you, ET. Okay, now let's begin the poster session in 25 in 3 minutes later. Now the presenters can test their screen. Yulong, you can share your screen now. Okay, can you speak? Can you turn on your microphone? I cannot hear you.
Can you hear me, sir?
Okay, okay. That's
Okay,
good.
okay. Thank you, thank you.
Okay, that's good.
Okay.
Let's test all the presenters screen first. So we will begin in 5:25.
Can I begin now?
In 2 minutes, okay? In 2
Okay,
minutes.
okay.
Okay. I can see all the presenters are here.
Okay, I think we can start now. Good afternoon, everyone. Welcome to the poster section. It's the last section of this year's APNet. And my name is Biao Han. I'm from the National University of Defense Technology. And I'm also the poster section chair. The first poster is, the title of this poster is RLCS, a classification system based on random forest and logistic regression for hybrid zero-day traffic. And the presenter is Yulong Liang. Yulong received a bachelor degree in information security from Harbin Institute of Technology in 2020. He is currently working towards the master degree in computer science and technology, National University of Defense Technology, and his research interest mainly focuses on network security and traffic identification. Okay, Yulong, please share your screen and begin the presentation.
Okay, thank you, sir. Thank you. Okay. Good afternoon, everyone. I'm Yulong Liang from National University of Defense Technology. It's my pleasure to be here with you today. To begin with, I plan to say a few words about zero-day traffic. It's the network traffic generated by previously unknown applications. In other words, the application set of the training for a classification system is a subset of it in real network. And it's the essential reason why machine learning-based methods are difficult to apply to real networks. So the subject of my talk is RLCS, which is a novel traffic classification system to tackle the problem. Let's break down its classification process into two tasks. The first task is zero-day traffic detection, which aims to map the test flow into two generic classes, known and unknown. The second task is application traffic classification, which classifies traffic just to be known into specific applications. Identifying specific applications in unknown traffic is not our concern. Okay, first of all, we need to perform filter extraction on the raw flows to construct input-ready vectors. In our experiment, we extracted filters through CSC flow meter, which is developed by Canada Institute of Cybersecurity. This page lists all the filters we need. Now let's move to the construction of our system. It's an ensemble system with a double-layer structure. The lower layer comprises two random forests, with the upper layer composed of two logistic regression modes. For brevity, the following describes the construction of the first pair of the random forest and the logistic regression mode. I call them RF1 and LR1. To begin with, we divide the train dataset into two groups, Group 1 and Group 2, each contain traffic of half applications. Next, we randomly select a portion of the traffic in Group 1 to train the RF1. Thirdly, we construct the positive and negative sets for subsequent training. Samples in the positive set come from Group 1, and samples in the negative set come from Group 2. Why we do this? As we can see, negative set has totally different applications from the train set of RF1. We need it to simulate the zero-day traffic. Afterward, we input all samples in the positive and negative sets into RF1 and obtain the corresponding probability vectors. Probability vector denotes the probabilities that the flow belongs to each application in corresponding group. Okay, we have demonstrated that the probability vector of a random forest is predictive of whether a sample belongs to known classes experimentally. Okay, then we replace each sample in the positive and negative sets using the maximum of the elements in the corresponding probability vector. we can see how to calculate the maximal MO from this page. Finally, we construct a binary classification mode, LR1, using the changed positive and negative sets. It can help us determine whether a test flow belongs to group 1. Okay, in the second part, I will talk about how to use it to perform traffic classification task. The process is not complicated. For brevity, we assume that there is no flow F to be tested. After filter extraction, we input F into RF1 and RF2 and get two probability vectors, respectively. Secondly, input the maximal element of probability vector into the corresponding logistic regression mode. The two LR are binary classification modes, which can help us determine whether a test flow belongs to the corresponding group. So we merge their outputs. If there is no positive label in outputs, we will label F with unknown. If there is at least one positive, we will label F with application which corresponds to the largest probability. There are three cases in this page. For a simple case, if only LR1 outputs a positive label, F is judged to belong to an application in the group 1. So we just need to follow the classification result of RF1 in this case. Okay, in the last part, I will briefly present the results of the evaluation. I have listed the dataset, the simulated experimental environment, and the metric on this page. Furthermore, we define the N1 occurrence as the occurrence of the N1 class classification task, which maps the test flow into one unknown generic class and all the known specific classes. No traffic and information from zero-digit applications will be allowed to participate in any training phase. The first figure shows that no matter how much the number of applications increases, TPR maintains more than 0.9, and the FPR maintains less than 0.1. Moreover, N1 occurrence maintains more than 0.9, and we can always keep more than 0.9 occurrence in determining whether a flow belongs to a known application. The conventional random forest is employed as a comparison in experiment 2. As we can see in the second figure, regardless of the change in the environment, our system can be applied very well and always maintain a high level of occurrence. In contrast, the random forest has extremely poor applicability when the rate of zero-day traffic is too large. Okay, that's all I want to say today. Thank you for taking time out to listen to my presentation. Thank you.
Okay, thank you, Yulong.
Thank you, sir.
Is there any questions from the audience? You can raise your hand or just type on the chat. If no, let me ask a quick question. How about the time efficiency of your proposed classification system? As you don't mentioned, could you explain a little bit about the time efficiency?
For the training, it costs a little more time, but we chose the logic regression mode as the observer mode because it is a let me see, because it is a lightweight and fast mode, so we chose it as the observer mode. So I think its time efficient is not a problem.
Okay. Okay, thank you, Yulong.
Thank you, sir.
Okay, now let's move to the next poster. Renyi, Are you here? Okay, good. Can you speak? Unmute your microphone. Please turn on your microphone and your video. I think Yulong, you have to stop sharing your screen. And Renyi, can you share your video?
Now can you hear me now?
Yes. Can you share your video?
Sorry, I don't have camera on my computer.
Oh, okay, okay. Okay, now let's start. The second poster, the title is Efficient Partial Reduce Across Clouds. The presenter is Renyi Wang. Renyi is currently pursuing the master's degree with the School of Computing and Artificial Intelligence in Southwest Jiao Tong University. And his research interests include data center networks and machine learning. Okay, Renyi, let's begin.
Okay. Good afternoon, everyone. I'm Renyi from Southwest Jiao Tong University. It's my honor to attend this conference and present our poster, which is named Efficient Partial Reduce Clouds. This work is co-authored with Ruoshouxi, Li Ke, and Xinhuan Lai. First, let me introduce the background of our work. Geo-distributed machine learning system attracted more and more attention and have become an essential infrastructure for large-scale artificial intelligence service. In these systems, recent studies show that performing model synchronization across wide area network could dominate the time cost of the entire training. Generally speaking, there are two approaches for model synchronization, which are all reduce and partial reduce respectively. Partial reduce is a recent proposed variant of all reduce, and by allowing P out of N workers to conduct all reduce operations, partial reduce is able to ease the impact of struggles, thus permitting for data parallel distributed training in heterogeneous network. However, due to the three features of the wild area network, the process of model synchronization can be very inefficient. First, the bandwidths across data center are scarce and expensive and growing at a slow pace. Second, the network performance mainly determined by geography distance, which means that the bandwidth of different links can vary a lot, possibly by several times. Third, there are always spare links when performing model synchronization, which gives us room for communication optimization. Based on these observations, our goal is to achieve efficient partial reduce for geo-distributed machine learning over heterogeneous wide area networks. In our work, we propose full mesh reduce. We call it FM reduce for short, a flexible and efficient partial reduce implementation to pursue our goal. The novelties of FM reduce are threefold. As its core idea, it leverages all the available workers to conduct the operations needed by a partial reduce. Then, to make the most usage of the available bandwidth, it provides network-aware communication for model synchronization. And to further speed up the synchronization, if designed, FM reduce allows the worker to scatter the updated model immediately, making the spare wide area network get better usage. And this is a three-phase workflow of FM reduce. First, when a worker completes its local training, it splits its model parameters into non-overlapping blocks, respecting the available bandwidth, which corresponds to network aware. Then these blocks will scatter to all other workers. On getting these blocks, the receiving worker would catch them to conduct aggregation for some certain blocks. And at the last, the aggregated result will be broadcast back to the workers who send these blocks. During our design, we still come from 3 challenges. The first is how to split the model in a network-aware way. We model the time cost of scatter and broadcast as these 2 equations. By splitting the model appropriately, we can minimize the time cost of we could minimize the sum of the time cost of scatter and broadcast. Fortunately, this is a linear programming problem, and we can solve it by using virtual linear programming package. And the second challenge is how to guarantee consistent partial reduce. This is used to determine which p-works are involved in a round of synchronization. FM reduce both blocking model and non-blocking model. In blocking model, before model synchronization, the system have to wait until P workers have completed their local training. So we can maintain a ready queue to record the worker training status. And in non-blocking model, any worker once finished its local training, it can immediately send its model blocks. To this end, FM reduce lets the worker with the smallest ID to check its receiving buffer and decide which P workers are involved, calling the first P block it receives. And the third challenge is how to guarantee concurrent transfer. Sometimes follows triggered by a new scatter might compete with follows belonging to a previous ongoing broadcast on some links. It's obvious that in such a scenario, the default max-min fairness is suboptimal for the bandwidth allocation. And instead, the principle of first come, first service is a simple yet efficient design. And in our implementation, FM reduce embodies these 4 alternative designs into partial reduce. And to verify the performance of FM reduce, we have conducted simulation experience and assess them by the number of training runs in a fixed period of time. As shown in figure 2, when other conditions keep the same, network aware and first come first service scheme can always efficiently increase the training runs compared to evenly divide and fairness. Regarding blocking and non-blocking, non-blocking can always perform better than blocking unless the model splitting scheme is network aware. This is because the computation of P workers can be known on the blocking model, which help to calculate a more process model splitting result. However, if P is equal to N exactly, the computation of P workers can be known in advance. So the non-blocking model can reduce the waiting time without any cost, and we believe that non-blocking model will outperform than blocking model. And most importantly, by employing all the N workers to conduct each partial reduce, FM reduce could achieve an effective speed up for model synchronization. As for future work, we are going to take the connection failures into account since they are common in wide area networks. And we would like to carry out real machine learning training with our FM reduce and carry out experiments in the real world wide area scenarios. Okay, that's all my presentation. Thank you for your listening.
Thank you, Yi. Is there any questions? Okay, I have a question. Because you in your method involves all workers, right? So yes. So how to ensure the fault tolerance? I mean, in particular, in the WAN scenarios, the connection failures are very common. So how to ensure fault tolerance in your method?
Okay. This is our future work, and for simply we are going to if there is a failure in on some link, we will change the we will change the route of the transmission, and to find some available link to extend the links which are in the filials.
Okay. Thank you, Ren Yi. Now we can turn to the next poster. Xue, are you here? Okay, you can unmute your microphone and share your screen.
Okay, can you see my screen?
Yes, okay, very good. So let me introduce our next poster. The title is Approximate Gradient Synchronization with AQGB. And the presenter is Xue Liu. Xue is a first-year graduate student in software engineering in Southwest Jiao Tong University. His research mainly focuses on optimization of distributed machine learning systems, especially in network communication, so as to solve the problems faced by large-scale distributed systems in the internetworking. So, Xue, please start.
Okay. Dear audience, my name is Liu Xue, and I am a first-year graduate student at Southwest Jiao Tong University. It's a pleasure for me to attend the conference, and I am back here to present our recent work in a poster session. So the title of my presentation is Approximate Gradient Synchronization with AQGB. Let's begin the introduction section. Recent studies have shown that in large-scale distributed deep learning, the communication tracked by the model synchronization could dominate the entire training, becoming the system bottleneck. Such a problem is getting more serious as large models are getting popular. To deal with this, numerous optimization designs, including data compression and pipeline, are proposed to maximize the overlap between the communication and the computation. The pipeline and the gradient compression is simplified as shown in this figure. This is obverse. Among them, gradient correlation is promising and widely employed by transmitting quantized at-arrow compensated gradients rather than raw values. It can reduce the traffic loss markedly. However, as a losing compression technique, gradients correlation has a possible cost of reduced model accuracy or increase the runs to coverages in large-scale shared cluster, because various distributed applications are likely to coexist. The available bandwidth transfer to the use is time varying. Accordingly, the perfect quantization scheme should have the ability to adapt its life of compression respecting the network. Unfortunately, to the best of our knowledge, none of existing schemes have supported this, as they all adopt fixed and inflexible quantization designs. In this paper, we propose the design of network-aware adaptive gradient correlation, based on which we further design AQGB. This adaptive quantized gradient broadcast to achieve approximate gradient synchronization for distributed training efficiently. Next, let us move to the detailed design as shown in this figure. AQGB have two goals that need to be addressed, one of which is design a hierarchical correlation scheme, and another is how to decide when to use which correlation ratio. Phase of Pro 1. Inconsiderably that greatest in deep learning are generally float 32 values. In the past, 32 bits were compressed into a fixed number of bits, usually using a mapping such as QSDD. Our AQGB designs an efficient multi-live coordination scheme based on specific layout of FP32 used in computer. We reduced the multiple bits to achieve coordination on demand for its initial multi-live coordination. For example, let's look at this figure. When the worker has no pair communication bottlenecks, it will transfer the four 32 bits float point number in 4, just as this QF. When the communication bottlenecks is significant, workers will drop the sum of tissue bits of the float point number to different degrees, like this QE dropped 4 bits, or QD dropped 8 bits. And the worst case, QA will drop 20 bits of tissue bits. We can achieve fine-grained compression ratio with a mix of these 6 coordination before we put the data into the packets. And in spirit Tengri, the last bit after coordination is +1, according to the specific problem. And for the goal 2, we use the example to briefly show how to adaptively adjust the degree of coordination to cover communication bottlenecks. And time T0 is the time when the back propagation of the work starts. In short, BP starts at time 0. The greetings from the 4 blocks will be fully generated in time T1, T2, T3, or and T4. At time T1, current accumulated unseen data is gradients G1. This G1. We think the base center rate is K1 at the time T2 moment. When the G2 arrives, G1 will finish the transmitting, but the actual broadcast ratio is only K2. And so K2 and the K2 is determined by the network. So current worker should use the coordination ratio of K2 divided by K1. The worker want to the level of GI to complete before GI plus 1 become available, and the level of the final block GM to complete before the deadline of TM plus 1. Then the results of our preliminary simulation shows that our design can dynamically change this compression ratio respecting the available bandwidth. When bandwidth is not enough, use a lower compression ratio to cover communication bottlenecks. As the available bandwidth increases, the coordination ratio gradually increases to perceive accuracy as much as possible, like this. And the percent of communication time overlapped with computation in a round of synchronization will be adaptive, increasing from about 15.1 improved to about 98%. Finally, a brief summary. We have proposed adaptive gradient broadcast scheme to achieve approximate gradient synchronization for peer-to-peer distributed train. When with efficient multi-live coordination design, it can dynamically adjust its life of coordination respecting the network state and trains communication partners, increasing the overlap between the communication and computation for deep distributed learning. That's all my poster presentation. If you have any question, you can look at the paper and the contact us through the email address. Thanks for all your listening.
Okay, thanks, Xue. Due to the time limitation, as there is no audience raise the hands and ask questions, let's directly move to the next poster. If you have any questions, you can contact Xue through the email in his paper. Okay?
Okay.
Thank
okay.
you.
Thanks.
And the next poster comes from Kexun. Kexun, are you here? Please share your screen and unmute your microphone.
Hello, can you hear me?
Yes. Good. Okay. Okay. Now let's begin. The next poster. The title is AOI-aware data propagation in edge computing assisted NR-V2X networks. The presenter is Kexun Chen. Kexun is currently working toward a bachelor degree in computer science with Southwest Jiao Tong University, and his research interests include vehicular networks and intelligent transportation system. Okay, let's begin, Kexun.
Okay. Hello, everyone. My name is Kexun Chen from Southwest Jiao Tong University, and it is my great honor on behalf of other authors to present our poster named AOI-aware data propagation in edge computing assisted NR-V2X networks.
Sorry, Kexun. I think you should enlarge your screen because the picture, the PDF is too small.
How about this?
Okay.
To start with, I'll introduce some background information. With the continuous development of 5G technology, ITS applications in vehicle networks are becoming increasingly diverse. For example, autonomous driving, remote driving. In all these practical applications, QoS requirements such as latency, service reliability are extremely important, which ensures the safety of the vehicle during travel and the experience of the vehicle users. However, all these existing traditional performance metrics fail to indicate the freshness of data. So we introduce a new metric called Age of Information, AOI, as an optimization objective, which is a better indicator of reflecting continuous vehicle state changes than any others. And it is also a critical requirement for real-time safety and driving assistance applications. So what is AOI actually? Age of information is defined as the time elapsed since the generation of the most recently received data updated to assess the information freshness. Most researchers now address the AI-related problems in the static setting. So it is very difficult to apply it in high mobility vehicular network directly. In ITS, there are a lot of disadvantages for traditional broadcast-based data propagation. The most importantly, it tends to cause broadcast storm and severe channel contention, resulting no efficiency of data propagation and large AOI. So the question is that with regards to rapidly changing and large-scale vehicular networks, how to propagate data while maintaining low average AOI and low peak AOI with low computation overhead. Our goal is as below. Hence, with the help of mobile edge computing, we propose a new unicast-based data propagation approach to reduce AOI. To address the AOI-related data propagation problem in edge computing assisted 5G new radio-based vehicular networks. This figure shows an example of the NR V2X system. It consisting of 5G base station GNB networks and a MEC server. The MEC server is located near the network edge and close to the GNB to increase the NR end-to-end V2X communication capabilities and provide large data storage and computing for the GNB. In this scenario, the edge computing server computes and determines vehicle nodes for the purpose of propagating time-sensitive data via V2V communication. This complete operation process of the system has 4 steps. The first step is context sensing. Here we can say vehicle A has contextual information including location and the channel quality of car C, D, B, and for the next step, data transmission and processing. The vehicle A and D and B, they upload their contact information to the edge computing node through the link, and the edge computing node constructs a global topology map based on the context information. The step 3 is scheduling decision. An adaptive data propagation algorithm is run by the edge computing node and computes the initial vehicle nodes and the scheduling decision to propagate data. The scheduling decision is distributed to the vehicle through GNB. Here, this data is sent to C and D. The final step is data propagation. According to the scheduling decision, multiple instances of data propagation take place simultaneously through V2V communication. Here, C communicate with A and D communicate with B and A. And in the step 3, the adaptive data propagation algorithm named ADP is described here. It consists of 2 steps. The first step is emergency level rating. The higher the emergency is, the larger rate the rate is. For example, you can say here the priority 1, it is the largest, so it has the largest rate. And the coverage rate and the graph here with probability edges are the inputs for the next step, named adaptive initial load selection. In this step, firstly, iteratively selecting several loads with the highest connectivity to meet the coverage rate, and repeat this step to get a node. And the last step is to choose the set of nodes with the lowest ALI. And here is the reason why called adaptive. To validate the effectiveness of the proposed ADP algorithm, a system-level simulation was designed based on the MES framework, an event-driven network simulator, APNet++, and a road traffic simulator, SUMO. And here are some simulation parameters. The performance of ADP in PLI and ALI is examined and compared with broadcast, and can be seen from these 2 figures. PLI and ALI for ADP algorithm using the unicast is less than broadcast throughout. In the case of different vehicle nodes, the unicast method is better than the broadcast method under the performance indicator ALI and PLI. In conclusion, the ALI-aware unicast data propagation method shortens the ALI of data propagation promoting guidelines for the design of future vehicle networks. Thank you for listening. That's all.
Okay, thank you, Ke-Xun. Is there any questions? Okay, a quick question. In your simulation, how to calculate the average AOI and the peak AOI?
Just in the simulation, just to simulate that some vehicles are sending messages to others, and you have a time to collect when the message is updated. So you give every message a time label.
Oh, okay. So you use unicast, right? So
yes.
How will the data propagation scheme involve with the dynamic network topology? I mean, the connectivity in V2X networks may be changed very frequently, right?
Yes. So every time you have to run this this algorithm for different maps.
Okay, if the topology change and you have
So
to
you
run,
have to,
you have to run. Okay.
Yes.
I see. Thank you.
Thank you.
Thank you for your answer. And okay, we will turn to the next poster. Ran Zhen, are you here? Ran Zhen, are you here? Please share your screen and unmute your microphone. Okay, I can see your slides. Please turn on your microphone.
Hello, can you hear me?
Yes, good.
Okay.
Okay, the title of the next poster is Memocom, Memory Efficient 100 Gbps Traffic Replay with Sequence Guarantee on Multi-Core Servers. The presenter is Ranzhen Cao. She is a first-year graduate student in the Computer School of Beijing Information Science and Technology University. Her main research interests are in network and information security. Okay, Ranzhen, please start.
Okay, thank you. Thank you for your introduction. And good afternoon, everyone. My name is Ranzhen Cao, and I'm now a first-year graduate student with Beijing Information Science and Technology University. It's happy to be here to attend this conference and present our work, MIMOCO, Memory Efficient 100 Gbps Traffic Replay with Sequence Guarantee on Multi-Core Servers. This is a joint work with my instructor, Dr. Wendy Feng, and he's now an associate professor at BIS2. Okay, network has become the most important. Okay, sorry for that. Network has become the most important infrastructure in today's information society. The trend of network softwareization utilized by 5G and 6G communication networks brings flexibility to network systems, but also introduces complexity, which is hard to be satisfied using the hardware-based traffic generators. Besides, the demand for high-speed packet processing is increasing. Hence, high-performance traffic generator is critical in the development and testing of network systems. For example, identifying performance bottlenecks by generating carefully synthesized packets or traffic to trigger certain conditions. And typically, a traditional traffic generator is provided in the form of a dedicated hardware device, so it's foreseeable expensive. Unfortunately, network function virtualization introduced the concept of running network function software on general purpose commodity servers in order to enable high-performance software-based traffic generators at an affordable price. However, high-performance traffic generation is a non-trivial task. For example, our previous work identified that generating packets at 100 Gbps cannot be achieved using a single CPU core on the commodity server platform. This is due to packets being required to load into limited L1 or L2 per caches. Therefore, it's necessary to make full use of the multi-core processor's processing capacity in order to distribute traffic generation and send tasks to multiple cores. On the other hand, generating packets across multi-cores simultaneously cannot guarantee the packet sequence. As shown in the figure, a flow consists of 6 ordered packets that must all be sent simultaneously by both CPU cores in order to maintain performance. This could lead to a misordering in the flow, since packet 4 might end up being transmitted before packet 3. And moreover, traffic replay is a key functionality of traffic generators, but high-performance traffic replaying is challenging. For example, when replaying traffic from trace files at 100 Gbps, theoretical calculation indicates that 12.5 GB files must be loaded into the memory for only a second packet replay. The huge amount of data can significantly burden the memory system. So to address the aforementioned issues, we present a software-based traffic generator, Mimoco. It sends packets at 100 Gbps line rate speed without compromising the packet sequence. And it can also replay real-world traffic from trace files with minimum memory usage overhead using ML model-based fixed-size memory footage. And Mimoco employs a memory reserving strategy in which each core reserves its own block of memory space in the TX queue, ensuring that packets generated by the core are delivered in the proper order to the traffic. Meanwhile, Mimoco used an efficient scheduler to adjust the space based on sending rates, allowing the overall traffic generation task to be divided into subtasks and the generated packets to fit into the reserve space. And to address the huge memory consumption in the traffic replay, we employed a linear regression to learn from the pickup file. Motivated by ML-based approach to compress videos, which choose keyframes and calculates the other frames based on the trend learned from the video. Likewise, we set all flows at a keyframe and learn if a flow is sent at a particular time. And therefore, the memory usage for the whole pickup file is just a keyframe, and the ML model only consumes a fixed-size memory. Next, replaying the pickup file is converted as generating packets based on the ML model. The build of the ML model can be conducted when capturing the packets. So to summarize our work, we have identified the challenges in high-performance traffic replay on general purpose commodity servers, and we present Mimoco and introduce its key design. This work is currently pretty primary, and we intend to keep working on it. We present the primary design here to broadly call for comments on our design. And thank you for your time, and I'm now happy to answer questions.
Okay, thank you. Thank you, Lianzhen.
Okay.
Is there any questions from the audience? Okay, if not, let me raise a quick question.
Okay.
So you said you have 100 Gbps traffic relay. Okay, so how to verify the packet sequence guarantee and guarantee the 100 Gbps replay rate? Is there any theoretical or experimental results yet?
Actually, we have recently done some experiments, and we are integrating the results these days. And basically, we can implement the traffic generator in high performance. If you are interested in it, we can email to you.
Okay, I see. Thank you.
Okay, thank you. Okay, thank you very much. And I will end my screen sharing.
Okay, thank you. And I think we can move to the last poster. Jianjun, are you here? Okay, please open your microphone and video.
Hello, can you hear me?
Yes, I can hear you, but I cannot see you.
Okay, I have, yes, wait a minute.
Okay.
Can you see me now?
No, but I think that's okay. That's okay. I can hear you. So let's start, and let me introduce.
Okay.
Let me introduce the last poster. The title is W-thread AFL, deterministic gray box fuzzing for multi-thread network servers. The presenter is Jianjun Lu. Jianjun received a bachelor degree in information security from the National University of Defense Technology. He is currently working towards the master degree in computer engineering with the Department of Computer in NUDT. And his research interest mainly focuses on network protocol fuzzing and IoT security. Okay, Jianjun, you can begin.
Okay. Hello, everybody. I'm glad to share my topic with you, the work about deterministic gray box fuzzing for multi-thread network servers, and the authors are Jianjun Lu and Bo Yu. The contents includes 4 parts: background, challenge, method, and evaluation. Network protocols are the communication rules between devices on the internet, and network servers are the implementation of network protocols. They are developed by people of all levels and was exposed to everyone. Since they are developed by people of all levels, so they might have bugs because of human factors. And the network servers are exposed to everyone, which means the attackers can exploit it remotely. All of these features make network servers and attract victims. Thus, it's necessary to find and repair the vulnerability of network servers. Coverage guide fuzzing is a relevant vulnerability discovery technique, using irregular inputs to trigger bugs. Look at the right picture. At compile time, we inject probes to the source code. Then we get the problem on the test. At fuzzing time, we choose C from the corpus and mutate it, then send it to the program. The probes we inject before will collect coverage. And when the target suffers failures or VSA, one round of the fuzzing ends. The core idea of it was the unsupervised evolution of seeds. To be effective, we have to filter more valuable input to mutate. And the coverage guide fuzzing consider that more coverage means better. So what is coverage? As we all know, a problem consists of lots of basic blocks. When we from a basic block jump to another basic block, we recall the branch to a map based on their IDs. The count of the map indicates coverage. Just look at a simple example. The function full, if x less than size of buff, then return buff. Otherwise, return 0. The simple code will be compiled to a program with 3 basic blocks: the start basic block, the left basic block, and the right basic block. If the condition was satisfied, the ID1, the start basic block, and the left basic block will be executed. Then the probes we inject at the compile time will collect coverages. We will record it to a map. So then the count of the map indicates the coverage. However, when the researchers apply the fuzzing technique to network servers, they encounter problems. Since the network servers have special behaviors, the main thread of network servers always act as a background thread. They just keep listening. And when the client connection comes, they spoon a subthread to communicate with the client. So the worker thread, we call it worker thread. The worker thread contains the key data and logic. That will cause a problem. That is, random scheduling of multiple threads will lead to non-deterministic coverage feedback. As we mentioned before, the actual branches is root to left or root to right, but the scheduling will cause when the scheduling occurs, the branches may be left right or right left, left root or right root. These branches are all fake branches and will limit the performance of the fuzzer. So to achieve, and researchers always measure the non-deterministic behavior using the stability metric. The stability metric was calculated as follows. We repeat to send the same C for 40 times, and we get the maps for in different times. We just compare the map 0 and map I. We count the same nodes to D. We count the total nodes to A, and the stability equals to D divide A. And we find the state of our fuzzer, APNet, has poor performance on the benchmark dataset, Professor Bench. As we can see, 9 of 13 are multi-thread programs and cover 6 of 10 protocol times. And all of these multi-thread programs behave low stabilities, less than 90%, some even less than 50%. So to solve this problem, our basic idea was that since worker thread contains key data and logic, so to be deterministic, just focus on the worker thread. So the challenge is how to achieve thread-aware feedback. We need to do 3 things. First, we need to know when the worker thread was created. Second, we need to distinguish the worker thread and background thread in basic block level. 3, we need to control the execution of feedback flows. Our methods are as the following. We achieve thread-aware feedback based on LLVM. LLVM is a IR editor. We at compile time, we inject codes in the basic block using the LLVM IR path, and then we get the binary programs to fuzzing. It looks like this. We check function pthread create or fork using the worker thread context. It was injected in the middle of the primitive code, and we inject current thread context flows in front of the basic block. And we inject recognition flows in front of the feedback flows to control its execution. Then we evaluate our work with 3 questions. First, can we increase the stability metric? Second, can we cut down fake branches? 3, will we not reduce coverage while we ignore the feedback of main thread? The data set is 4 benchmarks of Professor Bench, and we compare with the state of our coverage guide faster, APNet. And the results are as displaying. The stability we increase 2% to 25%, and the fake branches we cut down by 90% to 39%, and the coverage is similar. So in conclusion, our approach increase stability, and we are able to cut down fake branches, and we will not reduce coverage. That's all. Thank you.
Okay. Thank you, Jianjun.
Thank you.
Is there any questions for the last talk? Okay, let me ask a question for you. Because you mentioned your method is lightweight, so how to evaluate the overhead or the cost of your proposed method?
We can count the total acid, the acid times in an hour. One is the original method. One is our method. We can compare the fuzzing round, the total number of fuzzing rounds in an hour. And I have do the experiment. I find the original method and our method behaves similar performance. Yeah. Yes.
Okay. Okay, I see. Thank you.
Okay, thank you.
Thank you. Okay, that's all. And that's all for the poster session. And also that's the end of the APNet. Thank you very much for attending this section and also for attending the APNet conference in 2022. Thank you very much.
Thank you.